Page 1, Page 2, Page 3, Page 4, /IDACMLI Science / an Honorap Stability in Aviation. Macmillan & Co., Limited, London. Bombay. Calcutta, Melbourne, The Macmillan Company, New York. Boston, Chicago, Atlanta. San Francisco, The Macmillan Co., of Canada, Limited, I. Toronto. Stability in Aviation, an Introduction to Dynamical Stability as Applied to the Motions of Aeroplanes, KVG. H. Bryan. SCD. FRS IUOFSOC L. KT Urindipli. Aero-Mathematics in the University College of North Wales, formerly Fellow Officer House, Cambridge, Macmillan & Co., Limited, St. Martin's Street, London, T91-1. L. Uckhard Clay & Sons, Limited, Brunswick Street, Stamford Street, S.E. Anbangav, Suffolk. Preface. Up to the present time, the problem of stability has received very inadequate attention in connection with aviation. From that point of view of practical aviator, this is, perhaps, little Tobe wondered at. It would scarcely be possible for him to devote months of concentrated attention to long and laborious stability investigations, when it is no exaggeration to say that very frequently his success or failure depends, above all things, on the clarifies off downs at which he starts andlands. If a prize I suffered for a flight from Folkestone to Flushing, it is useless for him to fly from Harwich to the Hook, even on a much more stable machine than that used with you in her off the prize. Show ed that the publication of this memoir will add to aeroplane stability, being made the subject of much more continuous study and investigation than has been possible in the past. A general abstract of the present investigation is contained in the introduction, which may be buried with advantage before proceeding to tales of a more mathematical character. The general conclusions show that there should be no difficulty in securing inherent stability, both longitudinal and lateral, in an aeroplane, by means of suitably placed auxiliary surfaces rigidly attached to the machine, in order to achieve success. The conditions of stability must be very carefully studied, and account must be taken of the effects of 6. Preface. The inclination of the flight path to the horizon, and other causes which may affect their result seriously. There seems a general desire on the part of many writers to minimize the dangers of instability or defective stability, and to attribute accidents to their causes. But in reading the accounts of accidents, both fatal and otherwise, that appear every few days in the daily papers, it's difficult to avoid coming to the conclusion that much of thy's loss of life and damage could be avoided by a systematic study of stability, and certain other problems regarding the motion of aeroplanes particularized in this book. To the mathematician who is able to devote any time to original work, a wide region of unexplored ground is opened up, of which it has, in many cases, only been possible to exhibit glimpses in these pages. There's a freshness about this region which can scarcely be found to the some extent in searches for differential equations that they've not been integrated, high primes, or further additions to a large existing collection of properties of triangles and circles. I do not think any mathematician who cares to take up the subject now will experience any difficulties comparable with those which have been encountered in the preparation of the present book. There is abundant work, too, or the student how wishes to undertake research for educational purposes, and aeroplane stability seems to be a very useful alternative for some of the branches of applied mathematics now taught in our universities. Quite recently, much has been written regarding so-called automatic stability, depending on the use of gyrostats, pendulums, or other movable parts. Apart from the effect that movable parts are reliable to stout offer, it must be remembered that they increase the number of degrees of freedom of the machine. Thus further, Fs Roman 7 adding to the number of conditions which have to be satisfied for stability, a number quite large enough already. You anticipate that the successful aeroplane of the future will possess inherent, not automatic stability, movable parts LEing, used only for purposes of steering. The great difficulty in writing this book has been thinniness of the subject, and the fact that the further one advances in it the greater appear the possibilities of still further exploration. The selection and arrangement of the text has thus been much more difficult than it would be in a book compiled from existing literature. I have tried, saw for as possible, to avoid introducing any investigation, their results of which were certain to be only of academic interest, but this attempt has not made it much easier to draw the line. For example, the transformations of section 30, which are, of course, particular cases of a more general transformation, WR placed on the excluded list, but their application to the pendulum experiment suggested the desirability of retaining them. One pleasant duty remains, and this is to record me indebtedness to Mr. E. H. Harper for the valuable services he has rendered in connection with the investigations here described. To claim priority for him in many of the results. It was Mr. Harper that directed my attention in the first instance to the important effects of the inclination of flight path on stability, and the investigations of lateral stability of Antoinette type, and several other forms, are entirely due to him. The whole off the Formula 3 in this book have been checked by independent working by Mr. Harper and myself, and one hoped that the error correct. Besides Mr. Harper, Mr. A. Ferguson and Mr. Robert Jones have revised theproofs and made a number of corrections. It is impossible to be careful in a Omen 8 preface matter W lyric amir slip of facine might change stability into instability, and for this reason it is desirable that readers should, as far as possible, keep a farther check on the Formula E, even in spite of these precautions. Last but not least, me thanks are due to Prof. R. A. Gregory not Onel for his unfailing kindly advice and assistance in the preparation of the text. You'd also forhise offer to include a volume on the investigation of stability in the series of science monographs, of which heist editor. There are probably many instances, of which this ISON, in which a volume of this kind presents a more appropriate medium for the publication of results of investigation than the proceedings or transactions of a scientific society. Had it not been for Prof. Gregory's timely invitation, the theory of stability would have been developed much less fully than has now been done in these page. G. H. Bryan. Contents Introduction and Summary Chapter IIAR 1 Chapter Roman 2 Fundamental Principles 19 Chapter Roman 3 General Considerations regarding Symmetrical Derivatives 38 Chapter Roman 4 Graphic Statics of Longitudinal Equilibrium 57 Chapter V Longitudinal Stability of Sin, Lilifton, Cyst, MS 75 Chapter VI Longitudinal Stability Octable Lifting System. Extension of results TOSI stems other than narrow aeroplanes moving at small angles 95 Chapter VTI Asymmetric, or L. Lateral Stability, Straight Planes and Vertical Fins 123. Contents Chapter Roman 8 Lateral Stability Bent Uplanes 151 Chapter Roman 9 Schnurl Conclusions 165 Chapter XT Ompikison with Other Theories 171 Chapter Roman 11 Problems 178 Notes 181 Nomenclature 185 Notation 188 Stiff illustrations of airplanes *J*. The following illustrations, distinguished by Roman numerals, will, it is hoped, enable their reader to visualize the systems of planes described in the text, or systems resembling them, better than would be possible from the diagrams bearing Arabic numbers. They also suggest material for further research. Under each figure will be found a brief statement of the particular points which it illustrates in connection with stability. Figure PA IKI. A Chinook glider 58 Roman 2. The late M.E. Lefebvre flying at Reims 96 Roman 3. U.R.E. Mines biplane at Doncaster 110 Roman 4. M. Henry Farman flying at Blackpool 118 V. Glenn Curtis biplane at Rages 130 VI. Diagrammatic view Ofer Wright biplane used at POW 139 Roman 7. Raugier flying at Blackpool 143 Roman 8. A monoplane in construction by Blériot in 1907, 152 Roman 9. Latham's Trial Flight 160. Page 16, Stability in Aviation Chapter I Introduction and Summary 1. The development of the aeroplane has opened up a large number of interesting problems in both theoretical and experimental mechanics. One of these problems is the investigation of the pressures on plane and other surfaces moving in a given manner through a fluid medium such as air. This problem had attracted the attention of mathematicians long before applications to aerial navigation had reached the stage of practicability. The earliest attempt at such an investigation was that due to Newton, who assumed that the resultant pressure on a lamina could be measured by the momentum or change of momentum imparted, per unit time, by the lamina to the particles with which the lamina came into contact. This led to the so-called sine-squared law, according to which the pressure on a plane lamina appeared to proportional to the square of the normal velocity of the lamina relative to the surrounding medium. The kinetic theory of gases, Newton's assumption might reasonably be expected to hold good in the case of rarefied gas, in which the mean free path of the molecules was large compared with breadth of the lamina. The second method employed was the theory of discontinuous fluid motion, introduced by Helmholtz, to Introduction and Chap, and Kirchhoff F. Wickley forms the subject of a memoir by Sir George Greenhill, published by the Advisory Committee for Aeronautics. Divergences between theory and observation necessarily arise from the character of the assumptions required to bring the problem within their range of analytical methods. Failure of Newton's law showed that it was impossible to estimate the pressure without taking into account the current set up in the medium in the neighborhood of the lamina. In spite of these, many writers, even at present time, seek to establish formulae for the pressure on moving planes by reasoning which is more or less Newtonian in its fundamental characteristics. But it will be evident that such methods should only be adopted with great caution, their results being treated more or less in the light of empirical formulae, which must stand or follow experimental evidence. In the case of the theory of discontinuous motion, we are limited by mathematical difficulties to consider a tion of a perfect incompressible fluid, and divergences between theory and experiment necessarily arise from the differences between the physical properties of such an assumed medium and those of air, or of whatever as the case may be. Moreover, the soluble problems in general only refer to two-dimensional motions, so that in any case the necessary conditions would only be satisfied as approximately in case of aeroplanes the so-called aspect ratio of which is small, and the theory would fail in the neighborhood of the extremities of such planes. In this particular problem, a suitable balance between theory and experiment has been sought by the publication Report on Theory of a streamline past a plane barrier, and of the discontinuity arising at edge, with application of theory tone aeroplane, by Sir George Greenhill, F.R. S.P.P. 96+106 Fig. S. Advisory Committee for Aeronautics Reports and Memoranda No. ID London H.M. Stationery Office Wyman & Sons Limited, Price 5s. Summary 3 of Sir George Greenhill's report by the Advisory Committee. W. Leakley has been organizing the construction of apparatus for the experimental determination of air pressures on moving PHMS. 2. In the problem of aeroplane stability here discussed, where are concerned with the motions or changes of motion set up in the flying machine itself by these pressures, and by the other forces acting on it when equilibrium in steady motion is disturbed. This problem, unlike the previous one, is a direct application of the principles of theoretical mechanics involving theory of the equations of rigid dynamics. About the validity of these, no question can at present arise. Theon lie further assumptions are the expressions for the air pressures on planes and other parts of the machine, and the closeness of agreement between theory and observation in any particular calculation will depend on the degree of approximation, to which these pressures are represented by the formulae assumed for them. The present subject has hitherto not received so much attention as it deserves, owner reason, probably, being the complexity of the algebraic formulae which present themselves at the outset, and another, doubtless, the success with which aviation has been accomplished on machines, the stability of which hasn't been studied. When the Wright brothers made their first flights, texture at issue was one of motive power and weight, and an important condition for success was the reduction of weight and head resistance by avoiding the introduction of any more auxiliary surfaces than were absolutely necessary. If these involved instability, its effects could be overcome by skill and experience, and in particular lateral control was obtained jing the wings. Since then many attempts have been made to circumvent the Wright patents, with their result of diverting attention from the question of inherent lateral stability. B2. For Introduction and Chap. The Bryan Williams paper of 1903 was, I believe, the first attempt to direct attention to the mathematical aspect of texture, and it was intended to be suggestive rather than conclusive. The late Captain Ferber, whose papers were published soon afterwards, investigated independently the equations of motion of an aeroplane, and they subsequently applied the method of small oscillations to the problems of both longitudinal and lateral stability. This constituted the first attempt at a theory of lateral stability. Unfortunately, however, this last is defective in several respects, and the results probably fall rudely off the mark when applied to aeroplanes the main surfaces of which area of considerable span, as is usually the case. In Mr. Lanchester's second volume on aerodynamics, which appeared in 1908, the problem of stability, both longitudinal and lateral, is treated from a highly original point of view, theory of the equations of rigid dynamics being practically avoided. Of more recent contributions we have the papers of Prof. Marcel Brillouin and Dr. H. Riesner, the latter of whom has considered the problems of both lateral steering and lateral stability, while the Government Blue Book CD 5282 contains abstracts of papers by Lute Croco on the steering and stability of dirigibles, and B.M. Soro on similar problems for an aeroplane, with a special reference to longitudinal stability. This group of papers arrived after the investigations here discussed had been completed, and only a brief comparison of the results has been attempted near the end of the present work. 3. In this book the 6 equations of motion are first written down, and then applied to the small oscillations about steady motion of a body, such as an aeroplane moving in air-assisting medium. If first intended to measure forces in dynamical units, and perhaps the equations would have been a little simpler. 1 Proc. R.S. June 1903. A summary 5 if this had been retained, but for the sake of convenience, gravitation units offers have been substituted, the equations being based upon the homogeneous system. RR1T71 acceleration force equals YO lit x 9, which is no recommended by Datcher's Ophiolmetry mechanics, and avoids both the poundal and the slug. Advantage arise when air pressures are measured in pounds or grams W8 per unit of area, instead of poundals or dynes. In the case of an aeroplane which is symmetrical with respect to plane which is vertical in steady motion, the small oscillations fall into groups each determined by 3 equations of motion, and no further separation is at the outset possible. The The first group represents motions in the vertical plane on which longitudinal stability depends. They may be better described as symmetrical oscillations. The second group determines sideways rotations and displacements tuned side or thither off the plane of symmetry. These should be called asymmetric oscillations. On the off these depends the lateral stability off the machine. Some writers attempt to separate the three motions here considered, and treat separately the stability forrolling motions and directional stability, a mistake which Lanchester avoids by using the term rotative stability. It is important that the interdependence, not only of the rotational oscillations, but also of sideways displacements, should be taken into account. It is only through the latter displacements that gravity can have any effect on the direction of an aeroplane. Without such an effect, there can be no tendency on the part of an aeroplane to right itself after it is shield over sideways, and in the absence of such a tendency the aeroplane, if it has settled tuned side, will its introduction and chap, liable to side slip with uniform acceleration. In most existing aeroplanes, TLI's tendency is counteracted by warping, but it does not follow that because this plan can be successfully used, it is necessarily the lie or the best plan. Fourth, a second kind of stability Thebes name would be Asymmetric stability. We shall sometimes, for shortness, use the term lateral stability to note the stability dependent on this group of displacements in spite of the term having been used in a more restricted sense by other writers. 4. The effects of air resistances in each group of equations are represented by 9 coefficients, or 18 in all, which may be called the resistance derivatives. 1. Elimination, the frequencies and logarithmic decrements, or in the case of instability, logarithmic incitements. Of symmetrical oscillations are determined by an equation of the first degree in \, where the displacements are assumed proportional to E. This equation involving the symmetrical resistance derivatives. The conditions of stability require that the coefficients of the biquadratic, as well as Routh's discriminant, should be positive. Exactly similar conditions apply to symmetric oscillations, which again lead to a biquadratic in \, involving the 9 asymmetric resistance derivatives and corresponding conditions of lateral stability. The actual coordinates of the center of gravity, as well as the azimuth, do not occur in the equations of motion, or the corresponding velocities do so. The reason is that the conditions of equilibrium of an aeroplane, like those of a ship, do not depend on its position or compass bearing. For variations of these, equilibrium is neutral. The resistance derivatives are proportional to the velocity of the aeroplane when in steady motion. The problem as no before us resolves itself into the determination of the expressions for the resistance. A summary 7 types of the planes based on the available formulae or data regarding the pressures on them. 2. The evaluation and simplification of the coefficients in the biquadratics and their discriminant. 3. Analysis of the general character of the oscillations. 4. Separate discussion of the effects of various subsidiary causes which may affect the stability of an actual flying machine. First object Tobkep, in view is to evolve something like order out of the chaos of algebraical symbols that present themselves at the outset of the inquiry. This can best be done by a method of successive approximation and building up, the problem being at first treated subject to the simplest possible assumptions, but methods adopted being sufficiently general and elastic to allow of subsequent modifications, corrections, and extensions of the most general character. In this book, attention is concentrated on the mathematical aspect of the problem for several reasons. In the first place, there is no obvious alternative between developing the mathematical theory fairly thoroughly and leaving it altogether alone. Any attempt at via media would probably lead to erroneous conclusions. In the second place, the formula arrived at, even in the simplest cases, are such that it is difficult to see how they could be established without a mathematical theory. In the third place, there is probably no lack of competent workers interested in the practical and experimental side of aviation, and under these conditions it is evident that the balance between theory and practice can be improved by throwing as much weight as possible on the mathematical side of the scale. Lastly, Bishop to advocate the claims offer a plain equilibrium and stability as an educational subject suitable for study in our universities alongside with such branches of applied mathematics and mathematical physics as hydrodynamics and particle and rigid dynamics. 5. Starting with longitudinal or symmetric stability. The 8. Introduction and chap. Available experimental data refer to the air pressures and positions of the centers of pressure off plane and other areas, movino through air with given relative velocities of translation. If a lamina has an addition a motion of rotation, as when an aeroplane begins to pitch, the effects of this rotation appear to but present unknown. In all existing theories of stability they have been neglected, and at that time offertino no indications have reached us off the matter receiving attention at Hague Government Laboratory. The effects referred to introduce 2 constants or coefficients into the equations, and these equal-rotary derivatives. Apart from mathematical considerations, determination of these effects would be matter of common prudence, as rotations may easily put an aviator in tone-awkward predicament, especially when near landing. The experimental problem may, if desired, be reduced to the determination of woe points which are shown to exist in the plane of the lamina, such that rotation about one does not affect their resultant pressure, while rotation about the other does not displace the center of pressure. Two methods of experimenting are suggested. The difficulty is meanwhile obviated by the use of narrow planes for which the rotary derivatives are negligible, stability being secured by auxiliary surfaces, such as saddle. But in this case, the variations in the center of pressure will also, in general, be small. Whereas this led to a theory of narrow planes flying at small angles. This theory forms the best starting point for the systematic study of airplane motions, in just the same way that the definition of a perfect fluid forms the starting point in hydrodynamics. The theory of refraction of narrow pencils at small angles of incidence in geometrical optics, or theory of elliptic motion in planetary theory. According to the hypothesis, not only are rotatory derivatives and variations of the center of pressure neglected, but summary 9 pressure is assumed proportional to the sign of the angle of attack, or what is the sum thing, to the product of the resultant and the normal velocity. A conclusion described as the principle of independence of height shows that, subject to certain limitations, the stability of an aeroplane is but very slightly affected by raising or lowering its planes. For this reason, there is practically nothing to choose between monoplanes and biplanes in this respect. 6. Section on graphic statics of longitudinal equilibrium stands by itself apart from their stuff book, and will, it be found instructive. It is sometimes a little difficult to see how the conditions of equilibrium of a flying machine are altered by varying the propeller thrust or altering the inclinations of planes, and the object is to exhibit the results by means of geometrical constructions. This section might very well be at university students. 7. The simplest case of longitudinal stability is that of a single lifting plane with a neutral, auxiliary tail propelled horizontally by a constant horizontal thrust passing through the center of gravity. The condition of stability agrees with Lanchester's result. By the use of the equations of equilibrium, this condition may be put into several alternative forms, one of these being independent of the velocity of propulsion. The further use of approximate methods, the roots of the biquadratic are separated, the short and long-off oscillations discussed, and their ONO characteristics described. It is shown that Lanchester's method only applies to the long oscillations, but fortunately for Lanchester, these are the oscillations on which stability mainly depends. In a non-horizontal path, the stability varies very greatly with the inclination of the flight path to the horizon. The important part played by this inclination was found out, both for longitudinal and for lateral stability by Introduction and Chap. Mr. E. 11 Harper. A glider has greater longitudinal stability CW teres paribus than a horizontally propelled aeroplane, and when an aeroplane rises, the longitudinal stability rapidly falls off. Under simple assumed conditions, longitudinal instability sets in when the tangent of the elevation has some value less than twice that of the angle of attack. If find, however, at longitudinal stability is in general increased by head resistance, and a further increase occurs when the propeller thrust is a function of the velocity, which decreases with an increase of velocity. Both these effects are conveniently represented as being equivalent in their effects on stability, to depression of the direction of the flight path, through an angle for which a formula is given. The machine can therefore rise at a stepper angle than before without losing stability. By a doubly lifting system, mean two lifting planes placed tandem, or what comes to the same thing, a front lifting plane and a lifting instead of neutral tail. Stability investigations, it must be remembered that superposed planes practically count a zone of the same total area. Here a property is proved, which may be called the principle of equivalent systems, which enables the combination of two planes in question to be replaced by an equivalent single lifting plane with neutral tail, the two systems having the same conditions of equilibrium and also of stability, and in addition, the same total combined area of their planes. Without the substitution, the stability of doubly lifting aeroplanes involves the simplification of unwieldy formulae. For the mathematical student, the properties of equivalent systems and their invariance afford some interesting applications of determinants. From a technical point of view, the conclusion to be drawn is that there is no advantage or disadvantage in a lifting tail escom paired with a neutral one except that the neutral tail will. Summary Roman 2 have tobe the longer of thetwo. In an actual aeroplane where the pressure on three planes is affected by the wash off the front ones, the machine with the neutral tail would, lie, have the greater lifting capacity. In the following sections, the necessary modifications are considered forge, ropeller axis not passing through center of gravity, Variations in the position off the center of pressure as thingle off attack varies. The principal corrections for cambered planes. Effects often tangential or frictional resistances, raised planes, deviations from the sine law of resistance. Wash on tail plane produced by front one, and rotary derivatives. The discussion of these corrections might be extended almost indefinitely, and in order to draw the line somewhere, I have in some cases thought it sufficient to indicate the methods only. The effect of variations in the position of the center of pressure calls for a little comment in view of discussions that have already taken place on this subject. The sections dealing with this effect, two cases have been considered. One is the case where stability is mainly dependent on the action of an auxiliary tailplane, which in this case must not be parallel to the front plane, and the effect of the variations in the center of pressure takes the form of a small correction in their salt. The second case refers to the stability of a single plane, which is entirely dependent on the variations in question. Of course, the latter solution is not altogether satisfactory, owing to the fact that few known rotary derivatives have been neglected. Now, when the conditions of stability are taken in conjunction with the conditions of equilibrium, it is shown that this stability dependiog on the tail action is independent of the velocity of the aeroplane, but the stability of tailless aeroplane decreases as the velocity increases. This confirms the view that, using off a tail efforts, the more efficient means of securing inherent longitudinal stability. 12 Introduction and Chap. As has been observed, the conditions of longitudinal stability can be exhibited in various forms by making use of the equations of equilibrium, so that apparently widely different conditions may in this way be equivalent. A three-plane system, such as a lifting plane with auxiliary surfaces fore and aft, is shown, in certain circumstances, to possess advantages over at-will plane system in respect of stability, especially when rising in the air. It will thus be seen that the mathematical method is not limited in its application to the simplest case of an ideal aeroplane, but that account can be taken of practically all the modifications occurring in an actual flying machine as soon as the necessary data become known. And in any case we'll find out which modifications increase and which diminish the stability. At the outset of investigation a certain determinant was found to vanish, and this fact was of great importance in simplifying the analysis which, but for these, appeared of great difficulty. The discussion of three-plane system. The fact that this determinant does not vanish is important in indicating the greater stability of such a combination. 8. Lateral or asymmetric stability presents a difficult problem possessing many interesting features. In this case, the couple's setup rotations off the main planes depend on the span instead of breadth off planes, and instead of being negligible play a very important part in stability. To obtain expressions for them which may at least be regarded as approximate, a further assumption Hastob made regarding the distribution of pressure on them. This assumption being regarded as a further property which Hastob implied in the definition of narrow planes gliding at small angles. The couples in question are turning moments, which are so well known in aviation, and are usually counteracted. Summary 13 by operating ailerons or warping. In lateral stability, however, we have to consider separately in turn the effects of straight main planes, auxiliary vertical surfaces or rudders which may be called fins, bent-up wings and slanting up lanes fixed at extremities off the main planes which may be called stabilizers. An airplane having straight unbent-up planes without fin source stabilizers is devoid of lateral stability. Moreover, a horizontal auxiliary tailplane, such as is used for maintaining longitudinal stability, does not enter into the equations of lateral motion unless it's been considerable. If a single vertical fin is added, there is great difficulty in reconciling two of the stability conditions. If the fin is placed in front and near the level of the center of gravity, one condition is satisfied but not the other. If placed behind and near the same level, the second condition is satisfied but not first. Stability might possibly be got by placing the fin above the center of gravity and slightly in front, the height above being larger compared with the distance in front, viewed as small change in the motion of the aeroplane would be liable to render it unstable. The objections to fin raised considerably above the C.G. are evident. That most existing aeroplanes are laterally unstable is a necessary further deduction. This difficulty can be got over with use of fins instead of on. We have here to investigate the difference between the effect of several fins and that of a single fin of the sum total area placed at air center of pressure, and as the expressions involved are the moments oftener show off the rears of the fins, we transform the Sebi theory of parallel axes. We find that the horizontal distance between the fins has much more effect on stability than a difference in height. Probably the best arrangement ISON, in which the aeroplane is provided with 12 fins placed fore and aft, and 14 introduction and chap, raised somewhat above T center of gravity, saw that their center of pressure is vertically above the center of gravity, or nearly so. This arrangement is shown to possess a wide range of stability which is practically unaffected by the noi W Hickley the direction off Lea makes with the horizon. The condition for stability requires that the height of the fin should not exceed a certain limit. If instead weplace the fin set the same level as center of gravity, their center of pressure must be in front of it, and the stability is secured by making the distance between the fin sludge and the distance of center of pressure in front of the center of gravity small. This arrangement will be stable in horizontal or ascending flight, as also in a gentle descent, but the aeroplane will become laterally unstable and liable to turn round sideways if it dives downwards at an angle to the horizon equal to or greater than twice the angle of attack. A third arrangement, which like the last was investigated in the first place by Mr. Harper, has a vertical tail fine and descon vertical fine directly above the center of gravity. For stability, the tail must not be less than a certain length, and in this case it is found that stability decreases when the aeroplane is ascending, thus leading to alimit to the noi offlivation. The general character of lateral oscillations is discussed. Also the general FEX off couples due to head resistance, twin screws, friction, and camber. When consider the effects of stabilizers, Orban uplanes attached to tie JS off viewings, or infict wings WDTH bent tips, and bent up wings in general. It is natural to suppose that a pair of stabilizers is equivalent to vertical fin. This is, however, shown to be only true in certain conditions, such as when they are placed at grazing incidence with the line of flight, or are neither before nor behind the center of gravity. Thetwo solutions which follow are due to Mr. Harper. The first, summary 15, discusses the stability of an aeroplane fitted with stabilizers. The second, the Antoinette type of aeroplane, furnished with bent-up wings and a tail fin. Mr. Harper has shown that lateral stability in this case can be obtained in two ways. Neglecting the tail, it is sufficient to raise the dihedral angle off viewings above the center of gravity, butin this casether is a superior limit toichite. Or again, without raising viewings, the tail must be made not less than a certain length. In the first method, stability falls off when the aeroplane is descending. In the second, it falls off when rising, so that by a judicious combination of raised wings and tail, stability may be made practically independent of the elevation off the flight path. 9. Under the heading of general conclusions, no attempt has been made to give a detailed summary of Theurk, the shaving been done in the present introduction. The discussion refers chiefly to the diversity of opinion, which now exists as thought advantages and disadvantages of inherent stability. There is, however, annulment of indeterminateness in the arguments relating to this particular point, arising from the fact that a complete investigation of airplane motions involves the solution of other problems besides that of stability. A list of some of these problems is given at the end, while some of them afford materials for experimental research. List should afford most skeptical reader evidence as to the necessity of a large amount of further original work of a purely mathematical character, in which all that is required is the deduction of conclusions from definite stated hypotheses. At present, there is widespread belief that the methods of exact science cannot be brought to bear on the study of aeroplane motions, owing to the uncertain conditions to which they are subjected. Yet after all, the cause of the uncertainties probably lies in the fact that the study of aeroplane motions has not received so much attention on the part of I6 introduction and chap. Matlinetitions a shassel in given to their problems of a similar character. 10. A brief discussion is given, dealing with investigations of a need character by other writers. It will be seen that in several cases erroneous conclusions have been arrived at through not starting with sufficiently general hypotheses, a frequent cause over being failure to recognize the interdependence of the three components of lateral motion. In this respect, Lanchester's work forms a conspicuous exception, although has approached the subject from an entirely different direction from Thather adopted, and has avoided theosophthexual equations of motion. 11. If we consider only the problem of stability, in which it has been attempted to have at some approach to definite understanding in this book, it will be seen that this problem presents many complexities, which it would have been very difficult to foresee from experimental evidence alone. Indeed, it should be inclined to think that the difficulty weighs almost as great as that which would be experienced by any one who endeavored to explain the motions of the solar system without the assistance of the theory of gravitation and the fundamental equations of dynamics. The dependence of stability of airplanes on the inclination of their flight paths to the horizon is very difficult to explain from first principles. But an attempt at such explanation has been given in anno. These difficulties and the large number of problems still awaiting solution must be a justification for appeating theplia forth recognition of motions of airplanes as a subject for study, research, and original work by teachers and students of mathematical and physical science in our universities. A sub-branch of higher applied mathematics, the study of aeroplane motions, has been sadly neglected. The vaguest notions still prevail even a stothiver meaning of. Summary 17 Stability. The subject presents claims off the most urgent and pressing character for systematic study and investigation on similar lines, those which have been followed in the development of other branches of mechanics and mathematical physics, and it is on the bathy cooperation of university, teachers in mathematics and physics, that the present anomalous conditions can be remedied. No less strong arithmetic claims off the study from an educational point of view. Will be seen that the subject matter contained in these pages contains several interesting methods, including applications of properties of determinants, theory of approximations, and the principle of equivalent systems, as aptly taughtable lifting aeroplanes. Further, the introduction, step-by-step, of corrections which need in no respect stop short of practical requirements, and may be possibly carried to stage even beyond what is sufficient for ordinary needs. To see how matters stand, let us compare the study of aeroplane motions with some subject which is already largely studied and taught in our universities, say hydrodynamics. I have here a branch of applied mathematics which has been developed on the theoretical side, quite independently of the requirements of the hydraulic engineer. Many of its problems refer to hypothetical motions in an indefinitely extended ideal medium, and are far removed from any possibility of practical application, yet none questions the educational value of the training afforded by their study, even to engineering students. No any hunter student who devotes a year or more to the systematic study of hydrodynamics will at the end of that time have little prospect of finding any problem, practical or impractical, which has not already been solved, and which he can approach with any reasonable chance of obtaining a solution or result worth publishing. The present subject, on the other hand, literally bristles with unsolved problems, and the difficulty isn't so much that I8 introduction and summary the problems are insoluble as that their solutions are long and tedious. For this reason, it is important that the number of persons interested in the subject should no longer be nearly countable on the fingers of own hand. 12. There still remains textion of examples. An almost unlimited number of these can be obtained by applying the formulae and methods of this book to existing aeroplanes, the dimensions of which will be found in the principal aeronautical journals and manuals. Possibly readers of a practical turn of mind might have preferred to see some of the calculations worked out here. This, however, is quite unnecessary as the calculations are easy and well within the powers of a fair student of B.Sc. standard. In the case of numerical calculations, there is no need to limit theory to substituting values in conditions of stability. It is easy to obtain the coefficients in the biquadratic and to determine approximate values for roots. This way the periods and logarithmic decrements of oscillations can be found, or in cases of instability their logarithmic increments. Thus, even if it is decided to sacrifice some of the conditions of stability in the construction of an aeroplane, the effects of the sacrifice can be made the subject of calculation. As different new forms of aeroplane are constructed, fresh examples are continually suggesting themselves. For this reason, it would have been futile to recoup any of these pages with calculations, which would soon be out of date. Examples on longitudinal stability were worked out by Mr. Williams in our joint paper of 1903 referred to above. Roman 2. Fundamental Principles, General Equations of Motion. 13. In investigating the motion of aeroplanes, we start, of necessity, by writing down the general equations of rigid dynamics. We take a source in the center of mass of the aeroplane and choose three axes mutually at right angles, fixed relatively to the aeroplane and moving with it in space. We use the following notation: W, weight of airplane, F, B, G. Moments of inertia about thexes. Z, EF, corresponding products of inertia. Ti VU / components of translational velocity. PQR, components of angular velocity. High H/13, components of angular momentum. Then we have the following equations of motion using homogeneous gravitation units. WJ equals accelerating force along axis of 1 / JDT J / and similar. Also DHI plus 5 3H equals accelerating torque about axis of low GDT JG, while the expressions for the angular momenta are in the most general case. High equals A2, FQR H equals BQ Dr. FP 2. H equals CR rep DQC 219. 20 Fundamental Principles Chap. 14. Suppose in the first place that the aeroplane is flying steadily in a horizontal straight line. We take this linear axis of and shall call it the line of G8, the center of gravity being origin as postulated. A line drawn vertically doivnavards as axis of I, and a horizontal line perpendicular to these as axis of Z. In the case of asymmetrical aeroplane, such as commonly exists in practice, the plane of it will Bethagilin of symmetry, so that D equals 0 and E equals 0. It is assumed that gyrostatic effects due to the rotatory inertia of the propeller are neglected. If it be necessary to take account off them this must be done in a subsequent investigation. L. Insert ingadity oil terms in the equations of motion. For an aeroplane with two propellers rotating in opposite directions, the gyrostatic effects annul each other. If the aeroplane be turned in any other direction, this latter direction could be specified by Euler's angular coordinates. Butes these aeronaut will suited for the study of small oscillations. The following scheme is preferable. Starting from an initial position, imagine the aeroplane first rotated about thesis ophi through an angle f. This one in the system is specified in Routh's rigid dynamics and elsewhere. Thesis era first rotated about thesis of z, then about thesis of / then again about thesis offs. The all-jection Tothai's specification is that if the system receives a small rotation about thesis off, r, this cannot be represented by small values of the angular coordinates. In two general equations, 21 merely changes its orientation, then about thesis offs through an angle 6, lastly about thesis offs through an angle. The cosines of the angles between the axes horizontal / direction off light y vertical / fig. 2. 02/052 ocal thenu axis xi, y, z are given by the folio and O scheme. 22 fundamental principles chap. The angular velocities J9Q are given in terms of y /r0j, b the scheme p equals plus sin 6q equals 6 sin, f plus if /cos r equals 6 cos, f /j cos 3 sin. 4. Reducing as thigh should in the case of equals 0 equals to p equals 4, q equals f, r equals 9. Will be observed that 6 is the inclination off the line off light to the horizon, taken positive when the plane fig. 3. Is flying doivnevards and is the angle through which the plane off symmetry is turned out off the vertical position when the aeroplane turns over sideways. 15. They impressed forces and couples aeroduto, I gravity, Roman 2 propeller thrust, Roman 3 air resistance. The components of gravity along thesis are W sin 6, T F cos 6 cos / T F cos 6 sin. 5. The corresponding moments all vanishing. 4. The components of propeller thrust. When notice that in steady horizontal flight, this acts usually in the direction of motion, and where therefore justified in choosing its direction as our axis offs. The more general cases, 2 small oscillations 23 discussed later. Let the thrust be h and let it act at a perpendicular distance, h below the origin, then its components are specified as below, point off application. H force if torque hh. 6. 4. The components offer resistance, we assume that these reduce ta forces x, y, z, and couples l, m, n. That these are taken positive if hen theten toratar the corresponding motions of translation and rotation. Thus, e.g., the force acting along the positive direction of thesis offs instead of being represented by z as usual in textbooks, is represented by x. This convention is made because the forces and couples are of the nature of resistances, and it really appears to work out more satisfactorily than the ordinary convention. When I write the equations of motion, WG dt G dt, JRJ IOT IBAN is NKN V. If the axis of isosap principle axis of inertia F equals and the equations are greatly simplified. Steady motion and small oscillations. 16. Let the aeroplane be descending with uniform velocity u in the direction of the axis ox, and let this axis make a constant angle, O, with the horizon. It will follow from conditions of symmetry that the plane ox is vertical, and therefore equals 0. In this case u is constant. 24 fundamental principles chap. And equal to u, whereas v, w, j, q are the other velocity components aerial 0. Let the components of resistance and thrust in this case be denoted by the suffix O, thus x, y, z, l, m, n, and hg. The equations for steady motion become 2 small oscillations 25 tion where small oscillations are concerned. Need not L, E here discussed. If the aeroplane is moving in a turbulent atmosphere, there will be additional forces and couples caused by gusts of wind. In this case, we must add to the expressions terms x, phi, z, l, m, n, varying with the time, representing these disturbing forces and couples. It is clear that the first step in the discussion is to investigate what happens to an airplane when left to itself, i.e., when these components are all 0, and the aeroplane is said to be performing eerie oscillations. Separation of the two groups of oscillations. 17. The 6 components x, y, z, l, m, n, being each expressed as a linear function of v Roman 4, p, q, r, for purposes of approximation. There would beltoj their 36 coefficients, such as x, x, f, if we knew nothing about the symmetry of our aeroplane. But if this is symmetrical, the coefficients reduce to 18, the other 18 vanishing. As x, y, and do not occur with suffixes Roman 4, p, q, and on the other hand z, l, mdo not occur with suffixes u, v, r. It is to verify these statements, as the following instances will show. If, for example, x weave different from 0, say positive, then a sideways velocity and / from right to left, Looking in the direction of flight would cause an increase Roman 4x in the head resistance x, whereas a sideways velocity in the opposite direction would cause a decrease. A Sanother instance, if z were different from 0 and positive, then if the machine were towed up down with angular velocity r, it would experience a sideways resistance, rz, which would bear reversed in direction if it were towed up, the angular velocity r being reversed. The reader may be left to verify the other cases which pi-essent themselves. 26 Fundamental Principles Chap. In small oscillations, moreover, 6 will differ from O by small C1 e, and will be small sothet all right. Sin equals sin 0 plus f cos dg, cos 6 equals cos augessing sin, p equals f cos equals 1, 10. Finally, we suppose thenu propeller thrust tobe h4br, remaining constant. When all these substitutions are made, u plus u being off course written for. The equations 7 give w equals w sme plus equals 0 plus h plus dh gat backslash uxq u zu vxy rx. 11 Yoed FVY Zoz 2 JZPQ ZG LLW tilde equals low to LI LPQ LG EI7 and U na VN LLR. We substitute from the equations of equilibrium and rearrange the equations in two groups. The first group containing those the first, second, and sixth, involving U VR the second, consisting of the third, fourth, and fifth, involving W P Q. With us obtain the groups W equals Wicost plus 8HUX IXRX 12I0W J plus Y equals Wesson 6 NRVY RY 12. G equals H8HUN VN 12 RGDT Anthegra. Omen 2 Longitudinal Stability 27. The first group represent oscillations in the plane OFX / which weka longitudinal or symmetrical oscillations. The second group represent rotations P, cabout thexes OFXendian motions if perpendicular to the plane OFX, Y, which we should describe as lateral or transverse oscillations. It will be noticed, however, that while represents a cantover sideways, you represents turning round off the direction of the machine, say a directional rotation, and determines a lateral motion of translation. In view of the frequent attempts that they've been made to spur at lateral and directional stability, and the fact that the motions are not all rotations, it is better to distinguish the oscillations of second group by asymmetric oscillations. Another alternative is to theorem lateral to the whole group of asymmetric oscillations, which are in general mutually interdependent, and in this book it will never be used except in this sense. Whether have equals 0 plus fi equals v0 tilde, as may easily be deduced from equations for or from geometrical considerations, symmetric oscillations, condition of longitudinal stability. 18. To investigate the symmetric oscillations, we assume u vr eto proportional to /sothet ducive doctor do it equals dt equals mrff equals, and notice that the last equation gives r equals /e. But the equations are of a more symmetrical form when r / is substituted for ethanthi would base u are substituted for. This is, however, a mere matter of convenience. 28 Fundamental Principles Chap. Equations 12u v r dow become on transposing w plus x /t plus x v plus y plus equals Roman 2 rn plus w tilde plus n v plus usin plus tvj plus y equals 0 ivu plus n v plus c tilde plus n av equals a. 15. We consider at the outset the simplest case in which the propeller thrust is independent of the velocity. So that hh equals. In a later section we shall examine the necessary modifications when this assumption does not hold good. The right-hand sides of the above equations vanish, and when eliminating u v r, their result assumes the form of the determinant w plus jf x cos 6 plus x1 w plus f sin 6 plus tf plus y a gn n d plus n 9 equals 16, multiplying by a, or move / from the denominator in the upper linear developing the determinant in powers of a, we get an equation of the first degree which we write %o plus x3 plus sx2 plus registered / plus s equals 17, where equals gwx plus y plus wm equals gx zoa n plus wlyn plus xn gj equals xlyn plus x f I /ryn plus x rivyn uw plus w xn plus na cos 6n sin 6 at w equals 1 cos yn sin n xiv. 18. Roman 2 Longitudinal Stability 29. These coefficients may be simplified with advantage by the following notation. Write a, fourth a determinant x. 30 Fundamental Principles Chap. If the biquadratic has a pair of complex roots addi I where e equals v, 1, the corresponding disturbance takes the form e cos t plus h sin bt. And if the real part is positive, this represents an oscillation which increases with the time and steady motion will be unstable. If on the other hand the real part is negative and equal to 7. Solution takes the form e, a cos t plus h sin t, and the disturbance becomes adamped oscillation off which the modulus off decay or coefficient off subsidence I equal toy. For such disturbances, the system tends torvert to its state off steady motion and istable. The condition that Thurut's off a biquadratic equation shall all have their real part negative anthus indicate stability off steady motion is given by Routh, Advanced Rigid Dynamics. Supposing that 5 is positive, as is the case above, this condition requires that %53O do 0 registered O and app where FPO equals 33E2 minus 5T2, 2, 553 19 shall all be positive. For a proof off these conditions wherefore to Routh's treatise, but a partial verification of the last condition S may be given by X, meaning what happens if the ethereal part off a pair off roots off the biquadratic. 17. R asterisk plus 93 X3 plus EX2 plus 2, X plus G, equals from being negative becomes 0. In such a case, the root /3t 0 leroots off plus slash s equals and by substitution and equating the real and imaginary parts we find that / tilde equal. /3 must be solution off both equations 2lx asterisk plus s, a2 plus s equals 33x3 plus 3, x equals the second gives 2 uv b equals ts. 11 lateral stability 31 which substituted in the first gives 3, 2 soil plus registered equals or s3, 5 2 go 53 2-5t2, 2 equals which therefore represents the limiting case when their al part off a pair of fruits changes sign. The corresponding inequality representing a condition for stability may also be written 93 2, 2, OS3. 19a necessarily implies the condition 5 are positive if all the other 4 coefficients are positive. Asymmetric oscillations. Condition of lateral stability. 20. Fourth asymmetric oscillations wet W, P, Q, and proportional tau, and notice that in this case we have deli / F cos 0 equals tilde JL, ost equals J cos D, JQ sin which Wusata substitute for slash in terms off bend J. Our equations 13 Roman 4 PQ no become W plus Z W plus Y cos 0 plus Z P plus TF sin 0 plus Z Q equals LW plus A plus LY plus F plus L Q equals 20 giving one elimination X W W plus Z equals 6 plus Z 4 plus OW. Sin 0 0 plus ZQ F plus L equals 21. 32 fundamental principles chap. Multiplying by Zan expanding the determinant in powers of zinth form / plus 33ix3 plus cx plus 3 ix plus sj equals 22. When O have fourth the coefficients 3t equals w ab f2 equals z ab f plus wm plus bl plus fl plus m / r z jam plus bl plus f l plus 3 / plus w mlm z fm plus bl z wjfl plus m I equals z lm lm plus z lmml plus z tilde WJLMLM plus FL plus M sin 6 BL plus FM cos 6 / equal LMML cos 0 LJF ML sin 6. 23th expression for section may also be arranged thus equals AZMMZ plus BZLLZ plus FZMPMZ plus ZLLZ plus WLMLM plus WJFL plus M. Retino SB for Z. U resistance derivatives 3 and if SB for the conditions of asymmetric stability require that 5EI 53I pound I2, IC and Q shall be positive, percent being off necessity positive as is easily shown by principles of elementary RIOID dynamics. Observations on the resistance derivatives. 21. It will no be seen that if or ag of an aeroplane moving in ag of an manner, wek knew the values of 18 coefficients x, or as we may write them for shortness x, y, n, and zl if p as well as the dynamical coefficients, namely mass and moments of inertia, we could, by substitution in the formulae obtained above, ascertain if the motion in question were symmetric ally or asymmetrically stable. Also by numerical solution of the biquadratic we could ascertain the character of the small oscillations about steady motion, their periods if periodic, their logarithmic decrements corresponding to stability or logarithmic increments corresponding to instability. For the coefficients x, y, I, v, z, l, m, y, p, q, I propose the name resistance derivatives, as it is convenient to have some name for them. No assuming the resistances tob 2 proportional to the square of 7 relative even velocity, and this is the assumption the validity of which, under normal conditions, is generally admitted. The 6 forces and couples x, y, z, l, m, n will be quadratic functions of u plus u, v, w, 2, q, r, and their derivatives x, and will be proportional to u, remembering that where in ligoing to for staproximation, and that squares and products off the small quantities u, v, Roman 4, 2, q, are neglected in dealing with small oscillations. The quotients x, j, u, and r/u will be constants for a particular machine flying in a particular way. They d. 34 fundamental principles chap. Will depend on the form, dimensions, and arrangement of the aeroplanes and of the supporting frameworks, which of course also encounter air resistance, and the will also depend on the inclination of the aeroplane to the line of flight. If they were determined experimentally for every such inclination that might occur in practice, the problem of stability would bear reduced to arithmetical calculation. At some time, even granting the necessary experimental data to be known, the calculations would be exceedingly laborious, and in order to simplify them, it would still be necessary to search for approximate methods of solution by developing the problem further on the mathematical side as a first step. In the next place, we observe that since in rectilinear motion along thesis ox, wave x, y, and proportional to lj \\, if therefore an OO to OI given by the conditions of equilibrium, equals W sine plus H zo equals W cos F equals H n, and in particular if the propeller thrust is central so that no equals wave also n equals 0. Remembering that the derivatives are proportional to u, we find that the coefficients in the biquadratics in \v/ are dependent on u in the following manner. The suffixes being omitted from these coefficients as the conclusions are the sum for both the symmetrical and asymmetrical biquadratic. 2. Is independent of ui8 is proportional to ue. u3, is of the form z73 plus buq, is proportional to uma, however, at either biquadratic in the form of equation in \/gu, thus /x\493/x\3e/x\22/x\ehji7 plus u /fukgu plus CFU plus G *Q. 2 resistance derivatives 35 and the coefficients of powers of x, j, g, u will then be follows. 21 constant u, pound 2, 3 off from a plus b j j tilde 4 jn proportional to u tilde. The discriminant of the equation in this form is section jbss minus 215, sj 76 jja, and is of the form p plus qu plus ru / where p, q rare constants. The condition of stability would thus appear to impose limitations on the value of u. It must be remembered, however, that stability, at least longitudinal, according to all accepted ideas, has no meaning unless equilibrium exists, and when this is the case we may put the conditions of stability into different other forms by combining them with the conditions of equilibrium in different ways. Let us have to distinguish between the primitive conditions of stability, in which Nause has been made of the equations of equilibrium, and Medigid conditions in which these equations have been used to effect simplifications in the conditions of stability. For example, we say that an aeroplane is stable when its velocity exceeds a certain limit. It must be remembered at some time that this velocity is determined by the conditions of equilibrium, and the Medigid condition of stability may be substituted, in which the velocity does not appear. On the other hand, there may be cases in which it is desirable to consider stability apart from textion of the discrepancies between certain results given in this book and those given in Bryan and Williams' paper are thus accounted for. D2. 36 Fundamental Principles Chap. Equilibrium. Thus it is important that when the motion of an aeroplane is being accelerated in the vertical plane, it should not tend to swing round sideways. In other words, that it should possess asymmetric stability even when the forces acting on it are not in longitudinal equilibrium. Of course, in such a case the resistance derivatives will really be functions of the time, so that the investigation of the small oscillations will really be of a complicated character. It may perhaps, however, be sufficient to assume that the primitive conditions of stability, determined on the hypothesis of steady motion, hold good at every instant of the motion. Stability of a dirigible. 22. If it be desired to investigate the stability of a dirigible balloon by the methods of the present monograph, several modifications will have to be made. In first place, account will have to be taken of the inertia of the displaced air. In the case of a sphere moving in a perfect liquid, we know that this inertia is equivalent to toting half the mass of the displaced liquid to the mass of the sphere. For a balloon in equilibrium, the total weights of the airship and the displaced air are equal, and hence the inertia of the air becomes of considerable importance. The inertia of the contents of the gas bag must also be taken into account. If we suppose the balloon moving in aero represented by an ellipsoid moving in an incompressible medium, we can find an expression for the kinetic energy by hydrodynamical methods. This expression will be owing to assumed symmetry of the machine about a vertical plane, the sum of two homogeneous quadratic functions, one of u plus u v r, and the other of p q, and the equations of motion can be written down by Hayward's method. When two dirigibles 37 in the second place, the effects of gravity will be entirely different, the weight of the airship being balanced by buoyancy of air according to the principles of Archimedes. In a state of equilibrium, at rest, the centers of gravity and buoyancy are in the same vertical line. If this the distance between them, then when the axis of this being depressed from a horizontal position through an angle d, and the machine subsequently turned through an angle about this axis. Couples error produced about theses of after Roman 3 general considerations regarding symmetrical derivatives expressions for plane areas. 23. We shall now show how in the case of each lane supporting surfaces, setting aside camber for the present, the 9 resistance derivatives x, y, n can be found if the normal resistance and the position of center of pressure are known functions of the angle of attack and of the angular velocity are. In the first place, we assume, for simplicity, that there is no tangential resistance. Such air resistance may be considered subsequently. Fig. 4. Let S be plane area perpendicular to the plane of x, y, and slanting upwards at an angle of attack, a. Th. Longitudinal derivatives 39 to the axis of x. Let C be point whose coordinates are x, y, centrally situated on S, which may be taken in the first instance to an origin from which the distances of the center of pressure and other points on the plane are measured. P the center of pressure. Let R be the resultant thrust, the perpendicular distance of its line of action from 0, and the component forces and coupled due to resistance, taken positive when retarding motion, are x equals R sine y equals R coa n equals R. 26. The angle of attack being A when A right R equals KSU FA GP equals A, FA equals S suppose. 27. Where kiss the coefficient of resistance, ace the semi-breadth of plane, or a quantity determined by its linear dimensions, fa. A. Arrow functions determined by experiment, representing their relations connecting their resultant thrust, and position of the center of pressure with the angle of attack. Behave further equals x cosine plus ia equals x cosa, / sine plus s. 28. If no additional velocity components u, v, rare impressed, the velocity components of c will, / plus. And v plus xr and the angular velocity off the lamina about c will burr. Ta the first order off the small quantities u, v, r. The effect off these added velocities is to increase their resultant velocity of 7 to u / u, or as is evident by neglecting the second term in the exact expression, vel. 2 equals tj plus nef plus v plus xrf, and told the direction off the velocity of c, thus, or symmetrical or chaff. Increasing the angle of attack relative to c by an amount v plus xr tan, u plus v or u radians totally first order off small quantities. Hence, ta the first order thenu values of 7 and the distance are so far as to depend on the translational velocity components of c, given by r equals ks alpha plus 2 ksu, uvf, fu plus ksu v plus xr, f. 29 r plus xri equals x cosine plus a, p, a plus a jf 0, 30 where fa and 4 / a are the differential coefficients of fa and jya. 24. But the lamina possesses in addition an angular velocity about c, and in consequence of this neither the resultant thrust r, nor the coordinate off the center of pressure can be expected to be the same as if the motion off the lamina were one of uniform translation. To allow for this difference, it is necessary and sufficient to assume TL80, a, and fa not only are functions off angle of attack are relative to the point c, but also that they depend on the angular velocity off the lamina relative to a now. If the velocity u and the angular velocity r are increased in any given ration, I, it is clear that the motion off the plane will be the same as previously, but will take + times as quickly. The resultant thrust will be times as great, in proportional to u, and the position off the center of pressure will be the same as before. From this reasoning, we see that phi and a must be regarded as functions off the ratio r/u as well as off the angle of attack are relative to the point c, and we may therefore write their corresponding variations to the first order / O and J. The longitudinal derivatives 41 saw that where / A and C. A are certain coefficients which we may call T-rotary derivatives of A and F, A. The physical assumption that Ishara made is merely the O, generalization off the law according, to which their distances vary as the square off the velocity, saw that if the parts of a system move n times as fast, the forces due to a resistance are increased n times without Bano, Chano, at in direction or position. 25. Making the necessary substitutions, we obtain the following results. Writing equals x cos y sine plus a phi. Fa sine 2 / sin equals fa sin xsu asterisk / percent / plus / L sin o / cos a I equals 2 / a cos a j equals f / a cos a ksu q ksu equals / xfa minus 2 fa plus u cosa equals xfa minus 2 / a plus / ai 3 a 0 plus 0. F31 if there are more planes and sections of air pressures on them are independent of each other, the derivatives for the system are obtained by adding those for the separate planes. This assumes that the air encountered by on off the planes hasn't been disturbed or set in the ocean by the other. In other words, that neither plane comes into the wash caused by the other. The effects of wash will be discussed briefly at Hindoff, the discussion on longitudinal stability, although a great deal of experimental work would be necessary to attain anything like finality in dealing with them. 26. When notice the following results which greatly simplify the subsequent calculations. These results, 42 symmetrical or chap. Unfortunately, didn't it come to me notice until much long and laborious algebra had been gone through, by which they were approved in the first instance. If there are isonly a single I.e. in surface, or even if there are several J//E/planes, the determinant ow vanishes, and in addition that ninners off its third line udj, VJF, TJF vanish. Roman 2, if there are at lane surfaces only, and if the displacements off the center off pressure, A4 \A, of FA be neglected, then the determinant off the derivatives for either plane haste 3 rows and 3 columns proportional to author, i.e., using accented and unaccented letters tor for tothetwap lanes the determinants, x, longitudinal derivatives 43, Roman 3 if 4a and 0. A but not neglected and there are at plane surfaces the and lie parts of which donut vanish will be those in which I2, 0, AI. 0, 2 occur as factors, AA2 being the inclinations off that wap lanes, and these will be multiplied into theminers V. And itis easy to CR equals 2 UKKS ij FA sin. A 32 and that if can be expressed in a somewhat similar form, also containing sin. A suffactor. Without looking further at present stage off the investigation, it will be seen that the determinant A, so far from giving rise to laborious calculations, either vanishes or reduces to something readily calculable and probably in most practical applications negligible. An exception will be discussed in due course, in which it will be shown that in some cases stability may be increased by use off 3 planes, especially arranged so purposely to give a value of a different from 0. Roman 4 in the case off a single plane surface, using the expression for copyright, namely, J, CJ co S DORSM UI we obtain sir asterisk, IS2W phi equals, case with JA \a T, a co 8, a minus 6. 33 and it follows from the condition D positive thought a single plane cannot hestable unless F, A is negative, that is unless the center off pressure moves forward when thingle off attach decreases. This is the case in actual practice. Also, wesi that to secure stability, the plane must be sufficiently broad for the shift off pressure to have an appreciable effect. In such cases, however, it becomes necessary to take account of the effects of coefficients F, A, and A in the other conditions of stability. They do not occur in S. 44 symmetrical or chap. Observations on the rotary derivatives. 27. In the foregoing work, we have introduced 2 derivatives, FA and 9A, such that FAR/U and FAR/U represent the changes in the values of /A and FA when the lamina receives a small rotation about the point XY. It is important that the effects of rotation on the resultant thrust and position off-center off-pressure should be investigated experimentally if 1. Road aeroplanes and aerocurves aerotobused in aerial navigation. In the original results in Bryan and Williams' paper, these rotary derivatives, as they may be called, longitudinal derivatives 45 middle point. Then if the lamina receive an angular velocity about 8 will move away from Thuend, and will naturally infer that their resultant thrust will LE decreased. If it rotate out by the sama direction it will move towards Thuend, and will infer that the resultant thrust will be increased. Whereas this led to believe that CJ lease between on B. If the lamina rotate A, out its center C, the thrust will be increased on can, decreased on BC, Bute's the thrust is greater on the forward part, a C than on the backward part BC, it appears probable that the net result is to increase the thrust. Hence Weinfer that their acquired point C / is probably in front of can, quite near the center of pressure. A somewhat similar line-off argument may be pleading connection with 0. A positive rotation about a point on a B produced considera. Lie beyond B will certainly increase thingle off attack and cause the center off pressure to move backwards. Similar rotation about a point on B A produced considerably beyond A will decrease thingle off attack and shift the center of pressure forwards. But a rotation about appears likely to increase the pressure on the forward part, off plane, and decrease that on the backward part, shifting the center off pressure forwards, and hence it would appear that the point C2, about which the lamina must be rotated in order that there may be no shifting off the center of pressure, is probably behind. 7. Lows not coincide therefore with C. The last argument is somewhat indefinite, as it is impossible to be quite sure the current off-ramping in rotating lamina would behave in exactly the way that appears most plausible. There are, however, 2 methods of investigating texture experimentally, a much more satisfactory alternative. 28. The whirling table method. Suppose the lamina, 46 symmetrical or chap. Ta attached to rotating arm and W leerled in such a way as ta give forward velocity U at the point C. If the lamina L derotated about O where OC equals A, then Wehaver equals U/A. If rotated about a point 0 on the opposite side, U should haver equals Uja. If then FA, and A. Bayes served by determining experiment ally the resultant thrust and position off center off pressure when rotated first about and secondly about 0. The difference off two values off A multiplied by the length /2 will give FRA, and the difference off two values of P, A multiplied by /2 WDLL similarly give A. The values being in either case referred to the point C. 29. The pendulum method. According to the Blue Book for 1909-1910, experiments in now in tunnel which produces a current offer that may be assumed uniform give better results than whirling table experiments. To adapt this method to the rotary derivatives, it is necessary Fig. 6. Fig. 7. To etch the lamina under investigation to pendulum and observe the oscillations. To eliminate the effects offer resistance on the pendulum the latter would have. The longitudinal derivatives 47 to bemolkil theform off a disk orsplirk. Uagili low-sighted, but having its axis in thesis off rotation. Fig. 7. Then only tangential resistances would occur. Their resultant couple due to these would be proportional to the square of the angular velocity, as may easily L shown, and its effect on small oscillations miot be neglected for an approximate calculation. Let a betha lamina, the center off suspension, are the center off gravity off the whole mass, equals inclination of OG to vertical, of equals inclination of AB to horizon, so that equals constant. If the moment oft resist answers about 0, then when the lamina is to behave as in 31, section 25, n equals KSUF, AX cosine plus N, LA. 34, the general equation of motion is IW, OQ hind plus N, where / equals moment of inertia off whole mass about 0, or equilibrium wave 0 equals TR. O. Sin plus N in a small oscillation if equals D /E and equals a /E, and the angular velocity delta I equal to R wave sin 6 equals sin 6 fecost, and the equation of small oscillations becomes plus RJT plus 4, RFL equals 35, whence the modulus of decay is again /2L, and if the period is 27R/J, then PJW, 0G co. EJ this holds if the motion be oscillatory, a condition that can be always secured by making OG sufficiently great, or the 8 symmetrical or chap. T level oft NJDA is get directly differentiating N with respect to A. It follows that high observing thanodons off decay and R can be found, or if N be negative the logarithmic increment off the oscillations will determine it. Now using the notation of 31 section 25 Wessi that if N is this found fort with different positions off the point CX, Y, on the lamina with the same angle off attack. Formulae for N in 31 will give sufficient data to find both /R, A and A. It may perhaps be safe to omit further details off the method as the reader can probably supply them. This conclusion suggests, however, the possibility of going further and instead off using a single lamina, experimenting with a model aeroplane so as to find the values of N relative to different points in its plane off symmetry as centers off rotation. The idea suggests itself. How's their salts to determine their distance derivatives off aeroplane considered a sawhole, instead of building them up from a consideration off the separate surfaces. Problem thus arises, given the values OV referred to different origins in the plane of symmetry, to find as much information as possible about the other resistance derivatives referred to single origin. This involves consideration of the transformation formulae for resistance derivatives. Formulae of transformation. 30. Let U plus UV are both the velocity components, x, y, and their resistance components referred to the origin, 0. Let accented letters refer to parallel axes through the point x, y. Where U equals U plus or V equals V, XR, R equals RXX, Y equals Y, N equals NXY plus YX. 36. The longitudinal derivatives 49 and the transformation form a /3 folder the folio O types. 1. For XY, the type XI equals X2. For XY, the type XY equals XY plus YX, XX3 for N, the type IVI equals J /R plus XY4 for JV. If the type equals plus YL10 plus tilde equals I, Y plus /XV plus X XI Roman 12X plus F plus FX. 37. It will thus be seen that determinations off the resist ants couple derivative N about different origins will give the values of Zine plus YN plus XY plus X and as the values of X1 are equal to so /U, etc. Only one further datum is needed. If the condition OW equals is satisfied, this datum is available. 31. The formulae for change off axes. The origin being constant, areas follows. Using unaccented letters tor for tooled excess and accented letters tor for toxis making an angle A. In the positive direction with them we have KT at FA7 Dr. U equals A cos A. V sin A. V equals sin A plus V cos A X equals X cos plus A sin A Y equals X sin A plus I cos A D for D. DDT. 7 equals cos AJ plus sin AY 5 equals sin I plus cos AY do DV do Dr. 38. whence their assistance derivatives referred toth and waxes can easily be expressed in terms of those referred toth old x's. For example, equals m equals 1k plus y plus ii equals x cos 2 plus x plus r sin cos 1 plus r sin a pound. If t symmetrical, okay chap. Camber 32. The chief difference between plane and curved surfaces is that in latter the direction of the resultant pressure may vary with thingle off attack, and we should have tau set wo letters. A, the first denoting the inclination of, say, theccord off the arrow curve ta the axis offs, the other denoting the inclination off the resultant thrust to thesis off I. For Turnbull's doubly curved surfaces, experimental data would alone be available. But if the section off a surface is a circular arc of radius c, it is clear that their resultant thrust will pass through the center off curvature, and if the center off pressure be shifted forward through a distance hs equals a, the direction of r will change by an amount equal to ss/c or ba equals ba x alc a. For a plane surface, f/a is negative. Most important effect of this when thingles aerosmol will produce a variation bx in horizontal component equal to r cos ba. And when the necessary substitutions are made, it is seen that the principal effect of curvature is to introduce additional terms in totha values of x and x. The magnitude of these terms depends on edge, that is, on thingle which thirx obtains at its center off curvature, not on the actual size of the arrow curve. It might thus become important even with narrow arrow curves if thigh's angle isn't small. The corrections thus introduced are discussed in section 69. Further corrections may be examined at a future time if deemed advisable. The principal difficulty arises from our want of information regarding the rotatory coefficient /r, a, which also lead to variations in thingle a. Till these variations have been studied, the stability of arrow curves must be to some extent uncertain, and the extension of results calculated for plane areas must be regarded as the longitudinal derivatives 51 working hypothesis, divergences between theory and experiment being anticipated. Narrow planes at small angles. 33. Owing to the doubtful points raised in the previous paragraphs, as well as for reasons of simplicity, the study of aeroplane stability is best commenced by the consideration of systems of narrow planes at small angles. By the term narrow planes applied to an airplane with two or more plane surfaces. And behind the other, it is to implied that the breadth or chord over their plane is small in comparison with their horizontal distance apart. If the aeroplane receives a small angular velocity r, the difference of velocity set up between the front and rear edge of a plane will be small compared with the difference in velocity set up between the two planes, and for this reason, the rotary derivatives may be neglected in comparison with quantities actually taken into account. Or it may be assumed in the first instance that the shifting off the centers off pressure with varying angles of attack i.e., the quantities a are negligible owing to the smallness of. We shall now assume that the point of section 23, the position off which has hitherto been left arbitrary iscos and ta coincide if the center off cs sure when the aeroplane is flying steadily. That is, when o define x, it o have the coordinates off the center off pressure in steady fight. So that f, a, equals 0. The assumption that via, and a are negligible thus becomes equivalent to neglecting the distances from the center off pressure off the point cj, considered in section 27, an assumption which, as we have seen, is probably fulfilled more approximately in the case of c than of co. When the planes are gliding at small angles, wimply that thingles off attack are small, and in such pound 252 symmetrical or chap circumstances, it will be assumed that the normal thrust on a plane varies as the sign off thingle off attach. This property is commonly expressed by the formula P equals 2P9. The scene where P90 is the pressure when thingle off attack is 90 degrees. Of course, the formula fails when is considerable, for with a equals 90 degrees it would give P equals PQ instead of P equals PO. The formulae have been proposed which get over the difficulty, such as Duckerman sina P equals 2 Po, JO1 plus sina, but for small values OFA, the simpler one is usually regarded as sufficient. Whether if or right, A equals sin A. We further assume that sin A small and that the approximation sina equals on cosa equals 1 may be used if desired, and the terms off theater may be neglected in comparison with finite quantities. Remembering, however, that in horizontal flight h equals ksu sin 2, 39, it is evident that when sina cannot be neglected except in comparison with quantities off lower order. With these assumptions, and writing I equals x cosa sin A, equals x cosa 2 usina thermal off derivatives in section 25 reduces to xxx. xj equals 2ks sin a j equals 2 sin a, sj. 2ks sin a cosa y equals 2/rs sin a yy. Ij equals 2ks sin a cosa jj equals 2 sinios a, jj1 ks cos a, jy equals I ks cosa equals sks sina equals 22 ksi sina. Equals 2/f5 coso KSI. 40. The equations of equilibrium in horizontal flight become h equals us. Ks sin 1 W equals US. Ks sin ocos A HH equals U tilde 2 Ks sina 4130 for the S fin notation. A further simplification which will be found of great use, especially in dealing longitudinal derivatives 53 with stability under complicated conditions, consists in the substitutions S equals scos on slash I equals tan A. With this substitution, the foregoing formula give %2A, 5V equals 22A, 6VY 2A, 5M equals 2 phi, S x 2YM YU wire S, KS6JJ LKSEJ, JJ equals S, ASJJ equals 2 KSX ifs, XYLVNJP equals KS slash JX7 slash X, Y2% KSDEX, X IDX JJ equals S. KSXY slash X tilde equals S. KSX IDX X2 YX 40A with HMT KSEJWM% KS die HHU2 KS phi X IFI. 41A, the principle of independence of height. 35. Since thingles are small and are both approximately equal talks, and the resistance derivatives are Toth's approximation independent of the coordinates of the planes. Wethus see that if an aeroplane is stable when thage lanes Arion-Ilval ivith the center of gravity, the stability ison livery slightly affected by raising or lowering the planes. Instead of raising or lowering a plane vertically it displaced in a direction perpendicular to itself, the value of I will be altered, while I will be decreased by isina, saw that only this small difference between and will affect the stability, and the conditions of equilibrium will be unaffected. In this case, the line of action of the normal resultant thrust on the plane is unaffected by the displacement, and the inlie difference is that the tangential velocity of plane due to rotation, r, of the aeroplane is altered, the corresponding normal velocity being the same as before. When thingles of attack are small, the change of tangential velocity has only a small effect on the resultant thrust of air, and is far less important than a change of normal velocity would be. 54. Symmetrical or chap. The present deduction may be called the principle of independence of height. This property seems at first sight at variance with what one would naturally expect from analogy with the case of a pendulum, whose oscillations depend essentially on the height of the point of suspension above the center of gravity, or again from the case of an aerostat. It must, however, be remembered that the principle is based on the assumption that tangential and head resistances are 7 neglected, and the difference will be made clear by taking moments in each case about the center of gravity, with Theodoth Fo Uoino diagrams, Fig. 8, resultant Fig. 10. In the pendulum Fig. 8, the point of suspension cis fixed saw that the pendulum canly turn about C. In this case, rotation about just a tup the moment of the tangential force facting at cat right angles to GC. In the aerostat Fig. 9, the hydrostatic thrust IF equal to off air displaced acts vertically upwards, although the center of buoyancy can its moment about G10's bring RC into the vertical position by producing rotation about G. In the plane parachute Fig. 10, without tangential, longitudinal derivatives 55 resistance, if variations in the position of the center of pressure are neglected, their resultant thrust railways passes through G, and has no moment tending totter in the parachute about G. Of course, Thuate was a moment about C, but all the forces pass through GAN, their only effect is to produce an acceleration off parachute a sawhole in the direction of the resultant force. The forces on a body have no moment about the center of gravity, they have no tendency to produce rotation. On the other hand, tangential resistance would tend totter in the parachute about G, bringing thesis GC towards the vertical position. Fig. 11 shows an aeroplane with one aeroplanes A, B, and center of gravity G, if the normals to Thetwo Fig. 11. Planes intersect in slash. That point slash will present the nearest analogy to the center of suspension off the pendulum of Fig. 8, or center of buoyancy off the balloon in Fig. 9. Resultant off that one normal thrust that on B wall pass through slash, and if it does not act along GI, its moment about Gwilton to rotate the aeroplane. But if A or bear displaced perpendicular to themselves to A and B backslash the normals, them will still meet in the same point slash, and the equation of moments about slash will be the same as before. The thrusts on A and B will also be the same as on a B when the aeroplane has no rotation about G. 56 longitudinal derivative CH. Roman 3 odd when it rotates the normal velocities of A, B will be the same as of A, B, while the difference of tangential velocity between one and only has a small influence on the resultant thrusts. In actual practice, it is certain that, owing to head resistances and tangential forces, stability will be affected to a sensible extent by raising or lowering the planes, and also if the planes are too high. Sudden gust of wind will cause the aeroplane to heel over. The inference, then, is that this effect must be in large measure attributed to tangential forces or head resistances. On the other hand, the principle receives confirmation from the fact that successful flights have been made with machines in which the center of gravity is above the aeroplanes. It must not be forgotten, too, that we're no only considering systems planes, no-curved surfaces. An important corollary is that there isn't a practical difference between monoplane and biplane machines in respect of stability. It is the horizontal, not the vertical, disposition of planes on which stability mainly depends. The nomenclature, monoplane and biplane does not cover the necessary distinctions. The differences with which we are concerned are between the single lifting SG stem in which the whole offtuate is supported either by on plane or bitwo or more vertical superposed planes, their remaining planes taking the form of a tail rudder only, and double or multiple lifting systems in which thuate is supported by or more planes, or sets of superposed planes, disposed in a fore and aft direction. After Roman 4, graphic statics off longitudinal equilibrium, single lifting systems. 36. Before considering stability further, it is useful to discuss the problem of longitudinal equilibrium with special reference to steering in a vertical plane. This can be graphic methods. In the following discussions, we shall in general suppose the aeroplane to be longitudinally stable. In such cases, a variation in the direction of the rudder plane or in the propeller thrust will cause the aeroplane soon to assume the new position of equilibrium, determined by altered conditions. If the aeroplane is not stable, we can still examine the effects of a change of the kind on the conditions of equilibrium. Although the initial effect of change may be the reverse of that needed to bring the aeroplane into equilibrium, and the new equilibrium position may lie attainable by careful maneuvering. Case 1. Single lifting system with a neutral tail or rudder. We speak of tail rudder as neutral when its plane is parallel to the direction of the relative wind so to encounter non-normal thrust. This is sometimes referred to as grazing incidence. In this case, the following three forces have to by equilibrium. 1. The W8 acting vertically through the center of gravity G2. Their resultant thrust on the supporting plane. 3. The thrust off the propeller. 57. 58. Graphic statics chap. The first condition of equilibrium is that these three forces must pass through one point. Suppose H asps through the center of gravity G, then R will also pass through G, Fig. 12. The other condition of equilibrium is that the three forces W are parallel and proportional to the three sides of a triangle, also constant while thingle 50. I. A Chanute glider. The two superposed planes constitute a single lifting system, the tailplane being in general neutral. Section 36. Being used as a glider, the longitudinal stability would be greater than in a similar aeroplane propelled horizontally. Section 55. The photograph was given to Thuther by the late Mr. Octave Chanute. Between hand the main plane is constant and we will denote this angle by. We then have the following geometrical construction for the triangle of forces. Draw DE vertical and length units. On DE, describe a segment of a circle containing an angle 90. W, and in it place a line DF containing units of length. For longitudinal equilibrium 59, then FD will be parallel to the force hand EF will, parallel and proportional to the normal force R. Fig. 13. The aeroplane will therefore be in equilibrium when the axis of the propeller is parallel to F dan the main plane is perpendicular to EF. In order that F dan therefore H may be horizontal, we must have H equals W tan Q. The direction of the aeroplane relative to the horizon is thus determined by the magnitude of the thrust H. If H be increased, F will be lowered relative to dan, the aeroplane will point more upwards. The actual direction of flight is in the present instance. Plane parallel to the tail rudder plane. If this be altered in direction for steering purposes, the direction of flight will alter accordingly. This conclusion depends essentially on the hypothesis, made in dealing with narrow planes, that when neglect the shift off the center of pressure when the angle of attack is varied. In this case, if the three forces W, R, ever pass through the common point G, they will always do so. Hence the conditions of equilibrium require that the moment about off the thrust on the rudder vanishes. Therefore, the thrust itself must vanish and the rudder must always be neutral. Finally, if the angle of attack is a, the velocity of aeroplane is determined from the equation R equals KSUCU. Graphic statics chap, or indeed from the assumed law of resistance, supposing the sign Lebenar assumed to hold good. Thus, in conclusion, when their equilibrium, the inclination of the machine to the horizon depends exclusively 0.7 if the propeller thrust. Increasing this causes the machine to tip in front, decreasing it causes the machine to tip down. The direction of flight is always parallel to the plane of the tail. If thighs head turned in direction. Corresponding CHCTNG will take place in the direction of flight, the magnitude of the velocity U depends on both causes, being determined by the law of resistance. 37. If the propeller thrust H does not pass through G, the forces hand R will intersect in a point slash, which is fixed relative to the machine. In order for the tail to be neutral, the conditions of equilibrium between the forces W, R, require that 6R slash shall be vertical. If the machine be tilted forwards or backwards, this will cease to be the case. And the rudder plane will necessarily cease tobe neutral assignment from the equation off moments. Since the inclination to the horizon depends on the value of h, there will be only one value of I for which the pressure on tailplane vanishes. If the engine's aerostopped and the machine glides steadily under gravity, as it should do with the rudder neutral, then, according to your assumptions, the and lie forces which maintain equilibrium are ran W, and it follows that R must pass through G. If the engine's arrow started and exert a thrust H, the rudder cannot still remain neutral unless the thrust also passes through G. Unless, therefore, an aeroplane is provided with substantial fore and aft planes capable of sustaining a considerable pressure, it is important that the propeller thrust should pass as nearly through the center of gravity as is possible under practical conditions. Otherwise, the for longitudinal equilibrium 6I machine must be regarded as adably lifting one for all practical purposes. It is very important that in case of a stoppage off the engine's the machine should glide on an even keel, without the rudder being subjected to excessive strains. A second cause off pressure on the rudder plane is shifting off the center off pressure when the angle off attack varies, the main plane being no longer assumed tobe narrow, according to a signification. This causes the rudder, if neutral, remains so, as long as the angle of attack remains constant. To secure this, when it is required to rise or descend at an angle 6, the propeller thrust must be increased or decreased so as to tilt machine up or down through the same angle 6. The angle of attack being constant, steering in a vertical plane will have tobe affected exclusively by varying the propeller thrust, and nit turning the rudder plane relative to the machine. If, on the other hand, the angle of attack is decreased, the center of pressure will move forward and the air will have to exert an upward thrust on the rudder plane if it is fixed posteriorly. When the angle of attack is increased, the center of pressure in general will move backwards and the opposite will be the case. Double lifting systems. 38. In the general case of a double lifting aeroplane, where neither the front nor the rear planes are neutral, there are for forces in equilibrium when the machine is moving uniformly. These are through watt G, the propeller thrust and the resultant thrusts R and R, on the two surfaces S and S, at air centers off pressure and B. As before we shall suppose in the first instance that H passes through the point G. Let the normals to the surfaces at air centers off pressure meet in JF. 62 Graphic Statics Chap. S auth at Forneroiv planes 31 is regarded as affix point. Fig. 14. For equilibrium there resultant of Rye and E, 2, which acts through M must be equal and opposite to the resultant of wand acting at G. Calling this resultant Ritz line of action is along GM and the plane CS, are equivalent to single plane off suitable area, having its center off pressure in the line G manned its plane perpendicular to GM. With the inclination to GH off thighs equivalent plane, thingle between hand eyes 90 degrees /co. As before the three forces at Gara presented by its sides off the triangle DEF and Fig. 13, thingle at F being constant and equal to 90 degrees and if H be increased Fig. 13, Fig. 14. It is obvious that F will be lowered relative to D and the machine will be tilted upwards. Conversely, if HBE decreased, the machine will be tilted downwards. If the engines aerostop without moving the planes, the aeroplane will be in equilibrium when GM is vertical. This adj depairs that the inclination of the machine to the horizon depends entirely on the propeller thrust. In fact, when we say that, so far as the equilibrium is concerned, the Nachi 7IE behaves exactly like a glider, the resultant off-proj Eller thrust and gravity taking the place off gravity alone. It remains to the motion, knowing R, for longitudinal equilibrium G. Values of hand W being given, the components R and 2 are known, and if and A. 2. Arathingles off attack wehave Rai equals Xi SE. 7. Sin IR equals KJM Sina. 42. No from the conditions of equilibrium wehave Risin GMA equals R. Sin GMB hence Chi Si Sinesin G Make S. Sina Sin GMB. 43. Which determines the ratio Sina Sin A. Also adj A. The angle between the directions off the planes is known being equal to AMB and ANA may be found. When this has been done, W may be determined from either of the above equations, 42 or otherwise. 39. iPhone or author off the planes S just for steering purposes saw that its inclination to the line a B can vary. It is necessary to have recourse to geometrical construction in order to ascertain the effects of steering on the position of equilibrium. Suppose A, G be to a straight line, and let MO be drawn through M perpendicular to the direction of flight to at A, B, and O. Then A equals AMO A equals BMO and 43. Becomes chi sin amo sin AMQ equals KS sin BMO sin BMG. 44. But sin amo equals JJQ sin 0 AM. Sin AMG equals Y sin GAM sin BMO equals J sin OBM. Then BMG equals SMGBM whence 44 reduces to chi CAO. Ag sin 20 AM equals KS BO. BG sin 2 ABM. 45 again if I arathingles which the planes S somic with the line AB m equals 90 degrees I obum equals 90 I giving chi SAO. AG cos 2E equals KBO, BG cos I. 46 this determines the ratio AO. Bo and its ois. 64 graphic statics chap. Found if I or a small angles is generally the case when may substitute the proximate relation chi \ow. Ag equals KS bo BG. 46 RT, based on the proximate assumption that cos I equals cos O equals 1, Tothus degree off approximation the position of was unaltered by varying inclinations off the planes to AB. 40. If the front plane be tilted up b increasing I, and M will be displaced to a falong BM and the direction of Fig. 15. Flight will be perpendicular to M to co instead of J/0 Fig. 15. The effect is to increase Thingle's off attack, which now become omb, for by Euclid these are greater than OMA 0 MB respectively, and the direction of R will be changed from MG to MTIC-G. The inclination of the machine to the horizon will be altered in consequence. And to estimate then it effect on the direction of light relative to the horizon, the figure must be combined with the triangle off forces at head point G, say GDE. If then, for longitudinal equilibrium 65 GD is measured contaiuino, / units offly, and with center dendradius I units, we describe a circle cutting MG, MTIC-G il end E, B and DE will be the directions off the vertical relative to the machine. The result of the change will be that the machine will be tilted over forwards through an angle EDE. And since the direction off line off light relative to the machine is altered by the amount MOM, the net result off till TUE up the front plane is to press the direction off the flight path through an angle MOM plus EDE. In other words, raising the front plane causes the machine to descend, and conversely depressing the front plane causes it to rise. If the machine was originally flying horizontally, OM will be parallel to DE. And if with center and radius OM we draw a circle cutting GM in N, the triangles GOM, GON, will be similar to GDE, GDE, so that on will be parallel to DE. In this case, the angle NOM represents the inclination to the horizon at of which the machine begins to descend. 41. The effect of tilting up the plane through an angle MBM is to alter their relative direction off the flight path through MOM Fig. 16. The angles off attack are altered from OMA 0 MB to AMA and OM respectively. It is obvious that AMA OMA saw that angle off attack on S is decreased, that OM 0 M pretty evident from figure 16. A formal demonstration, however, consists in observing that if 0 MB OM were equal, that points MM 0 B would Leona circle, saw that we should have MM equals MOB. But in the cases if which occur in practice MM is small being the angle between the front and rear planes, whereas MOB is usually somewhere near a right angle. And at any rate, note a small angle. The direction of R relative to the machine will turn through an angle MGM, and the direction off the vertical through EDE where GDE are thetwo F. 66 graphic statics chap. Positions off lick force angle at G. The net change in the direction off the flight path relative to the horizon is represented by the difference off angle of MOM ed. If the machine was originally flying horizontally and we draw a circle center and radius OM catino, QM in ME Fig. 16. And we see that angle MON equals EDE, and the net result of tilting up the 7 airplane is to cause the machine to rise at an angle NOM. Thus elevating their R-plane causes the machine to rise, and conversely depressing it causes the machine to descend. 42. Corrections. The above investigation will probably be sufficiently accurate for most practical purposes. It remains, however, to be shown that where the underlying hypotheses are only approximately valid, more accurate results might be obtained by introducing modifications in the construction. If cos E and cos I are not into unity, the point will no longer be fixed when the values OFI and 2*2 are varied. If I be increased the ratio AO, BO will be increased. For longitudinal equilibrium 67 and O will approach a noviig to position, / and OTCM will cont OM in a point below AB. The perpendicular to the new flight path relative to the machine will be MTCO instead of MO, and the depression off the path relative to the horizon will be slightly reduced by the angle AMO. If on the other hand EI be increased AO, BO will decreased and will move outwards to position 0. With that the elevation off the line off leaves HT due to the chanof will be reduced by an amount OMO. In either case the result is slightly to lessen the steering effect due to turning the plane. In either case the effect could be more fully studied by constructing the envelope off the line MO, first with L constant and secondly with I constant. 43. FFG does not lie in line AB, and we wash to study the effect offering the inclination off the front plane S relative to the aeroplane, we must join AG Fig. 17. Meeting B and produced in B, and the point A must be constructed on the line AGB produced. In fact, since the plane S2 is kept fixed, the construction is just the same as if this plane were shifted parallel to itself to the point B, subject always to the proviso that the inclinations off the planes to the line G are small. Fig. 17. F2. 68 Graphic Statics Chap. If GB1, 0 produce tome at OM in 0, that point 0 will similarly represent the turning point off the line MO when the inclination of S is varied. 44. Effective shifting of center of pressure. If OE toe change in thingles off attack, the center off pressure off owner 1 off pianos is displaced. This will cause a further change in the direction off light and in the inclination off the aeroplane to the horizon. In Fig. 8 if A, BB represent the displacements. Fig. 18. Off the center's off pressure, MM will represent the displacement of M, and the constructions of section 39 will give thingle EDE through which the direction off aeroplane is turned relative to the vertical. If the center's off pressure are displaced forwards, this occurs when thinole's off attack are decreased. The figure shows that the aeroplane will tilt upwards in front through the angle EDE. To ascertain the effect on the direction off flight. For longitudinal equilibrium 69, path relative to the aeroplane it is to imagine thingle and move backwards and brought into coincidence with AMB, in which case G must be placed through a distance GG equal and parallel to MM. Fig. 19. Here MT is nearer to MB than MG, and it readily follows from their relation AO. Agbo. BG equals constant. That is shifted to point 0 on the side of remote from B. This depresses the direction off flight relative to the aeroplane through an angle OMO, and as the aeroplane itself is tilted upwards, then its effect is to change the inclination off the flight path downwards through an angle equal to OMO. The two causes to certain extent counterbalancing each other. If GG be small and MG meets AB and G, it may be shown by differentiating their relation AO. Agbo. BG equals EO backslash psi backslash T. That's 0 0 GG ow. Bo tilde ag. BG. 466, and further that if the aeroplane was initially flying horizontally, the effect off the change is to press or elevate the flight path according as 0 0 is greater or less than GG. It is scarcely worthwhile, however, to reproduce here the discussion off these points in fuller detail. 70 Graphic Statics Chap. 45. Prof. Marcel Brillouin's mesocentric curves. A more complete theory off the effects due to displacement off the center off pressure hashing formulated by Prof. Marcel Brillouin. So long as these displacements are neglected, the point M, which is the intersection off the normals to the planes, may be regarded as the metacenter off the machine, being the point through which their resultant thrust, R, always passes. If the plane's arc broad, if the line of action off the resultant thrust is constructed 4 different directions off the relative wind velocity, through the whole range of 360 degrees, these lines of action when marred relative to the planes will envelop a curve, called the metacentric curve. It will be noticed that this curve isn't the locus off the various corresponding positions of M. Fourth, the direction off the resultant R depends on the reas S2 off the planes. It is this independent off the direction, off the tangent to the locus off if M. Brillouin has determined the metacentric curves for certain pairs off planes, assuming Lord Rayleigh's formula for the position off the center off pressure. And similar methods are obviously applicable, based on Josel's or any other alternative law. The metacentric curves are in general more or less star-shaped, having 8 cusps, 4 off which correspond to grazing incidents on or other off thetwo planes, and the intersection off normals to thetwo planes at their geometrical centers is a center of S3 ammetry off the curve. The existence off or other cusps is most easily shown in the case off equal plane areas. If the metacentric curve be constructed, and if a propeller thrust passes through the center off gravity, R, the positions of equilibrium area obtained by drawing tangents to the curve through G, and then determining the direction off the vertical by the force triangle GD. 1 Bevue de Mécanique, 1909. For longitudinal equilibrium 7146. Case where the propeller thrust does not pass through the center of gravity. In Fig. 20, the 3 forces H and R will pass through a point Z, which is the intersection off the vertical through with the line of action of H. Draw GL parallel to the line of action of H, and let it meet the line of action of RIN L. Then ZGL is a triangle off forces for the 3 forces at Z. And we have therefore HWBGL tilde ZG tilde LZ, suppose that one hair kept constant. H if the direct aeon of his nearly horizontal, saw that GZ is nearly perpendicular to ZH. Then for small angular displacements the length GZ is stationary, and L may be regarded a suffix point through which railways passes. That point L thurs takes the place of the previous investigations. If the position of undergoes a small displacement to M owing to change in the inclination of one or other off the planes, the new resultant R will act along LM, cutting ZH in Z, and the new direction of the vertical will, IZ. 72 Graphic Statics Chap. If ZH but not nearly horizontal, their relation GL-GZ equals Roman 2. W shows that ZL is a tangent to conic whose focus is G, and directrix is ZH, and the eccentricity E off which is equal to the ratio H/V. That point off contact PIS obtained by making ZGP a right angle, and this is the point about which the line off action of R turns in the case of phasemal displacement. Hence, given the position off the Mede 7 man the magnitude of H, the position of equilibrium Tn is obtained by drawing a tangent from M to the conic, and if this cuts Z hin Z, then GZ is the position off the vertical. The direction off flight normal MO can be constructed by the same method as before, that point of Fig. 21. Contact F, or lift HH horizontal, taking the place of G in the construction for O. Since an aeroplane is small compared with W, the conic isenellipse antitangents can be drawn to it from the point M, one on either side of G. If, however, we construct the forced triangle for the second tangent, we shall find that it determines a position of equilibrium in which the aeroplane is inverted. 47. If the engine be stopped, then, in the new position of equilibrium 2IG will be the direction off the resultant the intercept off a tangent to conic on the last rectum, is times the distance FR. Mn the focus off the point at which the tangent meets T directrix. This easily follows from the normal property SG equals ESP, and the property that PSZ is a right angle, the letter S being substituted for Gabov and G now L, eing the foot off the normal. Omen 4 longitudinal equilibrium 73R and will be vertical. If just above the line of action of H, instead of being below as in Fig. 21, the effects off the change will be illustrated by Fig. 22. One effect will be to change the relative direction off the vertical from GZ to GZ in MG produced, thus causing the aeroplane to dip downwards in front through an angle ZGZ. But as R moves forward from MZ to MZ, the flight normal will also move forward from MO to new position MO, so that the angles off attack off both planes will be decreased by an amount OMO. The net result WDLL be towed press the direction off the flight path relative to the horizon by an amount ZTZ, OMO. If instead off stopping thingin the propeller thrust H be reduced, eccentricity off the conic toe which MZ is a tangent will be reduced in the same proportion and in Fig. 22 MZ will therefore be displaced towards MGZ, so that the resulting changes in the position of equilibrium will be off the same kind as before, but less in amount, or an increase in the propeller thrust defects will be reversed, and the aeroplane will begin to rise. If it were possible to make thingles ZGZ and OMO equal, the direction off the flight path would be unaffected by stopping thingins, and under closely 74 graphic static CH. Roman 4 analogous circumstances the direction off the flight pathly might be made independent of the propeller thrust. This arrangement would be advantageous, but it is not in general practicable, as Brillouin has shown in the paper above referred to. If, as is usually the case, the angles off attack are small, MG will be large compared with the dimensions off the aeroplane. It follows that angle ZGZ is large compared with ZMZ unless GZ, and therefore the distance off the propeller axis below G are also large compared with the other dimensions off aeroplane, a condition impracticable for other fairly obvious reasons. The only possible alternative would be to make OMC/large compared with ZMZ. Even if this were mathematically possible, which appears not to be the case, it would have their result that every small displacement off the center of gravity would produce every large change in the direction off the flight path, a condition possessing obvious grave objections. Reader will have no difficulty in drawing the corresponding figure, with Theodore Figs. 20 and 21, for the case W where the propeller axis is below the center of gravity. In this case, when thingin is stopped or the propeller thrust is reduced, thingular displacements off the lines Gz and MO will be in opposite senses, so that if GZ and MO denote their new positions, the direction off the flight path will be depressed through an annoy ZGZ plus OMO. To some time, the ono less of attack on both planes will be increased by OMO, so that the descent will be less violent than it would otherwise be. Conversely, if the propeller thrust be increased, the direction off the flight path will be correspondingly elevated. After V longitudinal stability off single lifting systems, the simplest case. Single lifting plane propelled horizontally by a central thrust, Lanchester's condition. 48. Order to avoid algebraic complications at the outset, we first consider a system specified as follows: two surfaces, either of which may be replaced by a Fig. 23. Pair of superposed surfaces, SE so, off which the front surface S supports the whole weight off the aeroplane. Inclined to the line of flight at an angle off attack A, while there are surface soxasadale orator or auxiliary plane being placed in a neutral direction so that equals 0. Distance between centers off pressure equals /. The line of action off the propeller thrust passes through the center of gravity, and this fact will in the future be represented by the statement that the thrust is central, the direction of the thrust being along the line of light, which in the section is taken to horizontal. In these circumstances, their resultant thrust off Aeron S also 76 single lifting systems chap passes through the center of gravity. Thus, the center of gravity either coincides with the center of pressure or is orthonormal to st liraf, the center of pressure. In former case, we have for 81 both and equals 0, x equals and 1 slash equals. In the latter equals exactly and equals approximately, while for s, we have I equals I. The conditions of equilibrium give h equals ksm sin a w equals ksi u sin I cosa equals a slash cu sin a or equals a sabo. 47. The 9 derivatives are jr equals 2ei s u sin a, x equals ks u sin a cos ax, equals y equals 2 ks u sin a cos a y equals ks u cos a plus ksm yen, equals ksml n equals 0 n ks, jj n equals ks. Up 48. We obtain percent o equals gw, 49 rr equals cwkcl plus sin 2 plus s, backslash plus wksp. 495 tfb equals 2 gkss sin a plus wkss, pil plus sin a plus ks. 49c registered 2 tf equals yii, 49f at 2 pr. jf tf asterisk, f27 slash I2 smacosa. 49 fly it will be noticed that the conditions, and s positive require ito positive. That is, the auxiliary plane must have placed behind the main plane, a satale note in front. Virtue of the condition of equilibrium we have also m equals b. Odd sm acosa 2k equals ssj sin 2 fl, 1 sin 2a. 49. A vhen expressed in this form we see that odds ut and d section. O slash u contain the factor sin a, while the 3 previous coefficients remain finite in the limit when a equals 0. In biquadratic for backslash u, the last wo coefficients are therefore small in comparison with the first 3. And approximate the longitudinal stability 77 methods of solution may be used. In particular, we notice that in the expression 3, sd, yq3, xo, the first wo terms contain sin asa factor, wdl low xo contains sin asterisk a. The latter may therefore be neglected in a first approximation and the condition of stability, then reduces on division by to so 2. OE. 5850, now neoglektanov sinohave equals KW backslash S plus SNC plus WDS. 516 equals KWSR KSL plus JL. All. And using the first form of OVUW obtained from 50, the approximate primitive condition of stability Y plus KCUL tana backslash S plus S. 6 plus WM. 52, making use, however, of the equations of equilibrium. 47. Wehaven S equals KSSDW sinacosa equals KC sol W tana, 1 sin, equals KSSJ, IP tana to first approximation. Hence that terms underlined cancel to this order of approximation, leaving W, SUH tana SHSC. 53. Whence if 7 equals WLC saw that kiss the radius of duration about thexisofs GS, LTA. Naoi, this is the condition of stability obtained by Lanchester by an entirely independent method. Asusa has been made off the conditions of equilibrium in cancelling the parts underlined in 52. We ought to regard it as a modified form, Tothai's extent, off the conditions of stability. 78 single lifting systems chap. Another re-audigid counterfeit offsfahifich can I obtained by expressing u in terms of w by means off the condition of equilibrium, again neglecting the difference between tanna and sinacosa. Wethus o tain, JWS, asterisk, this form is probably better than the previous one. A sit only involves quantities depending on thuate and measurements off the aeroplane. In addition, the coefficient of resistance K, the propeller thrust, velocity of propulsion U and angle of attack are varied in a way consistent with the conditions of equilibrium the stability determined by 54a is independent of their variations. 49. If it is desired to proceed to higher degree of approximation in which cos nautic and tob equal to unity, the BIS plan is to write, as in section 34, SE equals secos and phi equals tanninth equations of equilibrium and the coefficients. And with this obtain, H equals KS backslash IW equals KS backslash U. 55 3T equals TF3A2, 56 AS3 equals WK backslash LC backslash S backslash plus S, plus O plus 21 CS backslash TJFI. 566 equals WKS, KS backslash L plus JL plus 2 KS backslash L plus F backslash. 56C, registered 2W3 equals YKs. SL 56D000GPO ISO, WSL, WSI equals KKS koi backslash C koshi plus S, plus 2KS SM a backslash SS plus L tilde SK cos A WSS. IH sin a tilde GSS plus A, 2 plus SH backslash plus sin A. and the condition for stability requires that Theiskspur be longitudinal stability 79 Sion shall be positive. Putting cosa equals I, Sina equals 0, this reduces Totley condition previously obtained. The foregoing expressions give the exact conditions of stability whether thingle able large or small, provided that their distance follows the sine law, and that the shift off the center off pressure is negligible when thingle off attack is varied. In view, however, of these assumptions not being exactly fulfilled in actual practice, it is probably better to be satisfied with the approximate solutions obtained by neglecting sin. A leading to W / percent as J cos 2 A plus so RPR 5, or U tilde tana. Evo COSIS / J or even simpler forms, 54. 54A obtained by substituting unity for cosanthes. In this / phi notation, the above conditions may be written or 7 VFV, 58 anthes Weschel regard as the standard forms of condition of stability as it will appear later on in a work. That the S / X notation considerably simplifies the algebra. Separation off the long and short oscillations. 50 in the biquadratic equation for / the last row coefficients, 49 psi. E. Contain the factor sin A, so that if A is small, these coefficients are small quantities off the second order in comparison with the others. This fact enables us to obtain approximate solutions off the biquadratic and to separate the different oscillations off the system. Let us write the biquadratic for / I plus 33x3 plus gx2 plus 3 x plus g equals 0. The suffixes being dropped as thigh were only used to distinguish the coefficients for symmetric and asymmetric. 80 long and short oscillations chap. Oscillations, ale theexence in x, and section being used to show that these are small quantities off the second order. If A is finite, then for a first approximation wemma, neglect xi and the aviation on dividing through by / becomes percent x plus 3b / plus A equals the roots off the equation determine oscillations whose times remain finite, however small Bethingles off attack, and we shall call these the short oscillations. If on the other hand / is small x may be neglected in comparison with section and Roman 9, and *IBX in comparison with A. Hence, the lowest order of approximation we get SX2 plus E equals or equals plus / T. This solution I saw first order off small quantities, and the values of x being imaginary, the motion is oscillatory. To find Dacloser approximation, we substitute the value of / given above in 3 /, still neglecting QU asterisk, and write the equation SX plus I2. 1 plus E equals 60. So we know that this order there all part off the values of xi equal to the small values of x thirds determine slow or long oscillations, whose period approximate to 27 RV, S/S, and modulus off decay I equal to 2's asterisk and is positive if the approximate condition for stability is satisfied, namely, Sx. S93 be longitudinal stability 8 I toxemu the character off the oscillations we must OO back to the equations of motion, W li, liar 2. S sine plus equals T plus S, sine cosa, V, R equals 0, 61H, KU/KU /IW // W / 25 1 sine cosau plus, S casa plus S, plus FFV plus, SU plus JJR equals 0, 61 10 plus S, LV plus SP plus FJF, R equals 6B 51 short oscillations. If we neglect sin altogether, the equations become 2UR equal, 62U9 plus S plus Y plus SL plus R equals 0. 62. SM plus Sol plus Y equal 62R and these are applicable to the short oscillation. The equation for / is in this case obtained by eliminating Van der Waals the last row equations, and this gives cake LPF plus KMI plus V plus SE equals 63. This equation is identical with the equation 5U plus 53X plus S equals if we take the values of / J3 given in section 48. And it is thus seen that the motions here considered are really the short oscillations off the system. Ratio V, risk given by either of these equations, say the second, which gives equals Z plus R tilde K ug S, J, or if preferred V or WJRX, where V is obviously the velocity off the tailplane perpendicular to the axis off. The equation is of course merely the equation off moments, being equivalent to equals KUS. LV LR, L. The velocity U is found in terms off from the equation. 82 short oscillations chap, X2. Ij R equals 0, which is derived from the equation of motion W equals W sin her equals R. 65. The assumption being in thesis that the effects off the epoxaires on 2 CMS may be neglected in considering the motion along the line of flight. Since, however, Udo's notator and Tothitwo equations from which the quadratic for A is found, follows that the short oscillations are independent of the variations of velocity in the line of flight and are determined entirely by the normal and rotational motions. Van R. In the next place we observe that backslash only enters in the equation, 63, in the form xju, and that the values of xju given by the equation are independent of the velocity u. The rates of oscillation are thus proportional to the velocity u. If instead of taking the time as independent variable, we take the distance flown, s, w years equals ut, we see that the actual path j described by the machine if he oscillating is independent of backslash j. The velocity of light, saw that if the velocity of light is changed, the machine will still perform the same number of oscillations. These oscillations WDLL subside to the sum fraction of their initial amplitude when the machine travels over the same distance. The condition of stability requires that in the equation for Zor xu, all coefficients shall be positive and Tyler f or k percent s plus ps, mod WSS p plus 8L0. 666. The first expression is essentially positive. Second will be positive if slash is positive, or if is negative, and numerically greater than Wx In the former case, though Williery, J lane is behind the assuming, of course, that U is neglected. Be longitudinal stability 83 main planes. The corresponding condition in the case of a doubly lifting machine is that T front plane must have a larger enel off attack T lion there are one, a swilb shown later. The negative solution is interesting in connection with aeroplanes having rudder planes in front, the right machine. The conclusion is that by placing the rudder either behind or sufficiently far forward in front of the main jigmas it is possible to skew stability so far as the short oscillations are concerned. The motion W will be either really oscillatory or subsiding in character, according to whether the values of /u are backslash. Line of steady flight fig. 24. Complex Oriole. The conditions being 3, 45, 6 negative or positive, respectively, that is h backslash s plus percent plus is. For MSS, p plus as j, or this condition may be transformed into f, sfis, is, plus as s 4/c2, c or 67, and it will thus be seen that if is negative or if is positive and less than a certain limit, the disturbance is subsiding in character instead of being periodic. Taking now a saying sample, the case where Zisrielin negative saw that is positive. Equation 64 shows that v, L-Randrer off opposite signs, and hence the angular displacement off the aeroplane isn't the opposite direction to the displacement off the tailplane. The motion off the tailplane is represented diagrammatically in Fig. 24 for G2 equals plus x/2 ff2, 6884 long oscillations chap. 2. Different displacements, one above and the other below the line of flight. Other case may be similarly discussed. Long oscillations, 52. For the second solution of the biquadratic, the values of backslash are to the lowest sufficient order of approximation, the imaginary part being off the first order and non the ideal part, determining the modulus of decay being off the second order. Obtain a general idea of the character of the oscillations, we shall neglect the latter part, and with use assume the oscillations to periodic. Writing SL4 secos on Fortney equations 61 give 2s/x li plus s backslash plus s plus v plus ls plus jr equals 69ys lv plus s l plus 5r equals 69r with f gismal. The only way of obtaining a solution, differing essentially from that obtained for the short oscillations, is by assuming that E is large compared with Van de Soth that E is sine or Rufius comparable with Van R. Moreover, in view of the fact that the terms containing backslash in the second and third equations, GL, were previously comparable with the others, it follows that for the long oscillations these terms may be neglected for a first approximation. If we neglect Zinthit-Leard equation, we obtain V plus equals 70, or Theno 7 mal velocity off the tail is 0. More generally, the equation, which may be written, V longitudinal stability 85 shows that the normal velocity off the tail is in every case small. Again, we may eliminate a S, E, and S from the three equations by multiplying the first by 1///, the second by 1 and the third by I/E indenting, and we get in removing superfluous factors plus ft plus t 1. And this, since it does not involve asterisk SC and so, be independent of the resistances and must represent the equation of moments about themata center. Observing that was assumed large compared with V, the terms of lowest order arithos underlined, leading to RTXI equals JR, 71A. On the other hand, if we neglect the second and third equations, we have one eliminating S, W2's backslash, EO plus S backslash V plus R equals 72, or substituting V equals L ragin, we obtain 2's backslash U plus S backslash L plus R equals 73 from 73, and 71A equals W 74I plus R KS backslash, which agrees with the first approximation for long oscillations given by taking the values off the coefficients in section 49, and neglecting terms containing /A in the value of low 53. Ta trace the undulating path DC skrill ed by the center of gravity. We suppose that the coordinates of this point at a time tear /ut and n. Thig says oft, 86 long oscillations chap, coincidiag with the direction of steady motion. Then if 6 Bethino-Wooler coordinate plus zj equals f7 plus cos sin, 75 rt equals u plus udo first approximation equals t slash f. Sin plus I cos 6 equals u6 plus arto for stage approximation. 756 ansins v silvery ass. H equals oi. I equals a kt equals ud plus v equals plus I or tc slash plus j, assuming the approximate expressions r equals /u slash y, v equals wehave finally equals c7x plus / or writing x equals / e where I equals s slash I where / is real. Put equals 4 cos x plus z sin a 7 and equate the real parts. Then we get the solution I equals acos x day /76 t equal ux sin x plus Roman 9 cos x dj if we writes plus ut. Y equals v, then x, it will be the coordinates off the center of gravity referred to fixed origin, so that the equations of the actual path will be given by x. Ut plus acos xn of I 77 /y equals ux sin x7 plus Roman 9 cos x7. I and ta trace that path idisonly necessary towed the ordinates of that curves determined, one by the equations aux equals ut acos, xy equals x sin x. 78. Longitudinal stability 87 and the other by the equations x equals ut plus acos /tj cos /t. 79. Off which the first I represents waves having thecrests more pointed than thetrophs, upper curve fig. 26. While the second represents waves the descending parts off which are steeper than the ascending ones, lower curve. The actual path, which is a combination of thetwo, should be familiar tonion ho-haze thrown paper gliders. Regard to the assumption r equals /ρ/g. In connection with the fact that while you have retained terms containing a, in the expression for tj, it should be noticed that terms fig. 25. Neglected in 71a would only affect the final result by cu entities off a higher order than the second. T /q, path off the center off pressure off the tiltplane is very approximately the first curve of fig. 25. The equation of motion being /r equals u plus tj where v, L negligible quantity. Effect of inclination off propeller axis. 54. If the axis of the propeller is /u along the direction of motion, the primitive conditions of stability will. 88. Inclination off flight path chap. Off course, bune change, butes the conditions of jui librium no give w plus ham ij equals ks /u phi. 80. The terms previously cancelled in modifying the conditions of stability will no longer cancel. The approximate condition of stability corresponding to 54 us / s, k if sin vl, corresponding to 54a Weschelhave according to 81a. If dispositive saw that the propeller thrust tends toward press the machine, stability is increased, and their verse is the case if the propeller thrust tends to elevate the machine. Effect off inclination off the flight path. 55. That the stability, both symmetric and asymmetric, of an aeroplane depends very largely on the angle which the direction of flight makes with the horizon, was first pointed out to be Mr. E. H. Harper. To whom the following investigations are largely due. The section next we assume the propeller thrust tall, ecentral and actins colono. The direction of motion saw that the tail plane is neutral and the shift off the center off pressure is neglected. The first three coefficients off the biquadratic area is given in 49 AE, but we have equals K8 SJ sin a plus KS sin, 82 D TFJI JJ TK SJS. /LTM Akasako 6 plus miasin div. 82. In virtue of the equation ofquilil riem w cos 6 equals fsgu sinacosa. 83. Be longitudinal stability 89. These reduced to tilde 3 tj3 equals kcs j2 sin a plus sinacos at 0 w equals ks j sinacosa 2 tana plus tan. md a2 wi equals jpq kss l sin cos 9. 84. C. Hence vanishes if the machine is ascending at an angle given height and 6 equals 2 tan. In this case, the discriminant becomes equal to 00 is negative, sotly at the flight is distinctly unstable. The limit for the angle of elevation off the flight path at which stability ceases is this less than the value given by height and 6 equals 2 tan A, showing that even other things being the same, a machine rapidly loses its stability low when it begins to rise in the air. It should be noticed that section vanishes when 6 equals 90 degrees, but this condition isn't likely to occur in practice. On the other hand, a positive value of is favorable for stability, saw that an aeroplane is symmetrically stable if feeing ho 7 is ontally it will be more stable if descending. An important consequence is that it is not safe to draw inferences regarding the stability of motor-driven machi from experiments with gliders. 56. For purposes of approximation and simplification, we shall suppose 6 and a both small j saw that cos 6 a may beta ken tob equal townity. In such cases, the value of 3 alone is affected by the inclination off the flight path. Corresponding to the approximate condition 52, we know have plus ks backslash l backslash 8. ht and a plus it and 6 backslash 8 backslash plus s 6 plus wps. 85, making use of the conditions of equilibrium, we may write the modified condition in the form corresponding to 53 ips backslash plus s. ks l tan 6 slash 2 tana g sid tana plus tan 90 single lifting systems chap. This being the modification required towed up Lanchester's condition to flight at an inclination 6 to the horizon. For the particular case where the machine is descending as a glider, saw that 6 equals a, this condition gives B228 backslash plus s ww G3 salt and a. Is auth at the minimum velocity height uj2j, required for stability I less than 2/3 that required by Lanchester's condition. On the other hand, if the machine is ascending at an angle equal to the angle off attack, saw that 6, a the condition becomes ysj Taylor requiring a value of u/g, more tangible that required for stability in horizontal flight. From the fact that 5 to 3, section are independent of 6. Section only contains 6 in the form cos 6, a, which is nearly equal townity, it follows that to your assumed degree of approximation, the short oscillations are independent of the inclination off the flight path, as is also the period off the long oscillations. On the contrary, th immoditus of decay off the latter depends greatly on the inclination. Effect A off head resistances and slash of variable propeller thrust. Asterisk JF. Asterisk in what follows we shall omit the suffixes in %33 so 2, OS, the context showing that we're dealing with longitudinal stability. 57. A under this heading we include all resistances not covered by the previous investigation, namely the resistances encountered by the body off the machine and eno and the arano. Also tangential forces due to skin friction and so forth. The most general supposition consistent with the longitudinal stability 91 assumption that the pressure off the aeronam moving igity varies as the square off the relative velocity, consists in admitting that the effect off these resistances is represented by additional terms in x yen, n proportional to u, and in the 9 coefficients x, n, proportional to u. We will forthwith present u-accented letters xn backslash to represent these added terms, which moreover satisfy the relations xi equals 2xo slash u, y backslash equals 2 yju, and n backslash equals 2 nju. Now in the first place, if y be different from 0, this represents an additional lift due to the air resistances, not accounted for by the off the aeroplanes themselves. Similarly, n represents a couple due to this cause. It will, I think, but generally admitted that these quantities may be summed to vanish in an ordinary machine, leaving only their assistance x tobe taken in toe count. At Isam at time, the following method shows that in normal circumstances, they would have little effect on stability. In first place, it isocitasho cf. Lanchester vol. I. Chap. Roman 7. Section 164, that for an aeroplane off given weight, the propeller thrust is a minimum when the head resistance is equal to the drift, while the horsepower is a minimum when the head resistance is on third off drift. In either case, the head resistance x is comparable with the drift ksju sin a, and is not large compared with it. If it be necessary to consider flights performed at speeds largely in excess of the most economical speed, in which the head resistance is large compared with the drift, a fresh examination of the conditions of stability will be required. Except, however, at these excessive speeds, the head resistance x will not be large compared with kcu sin a, and the part x backslash will not be large compared with the portion to a sef slash sin a of x due to the planes. In fact, x backslash will be small quantity off order a at least 92 single lifting systems chap. Off the remaining coefficients off the group, a y n. Those which do not vanish will not in general be large compared with x, and therefore they will also l eat least off order a. Bearing this fact in mind and neglecting quantities of higher order where these aerated to quantities off lower order, we obtain the approximate results. % equals wg 89 a tilde equals kws plus 8 g plus w psi. 896p equals kws vks l plus asin 51c. 89 ctt slash w backslash 3 equals ks cos s plus jks l off y plus k8 s4. Sin 2a plus 2 sin 89d. tjj equals jpks. jis Seneca Sacos plus s sin 2 plus j sin 6. 89e, that terms involving the other coefficients x backslash, y backslash, n backslash. Beno off her order than those retained and therefore neolifable. It is this seen that the coefficient x backslash alone enters into Theloist approximations, and this has an important effect on this stability. Now let the ratio of the head resistance atol drift KSI u sin A be denoted by V, then we shall have x backslash equals V. 2kc using A, and be making use of the condition of equilibrium 83th expression for simplifies down to equals KSS, L sin cosa, 2, 1 plus V, tana plus tan 6 plus, os 90, LUGU. While Theloist approximation given by G2WTTTX equals TWKS, Sol Sina, as in horizontal flight. It will thus be seen that themum effect off head resist ants is to increase the coefficient, thus increasing the 1n structure which gives rise to resistances not satisfying this condition would practically be off the nature of a plane, and should be included among these. The longitudinal stability 93, stability he increasing thema Julis off decay off the long oscillation. This result, which is best obtained in the first instance by algebra assistone above, is entirely in accord ants with what we should expect from general considerations regarding the nature of the long and short oscillations, as discussed in section 50, 53. Head resistance thus enables the machine to rise at a steeper angle to the horizon than would be possible if such resistance did not exist. For example, the effects of head resistance and inclination off light path will cancel one another if 2v tana plus tan 6 plus argic and 6 equals I. 91, or putting cos 6 equals 1, tan 6 equals 2v, tana plus equals minus 2, tan plus g. Velocity height. If the machine is ascending at an angle 6 given by Thie's formula, it will be stable as it would when moving horizontally in Thebeson's off head resistance, and generally the increased stability due to head resistance enables the tangent off the inclination off the flight path to be increased by the amount approximately given above. In all the previous work, the propeller thrust has been assumed constant, but either the horsepower or the rate of revolution off the propeller is maintained constant. The thrust will decrease when the velocity increases. In either case, the effect of these variations can be represented by addition of a positive term to x, and will be precisely similar to that of head resistance. It will be expressible in the form of an increase in the value of v defined above, and will increase the elevation of the flight path for given stability. The effect of such variations when the propeller thrust does not pass through the center of gravity can be investigated if the necessity arises, but the formulae will necessarily become somewhat complicated. 94 single lifting systems CH, V58, MV, EH. Harper has expressed the condition of symmetric stability in terms of the forces, taking account of inclination off the flight path and also off head resistance. This condition may, of course, be easily modified to take account of variable propeller thrust. When the following formula the thrust is assumed constant, let rho equals head resistance I2J equals KUSJ sino equals component off drift P. Propeller thrust then with the conditions of equilibrium we have JV sine equals R plus LP 92, and Mr. Harper finds that the approximate condition of stability 33 reduces to GL cos 6 backslash TJ SJJ plus LT2 plus 3I IP backslash 93. For the case of horizontal flight without head resistance mo equals 0, Ri equals P, and the condition reduces atones to 54 or 54A. After VI longitudinal stability off double lifting systems. Extension off results to systems other than narrow planes moving at small angles the principal of equivalent systems. 59. We have Lierto only considered case where the weight off the machine is entirely supported by the front plane or planes. There are plane acting only as saddle and being placed in a neutral direction. We shall no show how any results 2-1 oved for such a fig. 26. System can he extended tow system off the supporting planes placed tandem, and this recalibable lifting system. We assume the plane's tobsonar thesis offs that the principle of independence of height holds good, at the same time that principle allows the front ender planes tobe step, or placed at a somewhat different level, so that their salts may be less modified by the wash, which the front planes may produce on the back ones. Let us see a sob theorias off the front ender plane. AI 96 double lifting systems chap. Photo T/I spore/ and Ganural a Chenstrak I co Fig Roman 2. The late M.E. Lefebvre flying at reims, the earlier type of right biplane with auxiliary planes only in front off the main planes. Partial longitudinal stability dependent on the short oscillations isobtainable biplacing, though earlier planes sufficiently in advance of the main planes. Section 51. To secure longitudinal stability forth along oscillations as well, the front planes must be tilted upatagriator inclination than those at her rear. The aeroplane thus becomes a double lifting system, as discussed in S60. VI longitudinal stability 97, if their angles off attack, xi x. The coordinates off their centers off pressure. Using the S/A notation, S / equals S cos A8 equals asterisk C2 cos 0 2 slash Roman 2 equals tan a 2 tilde ta 0 2. Or see that their sistance derivatives can be written in the form r slash e. C7 equals SSV ijku minus 2s SR slash a. Slash 7 equals 2 zeriku equals 2 esks njkw equals 2 s fix njku equals 22 sxiv slash a. 7 equals 2 esks n. jq equals esks. 94 these involve the six sums 25 s phi 2 s phi 2. C2 SFX2. SX2 the values of which depend on the values of six quantities. S backslash slash adj slash I2 XX. The six sums are, however, note independent in virtue of the determinantal relation 0 to E. C7 equals asterisk 2S. 98 double lifting systems chap. Double lifting system. EI longitudinal stability 99 thrust bicentral. T lean the equation off moments as x plus so zo equals gives 4. Xi plus ojo equals 0. When xi equals 2, x equals 8 in the original system. Fourth equivalent system wehave x equals 0 x 2 equals I where is the distance off tailplane and the remaining equations give, remembering that thingles aerosmall, SEA 2 equals 20. 202 plus 10. 10 equals 9,000 a s equals 20. 20 plus 10. 10 equals 506 8 plus s equals 20 plus 10 equals 30 c s j equals 20. 2-10. 8 equals 40 d s j equals 20. 22 plus 10. 82 equals 720 e from a and b. Wefinda equals 18. 8 equals 271 hence by c so equals 2 equal. And by substitution in d. 1 equals 18 which agrees with their result obtained by dividing e by d. Thus, in the equivalent system, the areas off the supporting and tailplanes are 27 and 2 units. The inclination off the former is 18 degrees, and the distance between the planes is 18 units off length. Invariance of equivalent systems. 60. In deducing the conditions of stability off a tandem or double lifting system from those off its equivalent single system, a great deal off time may still be wasted in algebraical complications. And this was done in Mr. Harper's and me early solutions. A considerable simplification may be made by first making Alistoff the invariance of equivalent systems as follows. 1. If f equals 26/2 s j I. 96/2 equals isks is j thend, fan rare invariance. Off the center presents the distance behind the origin off the center off gravity of SE and SO, f the distance off the center off pressure of the planes themselves, it the radius off duration of S. Asterisk S2H2. S backslash SEL. V longitudinal stability law taking the other form, we may write it the invariants here are S backslash S. J equals S backslash S Roman 11x. 4 again S backslash plus S equals S backslash plus SOS. L equals 2 S equal. SI plus SES, P equals 2 SFX 2 equals SI plus S. And may write the condition WS backslash S, I or in a number off different other way. For example, we may write KGS backslash X2s which reduces by invariance to KIJ CSX. DV it is further to pointed out that the condition I/JL positive, which is itself in invariant form, shows that the front plane must have the larger angle off attach. It is easy to waste time in turning and twisting the conditions of stability into various other forms, and much of thy's danger is saved by a clear understanding of the invariance. The propeller thrust does not pass through the center of gravity. 62. If the propeller thrust does not pass through the center of gravity, it is obvious by moments or otherwise that if a tailplane is in a neutral direction, the center of pressure off the front plane cannot coincide with the center of gravity. Taking, however, a double lifting system. Suppose descending at an angle 6 with the horizon and assuming / the propeller thrust hits distance 0 2 double lifting systems chap. From the origin, Fig. 27, are its inclination to line of figlet, the conditions of equilibrium become, with usual notation KUES equals W sin plus H cos KXB SI equals W cos 6 plus H sin RJ KUX S fix equals HH. 101 in practice thingle 6 and T will be small. And from the first equation it is evident that his than small com paired with W, and still more is H sin T compared with W cos 6. That term underlined will therefore be neglected in diet follows, and we will further assume that cos oj may fig. 27. Bepute equal townity. This is equivalent to assuming either that equals 0 or that even if t just not 0, the corrections discussed in 854 Aeronoioible. Third equation shows, as stated above, that the system cannot be replaced by an equivalent system with both xi equals and fx equals 0. Or we can simplify the algebra is to assume equivalent system where either xi equals or fji. 2 equals q which is the better choice. Algebraically, the simplest plan would be to assume there are plane tobe neutral or phio equals 0. The third condition then giving ks /uxljbi equals hh. For the purpose of applications, their verse assumption icj equals seems on the whole most desirable, giving ksou/9 2 equals bh. For if his variable, or indeed h, becomes 0 through stopping thingens, the conditions of equilibrium are modified. It is clear that the easiest way of adjusting equilibrium is by turning the tailplane /EO. On the other hand, if the adjustment were made by varying x, this would involve shifting the center of gravity off the machine, thereby EI longitudinal stability 103 probably affecting the moments of inertia, and certainly affecting changes in the equivalent system that would be less easy to take into proper account. Assuming, therefore, for the equivalent systems I equals ANX, 2 equals I, the determinantal equation in backslash becomes O/Q2RT2 /ICXC, 7W cos 62, CL plus S2M2 plus SLML plus 2M2, tilde Q /O to JQ, /LIV1 JW sin 6-28, S plus SP plus equals 0. 102, the coefficients of the biquadratic are given L, Y% 3 equals FC, 103 A WIM equals KES /plus S /plus 8, L plus 21 C2s, 1036, 2, /W /32 W plus J zip SK2 phi, cos plus sine. LOSRFI where terms underlined are small, being off order fear if 6 is comparable with phi in comparison with those retained, and the may therefore be neglected. Behave further by the approximate conditions of equilibrium. 101 WCO8 equals KU% S /I plus SJX, whence H/3IS/W /421 VH cug equals K7J F I plus 103 /W /321 V Y /KV7J I 2 /Vi 2 I plus asterisk V2 H hit and J2 W equals XGXLL plus II. My H plus H stand 6S /plus S2 my M2J 103 RF 104 double lifting systems chap. When T I expressed in this form, it will be seen that 80/Roman 11 plus S 21-2 occurs as affector, not only oft butyl so oft whole of 3, except the last term which vanishes when 7*2 equals 0. Ace occurs in the case of A equals 0, writing /I fx equals V when O find that the condition 5 0 when reduced to its simplest form becomes 0. 104 when we transform this inequality by means of invariance talk over the case of a system where IIS different from 0, we may use the conditions of equilibrium, MHH and the invariance of section 60, including the notation SD equals S /Roman 11 plus 2x2 equals Y, equals S /Roman 11 plus SOX equals SI, and we may express the result in a variety of forms such as KG, JS /S plus S /SR plus JSDJ, W cos ID 0. 105-63. Mr. Harper has verified this condition by an independent method, starting with a system in which the tail is neutral, but the front plane has its center of pressure, not coinciding with the center of gravity. In this case, /x equals 0, but xi is different from. His condition is WS WS /WS /SXX, S plus S R plus XX plus V2, SL. L plus SX SSXX 0 106, which reduces Tothibov Ashe has verified. VI longitudinal stability 105 has also obtained the following form for this case. W/D2 FD /tan SR HRJ tilde / ZJ / ++-2/0. 107, whereas in section 60 Y is the distance off the center of pressure behind the center of gravity S /I squal Toth invariant SSY. Is V and S /plus S, R plus F2 FD. Re S /RD, V. If this be necessary also to work through a number of other formulae which are not of sufficient interest to justify their publication at present time. As his small compared with W, it easily follows that unless his large compared with it, the correction for non-central propeller thrust will be small. In an actual flying machine, H would certainly be small in comparison with I. The both formulae seem to suggest that making H positive, or lowering the propeller thrust, tends to increase the stability, but since a change of this kind also affects the conditions of equilibrium. Textion is not definite one until it is clearly specified what other changes in system are reflected in order to balance the moment of thrust. We suppose the balance to breasted by moving the center of gravity forward, or, what is the same thing, shifting the planes both backwards through a small distance. We may show from 106 that in the case of horizontal flight, stability is increased by lowering the propeller axis and decreased by raising %TIF. V pound 2. But the corresponding converse when 109 isn't satisfied ila simple. In this case, lowering the propeller axis, Yo6 broad planes chap, decreases the stability if the stability is small and increases it if already considerable. A case of more frequent occurrence in flying machines is that, in which the propeller axis and the planes are about the same level and the center of gravity is below them. This ice-equivalent to raising the propeller axis and the plane simultaneously above the center of gravity, so that the moments of the drift and propeller thrust continue to balance each other. It will be seen that in this case, the principle of independence of height must no longer be assumed. The corrections to lead to the formulae depending essentially on the small deviations from that property. Broad planes. Effect of shifting off center of pressure. 64. We shall now suppose that when the angle of attack is increased by the coordinate of the center of pressure of a surface increases by a p/a da as in section 23. This will in general be negative. Thus, taking Josel and Avanzini's formula, the distance off the center of pressure from the center of figure equals 0.6 Al, Sina equals 0.3 L sin Ax, whole breadth 2A, anthus A J A equals 0-6 acosa. 110. It will be convenient to write A, Fa equals ecosa high, and you will then represent, according to this formula, the distance off the center of pressure in front of center of area at grazing incidence when the angle of attack just vanishes. If any other formula for the center of pressure be assumed, when he'd only assume itohi function of aid find high as 0, A equals ecos A. We VI longitudinal stability 107 naught. In this section take account of the rotary coefficients of section 23. The effect of the shifting is to alter the coefficient n to qsx x and iv to k/s\x. In the section we shall assume that the propeller thrust acts along the direction of steady flight and passes through the center of gravity, i.e. when neglect the corrections of section 54, 62. Now an asynchrotous lifting system with neutral tails vanishes forth the front plane and u. Forth the plane, saw that tsx equals 0, that is, the part added to n, vanishes. This isn't necessarily the case for a doubly lifting or tandem system. For this reason, such a system does not in general possess a corresponding singly lifting system, which is equivalent to every respect, both algebraically and physically. An exception occurs when ice the SOMF for the front and rear plane. So that xsfx equals e s Roman 9 equals by the equation of moments. I may, however, still simplify the algebra very greatly replacing the doubly lifting system by asingly lifting one which is equivalent to it in every respect but the presence of to determine n. That is, we employ the substitutions of section 59. With the additional substitution of /sv/ for SAL, this determines the value of hut with their tension off the additional term. SSS/IX in third column, bottom row, off determinant. I have worked out the solution without Thusioff an equivalent system, but the algebra is for much longer, and it is therefore desirable to use this shortcut. The determinantal equation in X is no KU/KG/KUX LLLC X equals 112, neglecting terms off order /x in the first three coefficients. Yo 8 broad plamp S chap. And making use of the equilibrium condition W cos equals KUS/phi weget RS equals 113 AM equals plus 1 M Mr tilde 2 SM plus SSR. ESC TPV // equals tilde S/SFJ percent S/EL plus 2 SFV/X XO plus 8 1 plus S/EM S/F U plus tan 6 113 D at ACT W RG plus SVM 5 EV1 plus M tan 113 E in the approximate condition S B0 thepro ducts off the terms once underlined cancel, and in SWI may neglect /aton 6 compared with unity. For horizontal night the condition reduces to KGS/SSNL S/plus S2 SFX/S/E JLL plus SFX2 tilde W81 plus S/IJ0 114 65. For a double lifting system, this expression isoscelically transformed into the correct formula by means of invariance. In this case, S, L plus S/FI becomes SFGX, while ta transform S/FL plus SS/Roman 9. We observe that the term twice underlined in 2 arises from the determinant 2's/Y. SRI2's/FJI S/plus 8-2. S. 2I which becomes 0 minus 8 /Ix SFX22 as V2 S ESC0 ESC5 SAJX. Now if the bottom term in the first column had been 2XSFX instead of 0, the determinant would have vanished, and hence we find that VI longitudinal stability 109 2S S and FJ 2 Essex 225 V2 S 2 Esx 2 Sage equals 2 SAJ S and Esx with 2 S fix equals 0 originally equals 2 SNS /S2 I with V equals Phi/I and I equals XX. 115. It is not worthwhile to produce all the algebra that has been gone through in our preliminary investigations, as in all cases likely to of interest considerable simplifications occur. For in a system with twop lanes E/J will be small compared with I, and only first powers of need bear attained. It is only in the case of a single plane without Tadeloff and a kind that this might become inadmissible, and then the algebra becomes very simple indeed. We consider only the following cases. 66. Case I. Single lifting system with neutral tail. In this case, SFX equals 0. In the case of horizontal flippet, the condition reduces to C, W ca S, L plus SVM, KS backslash S backslash plus percent minus 2's backslash S, FLS backslash S, Eddie V0. 116. And the condition when higher powers of gyro are attained isn't much more complicated. Or flight at an angle 6 downwards with the horizon, if FJ L tan 6 be neglected in copyright Weget IS L plus 8V, L plus 2 minus 1, plus S app putting WKLF S phi sec 6 Weget UI tan 6 backslash, tan Q6 MM plus M L plus nan, plus 2 tana, slash cos R tan 6 Q cos 61. 11A backslash 2 plus 2 tax 7 plus R TTJ 0. 118. A quadratic in UJ. A low broad planks chap. 67. Case Roman 2. Single plane without tail or rudder. This case may be deduced from the preceding one be putting S, 2 and equals 0. But where the stability is entirely dependent on the shifting off the center off pressure, it is really easier to start afresh and useth a complete early IM photo. The S or 10 general illustrations co. Fig. Roman 3. Edward Mines biplane at Doncaster, an aeroplane having no auxiliary tailplanes or vertical fins. Longitudinal stahil I could only attain by means off the shift off the center off pressure with varying angle off attack, section 67, and this stability condition would thus impose a superior limit to the speed. There is no lateral stability, all coefficients in the biquadratic except the first were vanishing. Discriminant section 0 instead off the proximate substitute, S0. Wahave 21. 0 W backslash W ac 1 plus tan 62 slash Y. VI longitudinal stability and whence and with this substitution the condition which may be written reduces to FEL slash X tan. L plus asterisk FC2 SF L plus 2 slash 2 2 1 plus tan 0. 120 that is MK L plus 2 Y. Y cos 1 plus slash X tan. X2 L tan 0 L plus. L, or going back to the substitutions a S equals scos a slash asterisk equals tan a. UK cos 1 plus 2 tan 282, L plus tanatin slash etana L tanatin, tana plus itin. For horizontal flight 00 this becomes F72F, L plus 2 tan 282. ZJY etna HPPI oxy telly. 122, or again WMI plus in A slash Macosa for a glider 6 equals A giving IP 2K cosc, 1 plus 2 tan 282, L plus tan G2A. 2L plus 2 tan F goes slash 3 etan AL tan A, 3 S and 2A, L tan A. 123 or approximately. 124 G3 S and a V slash thus the minimum value of U. G required for the stability off a glider is only about 2/3 off the required for the same plane when driven horizontally through the air. Stability becomes impossible if the plane is rising at a greater angle than tan, 2 tan A. 112 broad planes chap. 68. Now Taquino Thieksak condition for the case of horizontal flight WFS, L plus sin V. I-22, KGS and Acosa and supposing 1 kept constant, there is an inferior unit toss in A, and consequently a superior limit to the velocity slash consistent with stability. That is to say, it is impossible to increase the speed of propulsion of a single plane above a certain limit without the plane becoming unstable. There will also be maximum value of a consistent with L22A corresponding to minimum velocity. The left-hand city off 122A will be found to be minimum when it equals 28 degrees roughly. On the other hand, in the case of a system of narrow planes, the condition of stability, when expressed in form 54 of section 48 gives a limiting value for W which is practically independent of the angles of attack off planes and depends only on their areas and their distances, in front of and behind the center of gravity. This condition is thus independent of the speed. For these reasons, it is highly undesirable that the stability of a flying machine should be made to depend on the shifting off the center of pressure. The machine should be constructed to satisfy the conditions of stability based on the theory of narrow planes discussed in this treatise. The effect of the shift off the center of pressure is certainly to increase the stability in certain cases, but the higher the velocity, the less is the advantage. This may easily be seen for the case of a single lifting machine from equation 118. Furthermore, the fact that no count has been taken of rotary derivatives, the FLX off which may become comparable with those off shifting off the center of pressure, renders it still more necessary torely for stability on the separation and difference of inclination off the front and tail planes. VI longitudinal stability 113. It is important to point out that these conclusions are not based on the assumption that the rate of shift off the center of pressure FA becomes small when A or phi is small, for according to your assumption it ends to limiting value, E. For large values of the investigation will require corrections owing to the deviation of the pressure on the plane from the simple asterisk sign law. Effects of friction, raised planes. Deviations from the sine law. 69. Suppose that owing to frictional resistance, the resultant thrust on a plane makes a small angle uith the normal. Then a difference will exist between the angle of attack on the angle aora plus which their resultant thrust makes with thesis off I. The case of variable is practically covered by the corrections of section 70 below. We shall write in this case s equals scasa cos A instead of s cos A and slash j equals tan A. Y equals tan A, or they're instead off assuming the principle off independ and set off height we may take account off the height off planes by writing a slash equals x. If x equals x2 if x will then thebsis are off the point where their resultant thrust meet the axis off. If we then write 2 slash a slash asterisk equals slash asterisk, so that x equals x, if the determinantal equation takes the from 22, 5f plus 2 sssc slash 22 sx, ssx 2 xxi slash fx plus jj equals 123. If is the sum for both planes, it is obvious that system may be replaced by an equivalent single lifting system with neutral tail raised at a sum height yabov I. 114 camber chap. The center of gravity, and the calculations might thus be used to investigate the effects on longitudinal stability of a low center of gravity. The formation of the coefficients of the biquadratic and substitution in the proximate form of the discriminantal condition of stability presents no special difficulty even in the most general case, but it scarcely appeared desirable to work out the formulae in this memoir. If the results at wanted, this can always be done subsequently. 70. If sine law of resistance be not assumed, we may still write r equals ksu sina, where is no a function of say ja, and according to experimental evidence k0 equals 2k I. In this case, their sistance derivatives only involve the values of rand r slash da, and we have s equals suk cosa plus. In A. 124, if we give k the proper value for the value off under consideration, the whole of the previous work holds good subject to the assumption that k slash da smace negligible in comparison if k cos A. If not, corrections may be applied, or the single lifting system. These corrections willingly occur in x, y, where s backslash will be replaced ly backslash kda, principal effect off curvature off main surfaces, camber. 71. From section 32, it follows that for a concave surface with neutral tail, the variations in the direction of r contribute to x an additional term, which I equal to ks_tj adj backslash a amacosa. Bi longitudinal stability 115 if we examine the correction due to the cause alone, assuming the other derivatives to have the same values as in section 48, we find that the correction does not affect percent registered or section. It introduces only terms off order sinento d, while for 3, when O find 3 equals kcs, L sin sin plus 2 kss, p sin cos A. 125 if. As usual with plane surfaces, the center off burst sure shifts forward as the angle off attack decreases. F backslash A is negative, and the effect off concavity is to decrease too, and this to decrease stability. If for very small angles off attack, however, the center off pressure recedes as angle off attack decreases, the effect off concavity then increases stability. In any case, the effect depends on thethermex yn, in assuming IV equals 0. In view of the difference in their resultant pressure on plane and curved surfaces, it will be more exact if we assume pseudo betheria off the equivalent plane surface. Effects of wash. 72. Another case in which the coefficients are modified in a similar way is where the wash produced by the front plane alters the direction in which the air impinges on their R plane. The angle off attack on the rear plane will be less than the angle which that plane makes with the line of flight, so that the resistance derivatives off the rear plane will again involve two angles A. In Lanchester's investigation, allowance is further made for the fact that oscillations off the front plane may produce fluctuations in the direction of the wash, which affect the pressure on the tail plane. In connection with the present investigation, the method of applying the latter correction for a single lifting system would be as follows. Let machine receive a small velocity v perpendicular to the I2 equals EI6 wash chap. Line off Higlet. This will produce an additional component velocity off wash current in the same direction, which will everywhere be proportional to when vis small. If the value of this component at head tail backslash EV, the effective change in the corresponding relative velocity off the and on tail will be v instead of v. Consequently, the portions of a y IV due to the tail will have to multiplied by e. This Cassathe correction is very easily applied. Considering the simplest case, the determinantal biquadratic after its less line has been multiplied by L/E becomes 0 SISJ plus F og 126. This equation is deducible from the original 1b substituting S, F for S, I/F or slash, and KE for a, and we only have to make the corresponding substitutions in the final result, which for horizontal flight now gives TRA Orions T with Lanchester's result. It should be observed that in this case we assume the tailplane toe placed neutrally with respect to Thuan. Will therefore make a small angle A2 with the line-off light, so that the first line-off Thebove determinant ought Tori WX-W2, S2 plus S backslash, X plus S, Jessin A, JJ cos 6 SJ. Sin A, even if goes A, is taken to unity in the second and third lines. This correction only introduces a small additional term, S/W backslash 2-2 KS backslash NS, FSM Sioin Jai, till I jij anthis is usually negligible. BI longitudinal stability 117 effective lage. The fluctuations in wash probably do not affect the tailplane exactly the instant when they aerosep with the main plane, but it would be rather premature and necessary to investigate the correction for the lag thus produced in the present state offer knowledge. It is obvious that the greater the speed of the aeroplane, the less will this correction be. Its existence should, however, be admitted. 3-plane systems. 73. We have seen that the loss of stability which occurs when an aeroplane rises at more than a certain angle is due to decreasing and changing sign. Now JG contains the determinant of the resistance coefficients, which for atwo plane machine has been proved to be 0. If, however, fortwawa substitute 3 planes or sets off superposed planes at different fig. 28. Horizontal distances from the center of gravity may have a value different from 0, and this fact may be used to increase the stability. For example, the machine may be provided with aeroplane in the rear, and a rudder plane or elevator in front off the main supporting surfaces, Asenth Farman and Curtis biplanes. Fig. 28. Let /SJ soyas 3 Betharias x zo. Access the abscissi or horizontal coordinates, and a thingles off attack off 3 planes, then with usual notation as backslash equals S casa / LTI equals tan AI, etc. Wehave. Yai 8 3 planes chap. By the rule for multiplication oft determinants this I equal to S phi, S backslash phi 2, S is MSS backslash S2, S is X1, 1 I equals 2's backslash S2's, and is essentially I positive unless it is 0. FV. BI longitudinal stability 119 shall again introduce the notion of an equivalent system of planes. Wecken, Asen section 59, choose asingle lifting surface with neutral tail having the values of 2 SV, SS ves asterisk SI. Esc/J esks, the same as for the given 3-plane system, but in view of the fact that is not 0, the value of S asterisk SV will no longer be the same, that is, will no longer be equal to SJ in the second system. Tojed over this difficulty, Wymage in the neutral plane divided in totwa parts, say equal parts for Simj, Licity, and /202/202C. L. Fig. 29. These parts separated by a distance 2c, the middle point between them still being at a distance I behind the center of gravity. The newsustum is this specified as follows. Fig. 29. Areas of planes inclinations coordinates SX. 23 planes chap. Fourth equivalent system we easily find J equals 2818 sin 2a. 130. And since a fourth original system has been shown to be essentially positive, it follows that C is positive, so that the distance of separation of that parts off the neutral plane is real. In other words, the equivalent system is a possible one. 74. When form the coefficients of the biquadratic for the equivalent system, taking into account inclination off light path buttonhead head resistance, always supposing the propeller thrust toked along thesis off-xan to be constant. Toth usual first approximation % equals GW backslash equals CWS backslash plus S plus W % P plus C2. 131.0. B equals WS backslash SS plus C2 plus SJ. 131C33 equals 2's backslash SC plus S backslash SMT plus tan 6. 131D E2W2 GGE equals XPKH cos plus Fisin equals XJSSLFIL plus Fitten 6. 2 equals S backslash S. Phi H ta first order. 131E if we suppose equals in the first instance and form the approximate condition S. 33.0. I shall find that the lie parts containing C which do not cancel arithos arising from the product of intertheterm underlined in X, which arises from the determinant backslash, and the condition of stability becomes 8, 1K % 8 backslash plus S. 8 backslash JTJMKG 8, W plus 2 FJI plus W ij backslash K, J2 plus A plus C, U. 13 ZJ the approximate condition for stability is the same as it would bane horizontal flight with C equals 0. When the direction, BI longitudinal stability 121 off light makes an upward angle with the horizon given by T22, 133. And this represents the increase in the angle of elevation, consistent with stability obtainable by separating the halves off the neutral plane through a distance 2c. Tossum up, the values of 53 iod are increased hit the substitution of 1 plus C4 1. The value is increased hit additional term due to the deter M and ant, though for ascending flight it is decreased hit the term involving tan 9, which is the negative. The netricid is an increase in thepy oximate discriminant 6, S23, this increase being equal to the increase in 5 multiplied with the increased value of 6. Or the original system, the increased elevation obtainable by this means is given approximately by the relation CWJFJN sin 9 equals JV negative B negative. 133 RT, a size evident from equations 18a. Textion off the hitherto neglected rotary coefficients off broad planes. 75. The transformations and methods off the last article help us to obtain some estimate off the general effects off the rotary coefficiency. A and J are only as deductions from assumed hypotheses concerning them. A plausible assumption is that when a plane rotates about its center ophi resi LRE, their resultant thrust is not affected by the rotation to any important extent, possibly not at all, but that the moment off the pressure so stup tends to retard rotation. If this be assumed, the effect is represented by an additional positive term in n, and can be made equivalent to the EH checked, considered in the last article off changing 2i to S1 plus R by a suitable choice. 122 rotary derivative CH, Roman 6 of C. The effect is this to increase stability, and in particular to increase the angle of elevation off height path consistent with stability, as indeed is almost evident from general considerations. If rotation about the center decreases the moment off resistances, the effect will be to increase stability. This alternative hypothesis seems much less plausible than the first, but questions of the kind cannot be decided by rule of thumb reasoning. In this connection, it is a significant fact that a balanced plane which is free to rotate on its axis will rotate continuously when placed in now-wind, but the decisive test is obtainable. Section 29. By attaching the plane to pendulum placed in an air current, the axis of suspension passing through the center off pressure, and observing whether the oscillations subside or increase. After Roman 7. Asymmetric or lateral stability, straight planes and vertical fins. Further hypotheses regarding narrow planes. 7q. In dealing with the longitudinal or symmetric oscillations, we assume to say definition of narrow planes that t-like chord or distance from the front to the back edge of a plane was small that the unequal velocities off two edges due to rotation had a negligible effect on distribution of pressure. On the other hand, in studying 124 narrow planes chap, to the right and left of the element, and depends only on the velocity of the element itself. A further assumption which Weirgard is simply in the statement that the angle of attack is small is that the pressure on S follows the well-known sine law, or what is equivalent, that the resultant thrust on S equals KdSXI LQ \\t. Roman 2 \I velocity x normal velocity relative to the air. A correction is probably necessary, at least near the extremities of the plane, but it is necessary to take all such corrections in toe count at the outset of the discussion. See section 93. To make the argument more general, and applicable in particular to surfaces which are bent to pour down towards. Are their extremities, let us suppose that x, y, zareth coordinates off the element ds, and that /m, nareth direction cosines off the normal to the element. Fig. 31's, their resultant velocity oft cis u plus u or plus zq, neglecting terms off the second order, while the normal velocity is 1u plus u or plus tilde q, fw, izp plus xr, plus 7 ieoxq plus ip. S auth again to the first order. We have fourth the resultant thrust ronthilment dr equals kds /lu plus 2 luu or plus zq, plus mtjvzp plus xr, plus nuwxq plus y. 134. Roman 7 lateral stability 125 and t-like corresponding forcing couple components. When integrated over all the elements, L ecum x equals FLDR, y equals JMDR, z equals FNDR, L equals F, NYMZ dr m equals FLZ and XR n equals F MXHJ dr. 135. If the aeroplane is symmetrical about the plane offs I slash, such integrals as contain only odd powers off Zoroff n. When CLR is expressed in terms oft S by means of 134 will vanish, and this will secure the conditions that the resistance derivatives x, y, w, j, q, and z, l, m, j vanish, i.e., the independence off the symmetric and asymmetric oscillations. We obtain x equals Ujkl ds plus 2 ui kl ds plus of klm ds plus erf klmx 2 li ds. 136x y equals uj klm ds plus 2 uj klm ds plus of km ds plus erf kmmx minus 2 li ds. 136 I slash n equals u klmx li ds h2 uf kl. mx li ds plus of kmmx li ds plus url k7 and x li. mx2 li ds 136hz equals o chi ms plus upt kn and y mz ds plus uct kn2 lz tilde nx ds. 1362 l equals o ikn and y mz ds plus upt k and y mz fds plus yuki k and y mz 2h and x ds 136 slash m equals oic and lz and x ds plus upch k and y mz. lz and x ds plus ukf k. lz and x 2 lz minus 7x ds 136 m. The first three refer to longitudinal stability. By putting slash equals sin a, m equals cosacos slash 3, n equals cosas in j3, they might beep lead to the case of an airplane whose surfaces slope upwards at an angle toward their extremities. This casa reduces to the problems considered in chapters v ibiputting cos equals 1. In most cases of immediate interest, this approximation will be sufficient, and 126 straight planes chap. Therefore, it is considered udesirable to produce a fuller discussion here. In lateral stability, the difference is important, and we start with the simplest case. Straight planes, 77. Bytheswemian planes perpendicular to the plane of x, y, in contradistinction to the beneplanes just mentioned. Fourth, these we put slash equals sin a, m equals cosa, n equals 0, and obtain z, j, l, m. Each equals in writtens, ri equals jz, is equals moment of inertia of area off plane with respect to the plane ox, y, wehave lp. Kui koia lq equals 2 kui sin cosa m, equals kui sin acos a, m equals plus 2 kui sin 2a. 137. Substituting in the expressions for the coefficients in section 20, we find and omitting the suffixes, both 0. Also for a single plane, 6 equals 0. If there are at planes whose angles of attack are a, and moments of inertia e and loit will be found that equals 2 widge sm aa. 138, which also vanishes if equals I or the planes are parallel, likewise if I or 1. 1 equals oron off the planes is our other plane off negligible span. In every cassette wo if not 3 roots off the biquadratic vanish. This indicates lack of stability, the effects of which can be studied by writing down the equations of motion T7. 7 lateral stability 127, the last will show that there is no tendency for the machine to right itself if it feels on side. For there is no term in them depending on thection of gravity, and therefore no tendency to assume a definite position relative to the vertical. The first tells us that if the machine has heeled over through an angle P, gravity will tend to make it slide down sideways, and there is nothing to check this tendency. The maintenance of lateral balance must therefore be effected by furnishing the machine with warping devices controlled by the operator. Or else other planes, such as vertical fins or others, must be added. The explanation of the third vanishing root, off biquadratic in the case of a single plane may be seen by multiplying the second and third equations above 19p, q, by Sinan Causet auditing. This eliminates the right-hand side, and the resulting equation expresses the fact that the couple about anormal to the plane is 0, so that there is nothing tending to check rotation about this normal, i.e. there is no directional stability. The following points should be noticed. 1. The effect of a strafe narrow jilkme on the lateral stability depends on the moment of inertia of its area about its plane of c/emmetry, and does not depend on gyration of the plane. Forkson did not enter into the coefficients. 2. A horizontal rudder plane for steering in a vertical P lane does not affect the stability unless its span is considerable. 3. Weme right I equals SR where cis the re and R the radius of duration off the plane. Weme following Lanchester. Extend the method to cases other than those off narrow straight planes by suitable conventions, astow the value of the various terms, these becoming his aerodynamic and aerodromic radii. 128 straight planes and fins chap. Effect off a single vertical fin. 78. If we suppose a vertical feor plane off area T placed a lower parallel to the plane ox, I with its center of pressure for grazing incidence, at hepoy at x, y, 0 or x, y, z, their assistance derivatives do tothize fine air given by z equals k2z equals k-ti equals k-tux l equals k-ti lp equals k-tuf l equals k-tuxi m equals k-tux m equals k-tuxi m equals k-tux. 140. While for a system of several such finswinly have to prefix the sign of summation to expressions off these forms. These expressions are, of course, to-bedded to the corresponding derivatives due to the main planes. In the case of a single main plane and a single fin we obtain 2. Your WJJ3-3, kk it, I sin x cosa j 2 kitic t by fx cos b plus x phi sin 6. Old W, JN4 equals tilde TPI kk ti 2 sinaco 6 cosa sin 6, x cosa / sina. 141e, consider the case of horizontal flight equals 0, and to simplify matters, suppose thesis oxis a principal axis of inertia, so that f equals 0, an assumption we shall frequently find it convenient to make. In this case, the second term in the expression giving x reduces to the part containing now the in lieu of securing the stability condition. S positive is by making x cosa, y sin a positive, that is, placing the fin rudder in front of a line through the center of gravity perpendicular to the main plane, i.e. briefly speaking, placing the rudder in front. but this necessarily makes the first term of negative. Aerosol which can counteracted by making negative and sufficiently large in the second term of t. That is, by 7 lateral stability 129 raising the finken, sidingably above the center off gravet. Mr. Harper and I have investigated the matter at some length, and find that when stability could theoretic ally be secured by this means the height off the fin would have tobe far too large, in proportion to horizontal coordinate x, tonable the method tobe lead, imply construction off a convenient flying machine, and further that the difficulty increases with the velocity u. There is, of course, a possibility of improving matters by making the product of inertia f positive, but this again does not appear very promising. In a flying machine of the no-prevalent types, Yis's aeroplane very different from zero, and the choice lies between putting the vertical rudder behind and making the machine unstable through a negative or putting it in front and making it unstable through negative. A machine, the dimensions of which were given, it would be a C to obtain in either case numerical approximate solutions off the biquadratic and toad side which was lesser of that woe evils. But a more interesting line of investigation is Stokes-Amin how wo finser better than one in securing stability. General case of a number offens. 79. It will be observed that 1. Their systems derivatives due to vertical fins parallel to the plane offs are independent of their ZCO ordinates. Thus, for example, two vertical planes symmetrically placed at opposite sides of the plane offs are equivalent to single plane of double theoria in the plane offs, midway between them. 2. For a number offens the resistance derivatives contain thesoms offer stand second powers off their coordinates, and arithas transformable by the rules k. 30 straight planes and fins chap. Applicable to centers of gravity and moments of inertia. Compare Lanchester's fin resolution. Writing T4 thesum off the reas off fins xy for the coordinates off their center off mean position or center off pressure, and ilf m for the moments and product off inertia off the reas off the fins with respect to axes parallel to the coordinate axes through the letter O, the sportan general elum tratio high co. Fig. V. Len Curtis biplane at rhymes. An aeroplane with two vertical fins, namely a triangular fin in front and a rectangular rudder plane behind. Thigh. This arrangement is favorable to lateral stability if the center of pressure off that fins is slightly above or in front off the center of gravity and certain other conditions are satisfied. Section 84-86. Point, the expressions z, m, off the last article hold good but we have L equals KLT plus M, L equals M equals KUT zij plus P, M KUTX plus M. 142 short and the algebra assume provisionally that K equals K. The Finchave adafferent resistance coefficient R from the main planes wecken subsec usually restore the difference by putting a factor cage K into terms depending on the resand moments off the fins. The determinantal equation is most conveniently now Putin the form of equation in xj cug and becomes 7 lateral stability 131 plus slash cos O 2 j sinacosa tx fj tzit plus p bj plus dx plus m j sin ficos plus 2 zina equals 143. At his stage it will be found convenient to write slash for slash cos on slash u for tana, consistently with the practice previously adopted in dealing with longitudinal stability. When the determinant is developed in the quadratic form, the following expressions represent the coefficients if x slash k cff slash is taken as variable 5, b, s, etc. Representing the coefficients if a is taken as variable 9t equals w at f. 144 0 m equals an abf, f3 i m plus 2 tzI plus 2p plus bi plus tif plus 3 slash. 144 slash asterisk tilde 2 equals n2e plus vo. 3i plus 2p plus br plus ml plus wt2tf plus m p minus 3txy plus pj slash x plus tx plus m plus w ti mj2p slash plus I vi I slash plus ymm p tft. 4 xp slash 144 cjj equals 7 t2 I ni 2 spf plus ilf plus ti m mp ella plus p p plus slash t I7 fmktwrnf khbg asterisk tilde f tilde plus 72 cf 2j cost pxi ti slash sin m xbj backslash lu. These expressions become much simplified when 1. The angle of attack A of the main planes is small saw that slash x is small. 2. The finser saw small that we need only retain the love t significant terms involving 7 orthocorresponding moments, and nd in particular m, pair small com k2. 132 straight planes and fins chap paired with slash. 5. The product of inertia f vanishes. 4 equals aura small. In these cases we have to sufficient approximation 21 equals w equals wib uoa b. KXJFI equals BX, TAMO plus BM, plus WI backslash TX plus ILF. 145, 2, WTX TW a WTT WT80. In these forms, we notice the folio vivenar points. 1. The moment often M off fins does not enter into the proximate values except in the part of S which isoferter T, all thowgly thehite yoff their center does enter. There is this node ventau e inmakins if a different from 0, that is, placing 2 finso nabov theather. 2. Id isositosith at MAL, P is 0 fort wo fins, and positive 4 in a number greater than 2 unless collinear. This expression occurs among the neglected terms. There is no advantage in using more thant wo fins. General character off oscillations, approximate resolution off the biquadratic, resistance toroling. 81. The conclusions obtained in connection with the separation off Longan short oscillations, in the case of longitudinal stability do not hold good in the case of lateral or asymmetric oscillations, and in the present case the separation off the roots off the biquadratic assumes a different form. In first place, if they're Aeronophins, only the first wo terms off the biquadratic remain finite, and these give rise. 7 lateral stability, 33 tune finite value of x, say x, which equals percent with the approximate values of 145 ah, wahave kmj a 146, whence backslash is essentially negative as required for stability. This solution determines the rate off damping off an angular velocity pabout thexisofx, a size evident from first principles. Itis in fixed equivalent to the dynamical equation. dpi equals p. 146a while this damping tends to check thoroughling motion about the line of flight. It indicates no tendency torstor equilibrium when the machine hashield overthrough a definite angle about this line. Even when fistnets are onda not small, backslash will in general be negative. Yav abfi essentially positive by the theory off moments off inertia, saw that percent is positive, and writing equals tmy plus z, etc. Assignmentary rigid dynamics we find with tmm and peach 0 jrj equals w/2m x cosine x cosa 2i slash scylla plus i's mz. 147 an expression which could onlive negative in the case of a preponderance off the mass off the flying machine between the planes x cosa usina equals x cosa 2i slash sina equals 0. A machine theme as off which was a distributed miss. HTB expected to exhibit anomalous behavior, but would not occur ordinarily in practice. If they find area instead off being 0 is small, the remaining roots zo a 3, 4 off the biquadratic will be small compared with backslash. They will therefore all make percent x asterisk small compared with x, and therefore will be given to a first approximation by the Kuljic ig x plus e backslash plus 2, a plus e equals. 148. 134 straight planes and fins chap. The condition of stability assuming the simpler approximate form S register Ds B0, which greatly simplifies some off calculations, and will be used hereafter when the full condition is too complicated. 82. In certain circumstances, the separation can carried further. Notice that /FPI PFN /KUG contain terms off first order in 7 backslash W leal in. S/KUG asterisk 1 term contains a factor off order ta, and the other isof the second order in T. As there are at one dependent small quantities on T, it is not possible to lay down a universal rule, but we may generally expect the biquadratic todic that form percent x asterisk plus 58x plus s to x plus s equals 0, the first row coefficients percent, 3 being finite, section off first order, e off the second order. We have discussed the finite root ai equals, /% another root backslash is given approximately by x4 equals, / and ice off first order. The middle pair off roots x, and x3 areoferter, the first approximation to their values being given by 33x2 plus 2 equals 0, and using this value I can substitute percent /* equals x2, g equals x2, leading to the second approximation given by m plus /6fx plus s equals. 149. Omitting thexents. We see that the modulus off decay of the oscillations, determined by the middle pair off roots x gan / cis sqi. 7 lateral stability 135, thus being directly related to the discriminant section. The method will fail and all thirds will be off the same order. If s/bay off theater off smallness of /b asterisk, that is if t bayafferter al if the method is applicable, then the various roots correspond to 1 arapid subsidence determined by /I damping of thingular velocity off-rolling. 2. A slow subsidence determined by x4. 3. An oscillation off medium period determined by /2 and xg, but the rate off subsidence off which may be comparable with that corresponding to x4. 83. An important point is carefully to distinguish the terms depending directly on thection off gravity. These arithmetums containing cos 6 and sin 6 in full expressions for jkuff and /kug. In the abbreviated or approximate expressions, they are distinguished by having u in the denominator. These Arithmetically terms which determine any tendency on the part off, machine to sum return to definite position relative to the vertical. No method which ignores these terms will give inherent stability such a swillinable a machine to right itself when displaced. The presence of u in the denominator is in agreement with the effect that, while the air pressure on a moving plane increases with the square off velocity, the effects off gravity remain constant, and therefore their relative influence decreases. The occurrence off / elsewhere is due to having measured resistances in pounds instead of poundal. Now arose off the homogeneous form off the equations of dynamics. Case 1. Systems with two raised fins that has same height. 84. We have already pointed out in dealing with fin that x cosa, usine occurs with a positive coefficient. 136 straight planes and fins chap. In it and with negative coefficient in 1. The simplest way out of this difficulty is to make x cosa usino equals 0, that is, top at the center off pressure off the fins in a line throwgly t center off gravity perpendicular totally main plane. Since a small, it comes practically to the same thing if it equals 0, i.e., if the center off pressure is vertically above the center off gravity. This arrangement is mentioned by Lanchester, who refers to its advantages in securing stability. A further simplification consists in assuming that wo fin sto beyond the same level, Socrates T2 center of pressure y fig. 32. The same for I joth. In this case, il/jan p will vanish, and if 71 t fig 32 arithurias xx, the coordinates of the fins. We shall have 27 tilde a tilde t asterisk tilde tt equals rp x square off distance between fins, 151. The condition IOII registered I reduces to negative. That is, for stability thedgens must herseized above the center of gravity. The expression for reduces to 2, x3c/3j, 3tm r22 I by fx, cos 6 plus, axfj sin 6 152. Remembering thaxismol, the condition unnegative will certainly make positive if f equals 0, and will also necessarily positive under the same conditions. If f, 7 lateral stability 137 is different from 0, there will still be wide limits consistent with the stability conditions 5, and positive. 85. The final condition. Section or 3, 5t minus 311. Section 3 necessarily becomes complicated, and it is useful to obtain some simpler condition which will suffice for the purpose. Now, after a good deal of laborious substitution, find that even the tangent off the inclination u is small the condition /wa. 153 substituted and makes that expression essentially positive. This condition is therefore sufficient for stability. In verifying this conclusion, it will be found best in first instance to make the substitution in x registered, and with the value subtained to substitute in theoric is rather laborious. Fourth, a case where higher powers of Lateral. I have tried the same assumed condition, which of course may be written kuqp cos asterisk f n \v rj lsrt, but the substituted in leaves certain negative terms in it. These are ohily much smaller than the positive parts in cases likely to occur in applications. At some time their presence shows that the above condition can only on a sufficient provided that a further condition is satisfied. It might perhaps be worthwhile to examine this particular case at some future time. The above condition may be put into various modified forms by combining it with the condition of equilibrium W equals KSM Sina. If we put a equals we and / equals SB / then and will be radii off duration off the mass off the machine and off the rear off its main plane respectively, and we find on substituting P asterisk V, Y2H sin, a Roman 2 equals WJ. 1536. 138 straight planes and fins chap. H being the height to which the velocity u is due. Even Thiebaud formula isn't required if the total area off the fins is small compared with that off the main planes. It will, in fact, be found that the terms of which are of the lowest order in tand m are essentially positive. It will thus be seen that the present arrangement possesses a wide range of stability. Moreover, the stability isn't much affected by the angle 6 which the flight path makes with the horizon section and the important parts of x containing costa knots in 6. A further obvious property is that, should such a machine be turned upside down with the fins below, it would become unstable and tend to right itself. Case Roman 2. Both fins at head level off the center of gravity. 86. If a P equals and J/I equals P equals 0, the condition of stability at reduces when equals to x cosa usina 0, that is, the center off pressure off that wo fins must bane 7 equals. 7 lateral stability 139. Now it may be true that this condition would usually be satisfied in uniform flight, since even if a plane were gliding down uniformly under gravity, 6 would only be equal to a, and an value of 6 greater than a could only be consistent with steady motion if the machine were retarded by reversing thingons or be a sufficiently orate head resistance. At a Asamet time, behave talk consider the possibility of a machine diving down at a step angle either in order torque over lost speed or as thurasult off a sudden gust off wind. And we have further to remember that the conditions of lateral stability are FL. VI. DL al J chematic vi U O for WK ict BLA lane used at PA U. An aeroplane having vertical auxiliary fin situated fore and aft of its center of gravity. From T-Lee figure, it appears probable that the center of pressure of the fins in this case was rather behind and not much above the center of gravity, and that the arrangement failed to secure lateral stability for this reason. Independent of those four longitudinal equilibrium. Conclusion is that, if for any reason such a machine should dive downwards at an NOF reader than that consistent with their relation tan to tan A, it would lose its lateral stability and would probably turn round sideways. This might result in an accident, either through the machine becoming uncontrollable or through breakage caused by undue strains. The erroneous impression might at least be produced that the machine had suddenly been struck by a side gust off wind, causing it to turn sideways. Analyge off the risk and its cause might enable an aviator to save the situation. 40 straight planes and fins chap. 87. Using the approximate forms of section 80, which, bait remembered, assume F equals 0, we find MKF equals plus 2, 155, and the stability condition 0 reduces to WXR WB cost, 2 tonatan N WLKUITB plus FVTX plus M. JJ 15 asterisk. This condition can be put in various forms or replaced by a simpler condition, which is sufficient, although not necessary for stability, by omitting some of the terms in the denominator of the last fraction. For example, omitting TX\M. We see that stability will be assured by taking WXR W cos 6, 2T LKV TF10 J. 156a, which from the equations of equilibrium gives WXR SU tilde \M 2 1 plus F, 2 1 tan 6 \, 1566, or again, we may write il/2T% B equals WK, whereas the radius of duration of the reas off the fins about their centroid, and K, just the radius of duration off the mass off the machine about thesis off I. In this case, the condition reduces to an any case stability is secured by making VL large and X small, that is, by making the distance between the fore and aft gins sufficiently large, and plus I7 ig the center of pressure not too much in advance off the center of gravity. At a Asamet time, X must not be too small, otherwise, section will become too small. Further, if an isnegative or the aeroplane is rising, the condition of stability S becomes more de situ. 7 lateral stability 141 safest fifas thingle offers uteresis. White, asaveher already shown. Stability ceases when thingle off descent becomes greater that given byton 6 equals 2 tan A. The existence oft will limits is a direct consequence of the fact that section occurs with negative sign in S. Present system ISON in which a numerical calculation of textual oscillations obtained by solving the biquadratic for a machine of given dimensions would pay off considerable interest. This suggests a subject for future investio adiu. Case Roman 3. One fine above and on behind of the center of gravity. 88. The following investigation of thy's case is due to Mr. Harper. Of suppose the finstobifarious T at point 0 Y and T at X 0 fig 34 and clearly have 7 4 T. 142 straight planes and fins chap we suppose F equals 0. Also if Ti S arcabove and behind the center of gravity Zandy will 1 TH negative. In these circumstances all coefficients except D are essentially positive. Putting equals 0 we see that the condition positive is secured by making ref /7 E27 /Zor 27 sinicosa which is equivalent to the condition asterisk L plus E positive 159. 159a it will thus be seen that for stability the distance off tail fill behind the centiof F20 must not be less than a certain inferior limit. It will be noticed, moreover, when 7 lateral stability 143 tionks L plus L. J positive repressionals the condition that if the machine receives its mid-lampdar velocity off-road a tion about a vertical axis assing through the tailplane, x0, the moment off the resistance is that isotix tens tacos themachi tohi lavarahout thixasof plwtn. THR Sport and Junal 111 Vatrations Co. Fig. Roman 7. Rugi ER flying at Blackpool. The voice in type with its box-like arrangement of vertical fins ice equivalent. So far as lateral stability is concerned, tow system with one fin above and on fin behind the center off gravity, the conditions of stability off which are discussed in section 88. S. Towards the left side off the curve that it would describe in virtue of the rotation. Effect off two or more transverse planes. 90. We have already referred to the case where, instead of a single main plane, there are at planes the moments of inertia off which are /I/O, and thingles off attack off which are A. The differences in this case and the argument applies tone number off planes may be conveniently exhibited by the following artifice. Construct the vector sum off vectors J2A and 144 straight planes and fins chap 7 2A, and let it'll E/2A. Then in the Forniuki 3LV RT lie resistance derivatives behave JJ cos oj plus low cos u equals hill plus low I plus icos a 1/is in oj plus I. Usin 2 equals J plus /I plus J sin A. I go /J sin QJ cos oj plus J Roman 2 I. 2 tilde I J it follows that the values off and J nij. Arithasama as for the C plane I, A. TV heil the values O/LJ. And MQ error increased by the same amount as the would the moments off inertia MM9 off the fins ivory etch increased I2/I plus L plus I. The effect will in general be to increase the stability particle arly in such arrangements as those of cases E and 11 above. Of course, if A is small/JF Joe 7 will be small and generally off the second order in AJ. The increase of stability will depend mainly on the equivalent increase in J70 in view of the flick that the value of M has little effect on the stability. Effects of structural and head resistances and twin screws. 1. As in section 57, most general effect of air resistances acting on the framework, tangential forces such as friction on the aeroplanes, and other resistances, will be to introduce additional terms in t'other resistance derivatives which we shall denote by accented letters Z, L, M. In an ordinary flying machine, some of these terms will probably be small or unimportant, and it will probably be only possible to make rough and ready estimates of their value. In this connection, experiments on models afford most desirable tests. When the machine is turning about thesis off with angular velocity q, the parts off the framework which are moving with the greatest velocity encounter the greatest resistance, and the circumstance, as well as the resistances on the fuselage and framework supporting the tail, give 7 lateral stability 145 rise to the positive coefficient m. This coefficient divided by /FF/ must be to the determinant, 143, of section 79 in the samoterm a slim moment off inertia m, off the fins. The effect of the moment off resistances is this equivalent tone increase in m. And from W it has already been shown this increase generally increases the stability. Similar effect occurs in a machine furnished with twin screws, like the Wright machine, arising from the fact that in turning round, the outer propeller moves through the air faster than the inner one. If the end that is moving quickest exerts the least thrust, as assumed in section 57, 5, the effect will produce a further couple tending against the rotation can, further increasing the value of m /. From elementary considerations, it should be pretty obvious, without further discussion, that if the speed u off the machine isn't largely in excess of that required for maximum efficiency, so that the head resistance is not large compared with the drift, C/B7A, the value of m will not be large with 2 QI and m tilde A or 2 QEM. In area sonably designed machine, L will be off the same order of magnitude, will thus be small compared with KU icos A or KUI. This J-Raj dirty ice equivalent to the obvious statement that if the machine receives a small rotation about the axis off, the moment off air resistances on the framework is small compared with the moment off air resistances on the main planes. It follows that the coefficient L has generally negligible effect on stability. The same thing is evident if we notice that the presence of the added term in the middle term of the determinant, 143, is equivalent tone increase in the moment of inertia m, which has but little effect on the stability. As regards the terms m / and L, these will probably either vanish or be very small even in comparison with L. 146 straight planes and fins chap. L and m / in the case of full designed flying machine. At most, they will be comparable with IKU IFJ, and small compared with the corresponding terms KU IJ dependent on the main planes. If they are equal to one another, their effect will be equivalent to change in the product of inertia of the fins. In any case, there would be no difficulty in taking account of them should the necessity arise, but this appears hardly probable. It will not rashly neglect effects of resistance represented by Z, L, M /. These include the effects of lateral resistance off the fuselage and framework. For a machine with a low center of gravity, Z and L / will evidently be important. For a machine with a long tail, Z / and M will be important. The terms must not be neglected, because they occur in the small terms of the determinantal equation for /, and the arianly associated with terms depending on the fin switch are also in general small. If the new coefficients satisfy the reciprocal relations Z equals U and Z equals M /, their effects can be represented by means of vertical fins. For instance, Zj and L / are then equivalent tone increase Zjq in the value of Tx, and if positive have thus the same effect as shifting the center of pressure off fins forward. and soon. This interpretation may perhaps be more useful than a direct calculation of the effects of these resistances. At some time, when the determinantal equation is developed and the coefficients are expanded, it is sufficient for a first approximation to retain only the terms of lowest significant order in resistance derivatives in question, as done in case often sin, 145. Probably their reciprocal relations z equals L backslash and z equals M backslash are satisfied in almost every case. But though further discussion thus becomes rather uninteresting, it may be pointed out that if these relations are not satisfied, it is still possible to present z backslash z M bisuitable. 7 lateral stability 147 increases in j backslash ti, t, r and tolo for t difference, writing 2 backslash ij plus ri and 7 slash plus for tie and t's in second and third columns off first row off the determinant, 143. The only important additional term introduced into the coefficients of the biquadratic is a term, txf in the value of jioi pif, other changes being negligible for a first approximation. There is another way in which the propeller may affect stability apart from gyrostatic action. The torque produced by the propeller affects the lateral equilibrium, and this, of course, indirectly influences stability, but it is further possible that when the aeroplane possesses a small angular velocity j about thixosofts, the propeller torque is slightly altered, being increased when the aeroplane rotates in the same direction as the propeller, decreased when it rotates in the opposite direction. This effect would L is represented by an additional positive term added to L. We have seen, however, that such an addition would in general have little effect on stability. Effects of friction and curvature off main surfaces. 92. Making use of the property of Neroiv planes assumed in section 76, we may easily deduce the corrections analogous to those of section 69 applicable to lateral stability. In first place, you observe that if thingle of attack A, defined by R equals KSU sina is not the same as thingle A, defined by the property that R makes an angle DO with thixosofts, then supposing at our main constant, we write slash equals slash cos acos A phi equals tan A slash U equals tana, and the resistance derivative become LP equals cur, LG equals 2Q at JL, M equals cut IM equals 2K Urexty, 161 L2, 148 straight planes and fins chap. T lie F feet off concavity off the main surface may be investigated by applying the considerations of section 71, TOA stripped soft the main plane, the legitimacy off the step being implied in the definition of neuroplanes. If the machine receives an angular velocity p, about thixosof x, and we consider annulment ds, distant z from that axis, the change in thingle of attack is to equals zj slash u, the center of pressure of s shifts forward through a distance a, j a da, and c being the radius of curvature, the direction of renthellement changes by an amount da equals a da slash c, their solved part of relong thixosof changes by an amount r casada, and its moment about oib, r z casada. The final result is stowed to j a term equals slash qa slash c, fa sinicosa ais. 162. If the plane rectangular and off constant curvature throughout its span, the corrected expression for m becomes mp equals qx fx p backslash a al. 163. There is a small corresponding change in L, which now becomes L equals cur L plus tj lix 4, ar slash c. 164. But it will be seen that with slash zan slash asterisk small this correction is negligible, the correction in M being alone important. These modified forms are only based on the assumption that a slash c is constant throughout the span off the planes, saw that this factor can be removed outside the sign of integration. This would still be true if the planes were not rectangular, provided that all sections parallel to the plane of x, if formed circular arcs off the same angle. It must be remembered that if the center of pressure moves forward as thingle of attack decreases, for A is negative. The correction does not affect the value of B when F equals 0, and under the same condition the effect on S. 7 lateral stability 149 is probably not very important. The most important effects are sin T and the part of section involving sin 0. T-lick portion oft involving cos 6 will be unaffected. Corrections for aspect ratio, for effects at extremities off main planes and forewash. 93. In order to simplify the algebra, we have in general assumed that the resistance coefficient kiss the same for all the planes under consideration. The sameter effect, however, is a function of the aspect ratio, as well as soft camber, and therefore in dealing with different surfaces C, so we ought to have retained IC co-S, where we have written KS and KS. It will be seen, however, that the algebra is quite sufficiently complicated as it stands, and the same results may be arrived at waiting till the final formula have been obtained. Then NML tiplying each area by a coefficient dependently, kj on the aspect ratio. This equivalent to reducing all the areas to the same aspect ratio, or more strictly, Tathasame resistance coefficient K. The results will hold good provided that reduced areas subtained be substituted for thexual areas off the planes in the formulae. Connection with lateral stability correction is required owing to the fact that the conditions assumed for native planes at small angles do not hold good at hair extremities off the main planes, where the stream lines flow over the tips instead of being, at any rate, approximately two-dimensional. This leads to correction in the value of slash or slash dependent onthoforms off the planes at their extremities, and therefore, the substitution OFA corrected constant fourth radius off duration implied in slash and slash. According to Lanchester, two such constants are required, which he calls the aerodynamic or aerodromic radii. If this is the case, one will occur in XN, 150 straight planes and fins CH. Roman 7J theater UJL, and M, if would denote by I/1. The corresponding values I corrected in accordance with this hypothesis, and if we believe their salts the approximate values given by 145 section 79, we find that I/, depending on the OD/NRME radius, replaces slash everywhere, except in the part of it involving cos 0, where I2 occurs. In section, we must replace I2 ficos, sin 0, by I-22u, cos 1/sin 0, and assuming tobe small, the effect off the difference between slash owned I/I equivalent to u increase in thingle which the flight path makes with the horizon from to 0, where e equals 6 plus /r. 165 if Lanchester's aerodromic and aerodynamic radii are equal, this effect vanishes, and the inlet change required is in the assumed value of slash. The correction for wash, when two fins are placed one behind the other at Hasame level, should give little difficulty, if it is needed. But the effect could be avoided by placing the fins at slightly different levels. After Roman 8, lateral stability BP and T uplanes, comparison off benoplanes with vertical fins, 94. When O consider such cases as that office up porting surface consisting of a pair of wings bent up at a dihedral angle or bent to pat their tips. In all such cases, the general expressions, 136 of section 76 must be adopted as the starting point, and the first point which J presents itself for inquiry issue farth effects off bending upper equivalent, in their effect on lateral stability, the addition of vertical fins. Consider a pair of filaments D soft such planes situated symmetrically at R on opposite sides off the plane of 152 bent up lanes chap. X, slash, and let the normals these elements meet the plane of X, Y in a point J, fig. 35, then in every circumstance their resultant pressures on that elements will pass through, slash, and will be equivalent to single force acting through J. The and Lippard off this force WDHW ill affect the lateral stability Wilbates component perpendicular to the plane of X, Y. And this it might appear that the elements were equivalent to single vertical fin off suitable area placed at point J. This, however, is fig. Roman 8. Amoxoplax Roman 9 construction by Blériot X 1907. Aneroidlane off Antoinette type in the connoisseur off construction, showing the benepwings and vertical tailplane in their azelsoth arrangement off the engines, the propeller in front being detached. The photograph was taken by Thuther in July 1907 on a visit to Blériot's factory outside the Port Maillot, Paris, with the late Captain Ferber, before aeroplanes had flown or Blériot had become well known. Not strictly the case as the velocities of Rand are rare in general, different from that of slash. If 7, by the coordinates of J, the equation off normal gives NZI 166, whence is 2LZ NX equals NX, and NY MZ2N/NX equals N plus LZ. Urge, and therefore, Roman 8 lateral stability 153 substituting in the formula of section 7, Weget Kerr equals slash equals Z. Equals I2 107 the effect off the element. S is this equivalent to that off element tie DS in the plane 2, equals at het point, RJ 0. In terms off first columns, buten the third column this is no longer the case, the factor Z is occurring in place of. The equivalence will be exact in the case when 1 equals. Slash, this requires that equals 0, i.e. that the element should be placed parallel to thesis offs, and therefore in a neutral direction to the line of flight, in which case it will exert no lifting force in steady flight. The simplest application of this property consists in replacing a vertical fin placed above the main planes by two small benoplanes situated at the extremities of these planes, sloping upatan angle /3 to the horizon and parallel to the line of flight. In this case, Weschelhave 1 equals 0, m equals cos/3, n equals sin ys, and if ace the rea over their plane, that will be equivalent to single finiferia 2 cr sin/3 placed at a height z cot/3 above them. Such a pair of terminal planes may be called stabilizers, the term being used whether they are neutral to the line of flight or not. Pair of tandem planes each fitted with neutral stabilizers will this be equivalent to system with two raised vertical fins, T. lias affording a convenient substitute for the system of section 84, which possesses such wide limits of stability. The substitution of stabilizers for fins, of course, presents obvious advantages not directly connected with the present investigation. 95. In the general case, it is convenient to put I equals synom equals Casacos 8, I equals Casasiu / 3. 1, 8. 154 bent uplanes chap. J11 this case, ace-like angle off attack or angle made be thielment with the direction off steady flight, /3 the angle through which thielment is bent up about an axis parallel to thexis offs. We shall also, in accordance with our usual convention, write ds equals d scos a. I equals tana andweget ny. Raz equals cosa usin /3, 2 cos /3, is an x equals cosa and zx sin 2lz and x equals cosa 2 ij. Zx sin 13 and writing equals 2 cos /3, usin /3, the expression's fourth derivative becomes sin 2f/s q tilde z, f and equals fsml 32z. R sin ds equals /sin /3 ids equals /t des equals jc2, zx seal 3, ds equals j sin, phys x sinl b ds equals j. Tilde sin dsf equals a /is. Sin /x. R sin 0 ds, 169. These expressions and the subsequent analysis become considerably simplified when x sin /3 is negligible com j ard with phys. This occurs L in the case of a single lifting system with bent up wings in which x equals 0. 2 in the case of a tandem system of bent lifting planes, when thingle offal ending up /3 is small compared with thingle of attack a, and the span off the planes is not small compared with the distance between them. Single lifting plane with terminal stabilizers. 96. The following solution, due to Mr. Harper, applies to the case of a single straight lifting surface S, furnished at Athens with a pair of small stabilizers, off total area 2, an 8 lateral stability 55, each being off area JT, placed with their centers in plane A, equals 0 at head points R, 0, Y, Z, and R, 0, Y, Z, their angles off attack being on the stabilizers being bent up at an angle /3. In these circumstances, the traces of the stabilizers in the plane x equals will make angles db/3 with thexis offs. If the direction off the plane at r be produced tomet g/ in p, and g cuba drawn perpendicular on rp, fig. 36. We shall have rq equals z cos /3, /sin I equals t with the notation off the last article. Thingle y3 rumst obviously not the two small if the stabilizers are tobe efficient. We shall, as usual, employ the notation t cosa equals t /lfc equals tana, which greatly simplifies the analysis and further shorten matters. We shall assume, in the first instance, that kiss the same for san t, it being distinctly understood that differences in this respect are to be corrected for an and future formulae by multiplying t or tinth, final result by the ratio cage cof-thetwo coefficients, and that this correction may, in certain circumstances, be considerable. Itonly remains to right ij. JT forfeit S equals in their salts off the last article, tor move thesine off integration, and towed the results tothos of section 76 due to the lifting plane. 156 bent uplanes chap. Thus thek juadioi in / becomes plus 2t/x. Sin 13 plus tv, sin /iv tie, cj plus 27y plus 2 equals 170 and the coefficients are given by 31 equals w ab f. 171 j equals t sin iabf plus WIE plus RS filfx plus TZO plus BI plus teek, L 2 t sin 2, 2, 4 2 3 plus bound plus 2 WRTY, C, F plus sinaf FC. 171 C plus JRR rich JTS MTIII. ZF Oscend, FZBQ cos, 171 FO at WK asterisk IK / tilde. The condition of stability S. Positive in the case of horizontal flight requires that shall have positive and greater than phys phi, that is, in the figure R stana B QT on. 172, and stability necessarily ceases wedi thingle off descent passes the limit given by tan 5 equals 2 tana. 173. The condition RQ positive is satisfied if the normals to ran BF meet above the center of gravity, not below. Thebove condition makes the first term of negative. In the case of equals and F equals 0, the condition positive leads to that is R stana RQ, Tana JRVRJI. 174. 8 lateral stability 157 if BI Kutian O, that is, BKU Ikasasana. 175. This condition, 174, is satisfied for all positive values O for RQ being positive, and for equals 0, in which case the planes would be neutral. Now, since a the condition of equilibrium W equals KUS sinacosa plus KUT sinacosacos /3 follows that when tismol compared with S this condition may be written approximately #I. 1, 6, and that this condition is sufficient even if tis not neglected. This requires that the radius of duration 0/themas off the aeroplane about thesis of should exceed that of theorias off its main planes about thesis of if this condition is not satisfied. Stability cannot be secured if the stabilizers in thenutered position. The conditions of stability may be written res taxia 1t5 1 isq. Offred. Off duration off masabout /s rq tanask. Offred. Off duration of sabout 0. J if the stabilizer's area attached at Hisame level is center of gravity, Sanji coinciding, RQ equals R scos and RQ must therefore R sanda. This further Tobe observed that by making the product of inisha F negative, both and can be increased, a condition FCT variable to increase stability. 97. The further condition necessary for stability is somewhat complicated, and we shall only consider the approximate form when both tan/r are small, and f equals 0, fj being also small from condition 172. In this case, 1. RCU2 approximates to RP 158 Antoinette type chap, while theterm D becomes negligible and the condition which may be written as BC/ leads to T, KM which becomes ICM tilde that is TOB, RQR Atana R stana 7 equals J, //IO /7W 2 Sinacosa coda / 178. Assuming the approximate condition of equilibrium, will be observed that the system here considered does not include /A7Z, E. The addition of thighs would further complicate the algebra, and the case may perhaps stand over for future investigation in view of discussion of the analogous problem of the next article. The possibility of satisfying the conditions of stability with negative offers another interesting question, especially in view of published accounts of Dun L3 airplane. Theory of Antoinette type. 98. The following investigation is due to Mr. E.H. Harper by the Antoinette type issued a machine supported by a single lifting pair of bent-up wings and provided with a vertical tail or rudder fin. It is stated that in such arrangements it has been found necessary to place the center of gravity, J lower than the intersection of viewings, and we shall assume that this is done, the tail being, however, onilval with the center of gravity. We are not concerned with the effect of a horizontal rudder, which only affects the longitudinal stability. 8 lateral stability 159 taking Fig. 37 as representing the section of viewings in the plane of y, z. Ran a point on viewing on the positive city off the plane of x, y, g cap perpendicular on viewing a p produced. Let rp equals p, pq equals e, saw that rq equals z cos phi, /sin 3p plus e, rp equals, sec/3 equals p. Also as opposed the rudder off area t placed at x, 0, 0, xl I know neophative if the rudder is behind. With this notation, the determinantal equation becomes cug plus /sin/s plus t w cost /kuj p plus e sin ds up sin I scos ds xt plus e sin ds /w sin 6f chi cug kwg x plus 2ff gypsin I cos ds xt fx cug minus 2 ipip plus e cos ds bx cug plus xd j fipip plus e cos fit s plus 2 li cos z s. 179. Assuming the hypotheses involved in the definition of narrow planes. These expressions would hold good even if Thingle's off-attack and off-bending upon/3 should vary 4 different parts off-thewing, asympthewings of birds, provided pan eastwell asan/seriatriated as varying at different distances from the plane of x, y, and arrow properly defined, p naught being the distance of r from p. O Antoinette type chap, L ut the length off the tuyagent at h measured tot the plane z equals 0. Except in case of numerical calculations, however, the investigation would probably be FJXR2 complicated TOLED tonasimple results. Whether F4 consider only the case where a/3 era constant. In this case, we may write JIP plus FS equals slip plus Y plus K, etc. I/L odd O, Fig, Roman 9. Latham's trial flight. Ink sample off Antoinette type in which lateral. S fahlily isubtainable by means of I bent-up wings. Roman 2, center of gravity below the dihedral angle formed by thewings. Roman 3, a vertical tail fin placed at not less than a certain limiting distance behind the main planes. Section 98-101. A longitudinal stability aeroplane may probably be regarded as a single lifting system with neutral tail, though it may be desirable topely corrections for displacement off-center off-pressure and camber, where prefers centroid off the positive wing, and is its radius off duration about that point. Will easily be seen that JPHL est S. FPD estic J estic V and the other minors off the determinant all simplify in. 8 lateral stability I6I the same way. Of Italy this simplification n lone, the other terms being leftist integrals, the coefficients off the biquadratic become Kuj% equals W ab F. Is ort equals W2 xf p co hf plus or minus LS, fix B Oj plus F co HLB, LS plus B jip plus fit S plus ab F, SM, plus T backslash ab F plus wax backslash 1806 equals 2. 4 slash X cos 2 slash 3 dash 3 F cos slash 3 plus B, CI 5 plus 2 Y J cos 23. SVJ V sin slash 3 RC plus. KJT slash JPF JIP plus E plus TWXI, P plus Euros JMS plus AJ, 2 slash. E cos slash 3 plus S FIP sin cos plus X sin 2 and DSTRWFL 3 FIP cos slash 3 plus 2. C sin plus E Z. S plus B, P plus IFT SJ, 180 CJF 3J 73 3 equals F FIM 13 cos S, K plus. Asin O F cos D G cos 3 JPFHS plus. J5 cos 9 I sin I P plus 6. 5 R plus R, 2 euros V cos 2 3. IE X sin J cos plus X sin slash 3, SVXP plus MSW plus J2 I F cos 6 asin 9. 180 FZ at TFFKU equals XHPQ tilde. V sin slash 3 cos plus J G asterisk cos 9 sin slash P plus F slash S plus 2 XP cos 5 cos slash P plus F. W sin up plus E, KM 180 E99. Case L, let T equals O nor tail. %3, all thetherms are positive except some containing first powers of F. These vanish when F equals 0, and moreover thetherms underlined twice in fair small compared with other terms and coefficients saw that the value of F has little effect on B. On the other hand, a 7 egative value of F will certainly increase both san 2 and will consequently have favorable to stability. We shall, however, here suppose that F equals 0. Make section. Positive when equals 0, we must have S in slash 3 positive. The condition D positive then requires that sin should be positive, hence M must also be positive, that is M. I62 asterisk Antoinette type chap. Thewings must tend upwards, not downwards, and their intersection must be above the center of J gravity, not below. The range off inclination off light path consistent with stability will be limited by the condition, from 0 tan 6 to tanakos. The condition J positive becomes with F equals QBC 096 plus adjskos Anbeck slash N, 6 RB Coffid. 0. BTJIP plus ETTTP. O V SMA COSA COSP U, LOL TF SK Sinacosa COS slash 3. 182. At U, the coefficient OF will be positive and the condition 0 will be satisfied for all values OF. This condition can be written B cos 6 KUS Sinacosacos slash 3K, that is from the conditions of equilibrium BWK. 182A, or radius off duration off mass about oi radius off duration O fetch plane about its centroid. In every case, or for rectangular planes offspan about 2BBW by 2, 1826 if. However, this condition is not satisfied. There is a superior limit, to the value of beyond which the condition fails. Condition 0, for which the approximation 6, registered 5B is probably sufficient in most cases, imposes a further limitation on the value of E. It is obvious that 633 is positive when E equals 0, which happens if 6 equals and is negative if equals 0. The conditions may be satisfiable for all values of making B, WK sufficiently large. Otherwise, the value of cannot exceed a certain limit, EO less than the limit E determined by the condition 0. The general conclusion is that, while the condition of Omen 8 lateral stability 163 stability, S requires the center of gravity toe below the dihedral angle, too low apposition may lead to the failure of the condition S0. The effect of this failure would be that the modulus of decay of the oscillations would become negative, and the oscillations would therefore increase in amplitude. This conclusion is entirely in accordance with their results of experience as stated in aeronautical books and journals, all through my Oinst somewhat ill-defined notions that commonly prevail regarding the meaning of stability. The production of dangerous oscillations has up till now not been always attributed to its probable cause, namely inherent lateral instability. 100. Case L, let E equals 0, stability being due to the rudder T, let X be negative, rudder behind center of gravity positive. In this case, all thetherms in 5, S, with the exception of F containing F, are positive. To make the part containing tin at positive in the case of equals 0, it is necessary to make 2 tonopip plus T, ds, x, 7, 183 j tan 13 up plus E, dss auth, assuming a suite of that 6 equals 0, and supposing the wings rectangular and of span 2b, we must have 46 tona, 3 tal T 183a. That is, the rudder, if placed behind the center of gravity, must beat a distance behind greater than b tanacot in order to ensure stability. This arrangement is usually not much difficulty in securing the additional condition of stability I0. For in 180, when tan y8 small j cug reduces to the zingly underlined part WBF, P plus euros, ls backslash and the positive part of s, also underlined, when multiplied m2. I64 Antoinette type ch. Romanate bythies cancels out with the product of Thetwo singly underlined terms in their Stophy section. Is essentially positive, at least Whitley this approximate value of 101. It will this bay observe that raising thewings above the center of gravity is favorable to the condition. Section positive, but the possibilities in this direction are limited by the conditions, and section positive. On the other hand, the addition of a tailplane is favorable to the latter conditions, but there is an inferior limit to the length imposed by the former. A combination of the two may evidently be advantageous. Another arrangement of considerable interest is that in which two rudder planes are placed one in front of and one behind the main plane, so as to make 2tx equals 0, and in which, moreover, 6 equals 0. In this case, the conditions 2 and s will certainly be satisfied. Range of stability. So far as I is concerned, section diminishes when the aeroplane is descending, while so far as is concerned, diminishes when ascending. A suitable combination of raised planes and or the two effects may be made to counteract each other. In section, the part containing sin is WRT, PLI sin cos slash 3tx slash p plus EVS sine. 184 anthis will vanish if t oc equals s sin cos sin slash 3 cos p, R2. 185 giving four rectangular planes and s mol ta equals fs sin cos sin slash 3 cos. 185a in this case registered will be independent of 0, except for the factor cos 0. If the coefficient of sin 0, instead of being 0, is made small, the range of inclination consistent with stability will still be correspondingly extended. After Roman 9, general conclusions, 102. It may, is supposed, Benoit can prove that an aeroplane can be constructed which possesses inherent stability, both longitudinal and lateral, when propelled horizontally, and also when the inclination off the flight path to the horizon does not exceed certain determinate limits. Further, these limits can be extended in various different ways, and the limitations regarding the angle of descent can be removed. Will be evident, however, that an airplane constructed on these lines differs in certain points of detail from those adopted by many of the most successful present-day aviators. Indeed, it does not appear to be denied that some of these are unstable. Thus arises a divergence of opinion regarding the advantage or otherwise of inherent stability, and all that can better know is to state the case for the side, which is supported by the present investigation. The case of longitudinal stability. There is probably very little need no to advocate the claims of auxiliary surfaces, for use of these has by this time become almost, if not quite, universally recognized. Practically every modern aeroplane is provided with tailplanes, and many are provided with both front and rear controls. An arrangement which, as shown, gives increased longitudinal stability, and in this connection is especially useful in ascending. The original right biplane was 105, I-66 General Conclusions chap, provided only with auxiliary planes in front, and this arrangement could only be made longitudinally stable by throwino thuate forward and inclinino. These rudder planes at a stepper angle to the line of flight than the main supporting planes, an arrangement which would certainly give increased drift or assistance in direction of motion. Since then, a stabilizing tailplane has been added in the machines put on the market. This in connection with lateral stability, however, that different counsels prevail, some authorities considering it preferable to avoid thusiopent planes, toward use vertical auxiliary surfaces to the minimum necessary for steering, and in short, to abandon inherent lateral stability altogether. Among their reasons given for this course, it is stated that L devices such as fins orbitup planes are every uncertain in their action. 2. They are liable to oscillations. 3. They may cause serious rolling when the aeroplane is suddenly struck by a side wind. Now, it will be seen that the problem of lateral stability is of considerable complexity, especially when bent-up surfaces are concerned. It is to see how an attempt to deal with the matter bitriol might lead to certain results, the significance of which it would be difficult to understand without some kind of theory to guide. In attempting to avoid one condition of instability, we run the risk of introducing another. If a single vertical rudder only is provided, introduces one kind of instability when in front and another when behind. The production of oscillations indicates that the aeroplane is dynamically unstable. In other words, that the arrangement instead of producing stability has had their reverse effect. We may illustrate this point in connection with the Antoinette type. It is stated that the bent-up wings necessitate a low center of gravity, but if these ispatulo oscillations, 9 general conclusions 167 are set up. This is entirely in accordance with Mr. Harper's investigations given here, which show that one condition of stability can be satisfied by placing the center of gravity below the dihedral angle formed by thewings, but that another condition sometimes requires that its depth should be less than a certain limit. By placing the center of gravity too far below the dihedral angle, the machine may again become unstable. The kind of dynamical instability that is indicated, if the conditions, is that in which oscillations of increasing amplitude are set up. 103. The behavior of an airplane TV hence and 7 by gusts of wind depends to very great extent on its inherent dynamical stability. A sudden gust of wind which quickly subsides will disturb the motion of the aeroplane, and the important requisite is that it shall quickly settle down into its original steady motion. Or thise to happen it is essential that the state of steady motion in question shall be dynamically stable. If thise isn't the aeroplane will either deviate further from the equilibrium position, or oscillations will beset up which will continually increase. A permanent change off of V7 ID velocity, say V, will cause an alteration in the conditions of equilibrium, and the aeroplane will have to acquire the steady motion consistent with the new conditions. The relative velocity of the aeroplane when moving steadily is u. The aeroplane will in future have to move with a relative velocity u and the refer a resultant velocity compounded off slash and v. This again involves the condition that the new steady motion shall be stable. The subsequent problem is just the same as if the aeroplane had remained in still air, but had from some cause or other been jerked in such a way as to impart an initial velocity toid equal and opposite to f. 168 General Conclusions Chap. Periodic guds of a wind would, of course, give rise to forced oscillations, thus presenting a further problem for the mathematician, as we have only here considered free oscillations. If the period of the gusts happened to coincide with a period of free oscillation, a swaying motion would beset up which might become dangerous. How the theory of forced oscillations shows that when the free oscillation is a damped oscillations, the forced oscillations don't in these cases increase beyond a certain limit. The damping of the oscillations thus becomes important, and this is secured by giving the aeroplane adequate dynamical stability. 104. One difficulty still remains, and shows the need of making the motion of airplanes the subject of further mathematical investigations than have been possible in the limits of this book. Investigation of stability may, from what has been said above, be fairly well sufficient when we have total with the effect of ht gusts of a wind, where the change of wind velocity vismol compared with the velocity u of the aeroplane itself. It is, however, important that investigations should be made of the dynamical effects of a sudden squall of wind of the most violent character, that an aeroplane is liable to encounter in the course of its flight. Further feature of such an investigation should be the calculation of the stresses set up in the framework of the aeroplane by human pressures. The problem is one of the many unsolved problems awaiting solution at hands of mathematicians, of which a list is given at hand. The important condition to be satisfied in such a case is that the motions initially imparted to the aeroplane shall not be of such a character as to render the machine unmanageable. In this respect, suppose we may take it for granted that rotations are the most objectionable motions, and that it is essential that these shall be small. If these be assumed, it is probably an easy matter to. 9 General Conclusions 169 reconcile this condition with the conditions of inherent stability. Thus, if an aeroplane is fixed with a vertical rudder plane in the rear, a side gust of wind will cause it to swerve round and face the wind. If it has the vertical rudder in front, it will turn away from the wind. If, however, it is provided with fins both fore and aft, and their combined serrator of 7 sure is at the centrum of gravity. Side wind will cause no rotation about a vertical axis. If the fins be raised above the center of gravity, as in the arrangement of section 84, a side wind will cause the aeroplane to heel over about the line of flight, but the rotation thus produced will be damped by the resistance to rotation depending on the term containing /cos in our equations, of Hickley is large. In any case, the rotation can be minimized by making the height of the fins not too great. And it will be seen that this is exactly what the conditions of stability require. As in section 86, the center of pressure of the fins is placed slightly in fro 7 at off the center of gravity. The conditions of stability require that its distance in front shall not be too large, and this is in accordance with the requirement that the rotation set to be aside t wind shall be small. The construction of airplanes with fore and aft auxiliary surfaces for longitudinal balance and stability, moreover, provides the framework on which itly remains towed the necessary vertical fins required for lateral stability. The Curtiss biplane already has a triangular vertical fin in front and a vertical rudder in there are. The oft were raised fins placed fore and aft is no new thing, for such an arrangement is shown by Lanchester in connection with models constructed by him in 1894. The Langy aerodrome consisted of 2 pairs of General Conclusions ch. Roman 9 upwings placed tandem with arrow behind. Having regard to the partial analogy between the ifix up wings and vertical fins, this type possessed some resemblance in its properties to the arrangement with 2 raised fins, and was probably laterally stable. This view is confirmed by the records off its flights. At Assam time, the stability of such a type deserves more detailed study. And it is with regret that it is no crowded out offer text and placed in our list of unsolved problems. After X, comparison with other theories. 105. We are only concerned with investigations directly related to the present work, saw that the following remarks only refer in many cases to the particular sections of the writings in question which deal with stability. Bryan Williams, 1903. The resistance derivatives were here divided by mass of the aeroplane. The X of this book was therefore then denoted by X. There was a term denoted in our present notation by EV, X plus Y, omitted in the expression for section, which was incorrect to the extent. Captain Ferber, 106. Captain Ferber assumes in first place that the surfaces of an aeroplane can be replaced by three equivalent fictive surfaces, S, and three planes mutually at right angles. This is true in certain cases, but not in the sense implied in his footnote, where he assumes that a surface can be replaced by its projections, and that theta will be small. If instead of an inclined surface, we consider its projections on the three coordinate planes, then when the wind is blowing parallel to off one frock. Royal Society, 73 June 1903. EQCLA Hillary 67, I Roman 2 October and November 1905. 171. 172 Other theories chap. Thesis there will be no pressure EU a perpendicular direction, such as there was on the original surface. Ferber's theorem is true in the following sense. We assume that an idle aeroplane is a system built upon non-interfering surface elements, the air resistances on which follow rigorously the sine law for all angles of incidence. Then by applying a similar transformation to that inelasticity or in dealing with moments of inertia, we can show that when the system is moving without rotation, there are three mutually perpendicular planes, so that the component forces due to resistance are the same in magnitude and direction as would be produced if the system were replaced by three areas, S/S, situated in these planes. Calling these the principal planes and their intersections principal axes, we can show that if certain conditions are satisfied, the equivalence can be extended to the moments of the forces by suitably choosing the positions of the reas ISE, 6, S in their plane. Conditions require that a wind blowing parallel to principal axis shall produce no couple about that axis, the exceptions thus being surfaces analogous to screw propellers. For an airplane with own plane of symmetry, these conditions are satisfied. When the FEX off rotation are taken into account, the equivalence no longer holds good. This is shown by our proof that fins give lateral stability that cannot be obtained with one. Captain Ferber thus neglects the most important FEX off rotation in his treatment of lateral stability, namely the terms depending on the moment of inertia off the main plane areas. A second sequence, probably off thighs, gets a cubic instead of a biquadratic for lateral stability, or Ashe calls it, an equation off the fifth degree with 0 roots. The extra degree is accounted for because including thezimuth among the variables, and a has been pointed out. Stability and azimuth does not come in todextion here anymore. X other theories 173 than in other forms of locomotion. The presence of other 0 root shows that there is something wrong with the stability. The neglected term / really is of first importance in the problem when we're dealing with aeroplanes, the surfaces of which have considerable span. Thusi of Euler's angular coordinates is also somewhat unfortunate. For as we have pointed out, the system is unsuitable for investigating oscillations about a position of equilibrium. Captain Ferber's equations breaking down if we put equals, see section 14 of this book. Lanchester, 107. In most points of fundamental importance, there is substantial accord between the present conclusions and Lanchester's, and the main differences are in the method of treatment. Lanchester's condition of longitudinal stability is based essentially on what we're called the hypothesis of narrow planes flying at small angles, and it agrees with the result here obtained in simplest case of horizontal flight, although it is probably correct to say that the method of obtaining an appearance of being want in Ginriger. Lanchester starts with a study of phugoid curves described by an ideal plane which always places itself tangentially to the direction of motion, drift and rotatory inertia, thus being neglected. He then applies corrections for resistance and moment of inertia, and in the latter connection takes account of the effects of the Willary tail on the rotatory motion. In doing so, he assumes the motion tobe harmonic and takes Themian effect over each oscillation instead of writing down a differential equation. The reason why Lanchester's method leads to correct aerodynamics, London, 1908. 174 Other theory LS chap. Results will be evident once meaning the discussion of long oscillations and their trajectories given in section 52, 53 of this book. In applying approximate methods to spare the long oscillations, two successive approximations are shown to be necessary. The first approximation determines the period of oscillation, and the trajectory of the aeroplane is shown Tothus order Toboff the character described by Lanchester. Toban affected by the rotatory inertia of the mass. To determine the modulus of decay, a second approximation taking account of the rotatory inertia is necessary, and the fact that the modulus of decay is of a higher order than the frequency justifies the averaging method adopted by Lanchester. But as an necessary consequence, of course, Lanchester's method does not give the short oscillations or even indicate their existence. Sufficiency of his condition depends on the fact, shown in section 51, that the conditions of stability for the long oscillations necessarily involve the conditions of stability for the short ones. In case of lateral and directional stability, Lanchester does not use the three equations of motion, but is careful to chase the interdependence of the three motions, which would be determined by these equations. He also emphasizes the necessity of bent-up planes, or both if an aeroplane is stability. Whether the stability is to be described as rotative or asymmetric is a question of terminology. Under the heading of fin resolution, Lanchester gives a discussion practically amounting to the same thing as our applica tion of the principle of parallel axes to the second moments of the fins. This method shows the essential difference between a single fin and a pair of fins, one in front and one behind, in the matter of producing stability. The coefficients which denote by slash are expressed in terms of quantities called the aerodynamic and aerodromic radii. See section 93, above fora. Other theories 175 discussion of the effect of assuming them unequal. The stability in non-horizontal flight is not discussed, but an experiment is described in which a model turns suddenly round sideways at particular points off its flight path. And the conclusion is suggested that owing to longitudinal oscillations, the straight path became laterally unstable at hose j points, where the inclination of the flight path exceeded a certain limit for stability. Brillouin/108. Prof. Marcel Brillouin approaches question of balance and stability from a different point of view. His investigations refer mainly to static instead of dynamic instability, and he seeks by the study of metacentric curves to discuss the conditions that an aeroplane shall have unique position of statically stable equilibrium and thus be self-righting in all positions. He proceeds to study the effect of maneuvering on the balance of an aeroplane, and his investigation thus becomes independent of the problem of inherent dynamical stability. Reisner, 109. First of fluorescent articles of considerable interest, Dr. H. Reisner of Aachen places the problem of lateral steering of airplanes on an exact and formal basis. In a subsequent article, he points out the insufficiency of the conditions for lateral stability previously proposed and the necessity of a further condition, thus confirming the conclusions of the present investigation. Krakow, 110. Lieutenant Krakow's principal paper refers to dirigible mode airplanes. In investigating the Longitudinal U-des aeroplanes, surface Mehrcentric Pi. Rentemechanik, 1909. To Zeitschrift Filler FL Mytechnik und Motorluftfahrt, 1910, 910 and F. Expo H, 1910-11. Bollettino della Società Aeronautica Illidiana, April 1907 and June 1907. Guillaume Blue Book, 1909, 10 pp. 41, 161, 176 Other theories chap. Longitudinal stability, he obtains a cubic instead of a biquadratic, based on the equations of rotation and of vertical motion. The equation of horizontal motion is thus ignored. This is certainly incorrect in the case of an aeroplane. Both Lanchester's and the present investigation show that in the longitudinal oscillations the variations in horizontal velocity play a predominating part, and moreover, have proved that the conditions of stability depend more on the long than on the short oscillations, stability for the former in general sufficing for the latter. For directional stability, Krakow again obtains a cubic, which is certainly inapplicable to aeroplanes. Even in the case of a dirigible, Krakow's fundamental assumption that the velocity is constant within the time considered is open to serious question. In another note, tension is called to the stability condition, which requires that for a single lifting aeroplane the neutral plane must be behind. It is pointed out that for a double lifting aeroplane the condition a positive has equivalent effect. So Rho/111. For longitudinal stability, Soro certainly obtains a biquadratic and deduces conditions analogous to those obtained in the present investigation. In connection with asymmetric stability, he falls into the common error of not recognizing the interdependence of stability for rolling and directional stability, thus applying the term lateral stability in its most restricted sense. He's thus led to conclusions with which the present writer altogether disagrees, and which are further in conflict with Thettrand of Lanchester's chapter on subject. Soro would do away with vertical auxiliary surfaces and bent-up planes, and would, in particular, avoid vertical et actual et avenir de aviation. Memoirs de la Société des Ingénieurs CLHUs DP France, LFL 08 Roman 2. Blue Book 909-10, pp. 54-154. Other theories 177 auxiliary surfaces raised above the center off gravity. See Blue Book, p. 66. In other words, he would leave his machine inherently Lewis-stall and would use a gyroscope or other similar contrivance to counteract automatically this defect. Lecornu/112. The government abstracts contain a reference to Lecornu's paper on graphic statics, which, like our discussion in section 36-47, deals with the application of graphic methods to the forces acting on an aeroplane, the sine law of resistance being assumed. Asterisk sur la statique graphique de aeroplane. Govips Rendis, February 22, 1909. 2 Blue Book, 1909-10. After Excel problems. 113. The following problems refer partly to questions not coming within the scope of this book, and partly to points which it has been considered scarcely desirable to discuss in further detail in the preceding pages. Some are pretty simple, and could be treated as exercises or research subjects for a science student of their ability. Others would involve mathematical investigations or experiments, or both of a prolonged character. 1. Characteristics of a system of idle planes following the sine law of resistance, i.e. the determination of the simplest possible scheme of equivalent planes. See note on Captain and Ferber, section 106. Purely mathematical investigation. 2. The steering of an aeroplane in a horizontal circle. A study of Dr. Reisner's paper on the subject, section 109, will certainly show possibilities of further investigation. 3. The stability of a dirigible, and in this connection the discussion of formulae that shall best represent the resistances due to inertia combined with head resistance, in view of the fact that the hydrodynamical formulae for inertia effects refer, of course, to motion in an incompressible, unresisting medium. The 6 equations of motion tobused and not assumed independent unless shown to be so. 4. Determination of initial motions set up when an aerog lane incidentally struck by a gust of wind in any. Th. Roman 11 problems 179 direction, longitudinal, lateral, or vertical, or compounded OFL 3. 5. The calculation of stresses set up in the framework of the aeroplane in such a case. 6. Experimental investigation on the effects of rotation on broad planes, and if possible the determination of formulae, empirical or otherwise, which shall represent these effects at least approximately. 7. Experiments on the wash caused by front planes on back planes, also on the effects of wash caused by propellers. 8. The effect of center of gravity on longitudinal stability, i.e., a further development of the method suggested in section 69, for an airplane the planes and propeller of which are both raised to the same height. 9. Experimental study of the effects of inclination of flight path and stability. 10. More detailed examination of the effects of product of inertia, von lateral stability. We'll be seen that in our investitue, F has been retained in most of the fundamental formulae, but that in the final deductions we have usually put F0, thus assuming the line of light Toba principle axis of inertia. A deviation from this condition may either increase or decrease the stability. The investigation may become important. 11. The lateral stability of types like the Langley aerodrome, consisting of 2 pairs of bent-up wings arranged tandem. Mathematics isn't this case bound, tobe fairly heavy. 12. A more extended descriptive examination of nature of the symmetric oscillations and the motions associated with them. 13. The investigation of the forced oscillations set up in an aeroplane by periodic gust of wind, with a special reference to the case of synchrony with the free oscillations and the influence of damping in this case. N2. I80 problems chap. 14. The possibility or otherwise of helicoidal steady motion in the case of a symmetrical aeroplane, in particular when steady motion in a straight line is literally unstable. 15. A further discussion of the effects of camber on both longitudinal and lateral stability. 16. A complete mathematical investigation, in the form of a thesis, on stability and oscillations of a kite. Special reference to action as to how far the resistance derivatives and stability of an aeroplane could 1. 6. Investigated experimentally by flying the model, a sack kite. 17. Experimental determinations of the resistance derivatives of airplane models by attaching them to whirling tables or pendulums, with a special reference to those derivatives which depend on rotation, comparison with calculated values, experimental flights with the same models, and comparison of their behavior as regards stability with their results of calculation. 18. Further photographic determinations of the paths and oscillations of model aeroplanes and gliders, with special reference to their lateral oscillations. 19. The graphic statics of longitudinal equilibrium for systems of 3 or more planes having different abscissa pound e, effect o faltering the inclination of on off them relative to the aeroplane. 20. Finally, the discussion of the equations of motion of an aeroplane in their most general form, and the search for cases in which these equations admit of exact integration, is probably a mathematical J-problem which, like the well-known problem of three bodies, may well occupy the attention of pure mathematicians for the next half-century, and still leave plenty of work to be done. 11 notes I8I examples. 114. Particulars of the construction and dimensions of the leading modern aeroplanes will be found in most aeronautical journals and manuals and engineering papers. An abundant supply of examples can be obtained by calculating their stability by the methods of this book, determining the coefficients of the biquadratics for longitudinal and lateral oscillations, approximate solutions of the biquadratics, periods and logarithmic decrements, or, in the case of instability, logarithmic increments, of principal oscillations. Notes: gyrostatic action of propellers. 115. The gyrostatic effects due to the angular momentum of a single propeller not only affect the steering of Q aeroplane, as this will known but introduce interdependence between the equations of rotation about thexes of E and Z, thus mixing up the longitudinal and lateral oscillations. Narrowgrous investigation. All 6 equations of motion would have to be considered simultaneously. This plan is undoubtedly to destroy the gyrostatic couples either by the use of twin screws rotating in opposite directions, or by following the suggestion of recent French inventor who makes the rotary engine and the propeller rotate in opposite directions, so that their gyrostatic effects cancel. A pair of cogwheels is all that is required. If the gyrostatic couple is small, a solution of that problem could be obtained if it were worthwhile to do so by approximate methods. Or a first approximation, we should neglect the effect altogether, so that the oscillations would fall into symmetric and asymmetric. I-82 notes chap, metric groups. We should then apply small corrections for the symmetric motion set up with the symmetric oscillations and vice versa. If an asymmetric and a symmetric oscillation happen to have nearly the same period, resonance effects would be set up with W-lich physicist familiar, and the aeroplane would probably not be very comfortable one to travel on. A proposition on automatic control. 116. The name automatic stability is now applied to devices for regulating the balance of airplanes by means of gyrostats or other mechanical contrivances. In this connection, the following proposition may be useful. An aeroy lane formed off idle straight 2 lanes T with no vertical finsorentup surfaces cannot hindered laterally as fall height use of gyrostats or gian. Diddums alone. This applies even to the case where the aeroplane is provided with warping devices or ailerons, if these are only brought in token by the operations of the gyrostat. Proof: in order that the plane of symmetry should tend to assume a vertical direction when the machine is disturbed, the gyrostat must be sensitive to variations in the direction of gravity relative to the machine, since the vertical direction is entirely defined by gravity. Now, suppose such a machine, initially moving horizontally, to be heeled over sideways through an angle slash. By assumption, there are not tangential resistances. Therefore, the machine will slip sideways with acceleration g-sin. The inlay effect which the gyrostat is able to detect is equivalent to change in the intensity of gravity from g to cos, the direction of the latter component relative to the machine being unaltered. There is nothing, therefore, to make the gyrostat bring the machine back to the vertical. 11 notes 183 the inlirum de istorad the acceleration g-sin, or make it evident in some way or other. This can only head on by the use of some kind of in-source stabilizers or their auxiliary surfaces attached to the machine or to the gyrostat. In any case, it is impossible to do this without an equal degree making the gyrostat sensitive to changes in wind velocity. When this is admitted, it might just as well do away with the gyrostats altogether and rely on the auxiliary surfaces instead. One further point should, however, be considered. Aeroplane might be provided with auxiliary surfaces calculated to make it more inherently unstable, and gyrostats might be used to convert this instability into stability, as is indeed actually done in Brennan monorail. What Isher implied is that if an aeroplane, when tilted over sideways, tends either to return to the vertical position or to deviate further from it, gyrostats may be used with effect, but if it possesses neither tendency, it become ineffectual and some kind of auxiliary surfaces must necessarily be introduced. Note on the critical inclinations. 117. In discussing the effects of inclination of light path instability, we came upon the 2 limiting relations, tan plus 2 tana equals 4 longitudinal, and tan, 2 tana equals 4 lateral stability. It is useful, therefore, to get some rough idea as to and wherefore of such condition. Their dependence on the law of resistance, consider a single plane area the pressure on which obeys this law. Draw the curve r sin equals constant, and as long as the relative wind velocity is represented by a radius vector off this curve, the pressure remains constant, and if the plane receives a small additional velocity d in a direction tangential to the curve, the same. 184 notes chap. T Leonoff occurs. If a direction oft f deals within the curve, the pressure decreases. If without, it increases. Thingle fig. 38. Between 7 and the direction off d backslash when the latter ist tangential ist in tilde, or d odgder, equals u backslash tilde backslash 1 tan e. If no theoria is a kite placed in a horizontal wind, a being the inclination off its face ta the horizon. If the kite is kept in place by a string whose inclination ta the vertical I less than thingle whose tangent equals 2 tan a, it will be seen that a small additional upward velocity perpendicular to the string will increase the pressure and cause the kite to rise further, while a small velocity fig. 38. In the opposite sense will reduce the pressure and cause the kite to fall. This result indicates instability. For stability, the inclination off the string to the vertical must be greater than tan tilde, 2 tan a. A complete discussion of the conditions of stability would, however, necessitate taking account of equations of rotation, as well as translation. We may similarly show, with the assumptions of section IQ, that if the main plane of an aeroplane receives a small rotation in a plane whose inclination to the line of flight is given, it in tilde 2 tana knockuples aero setup. The limiting condition tan equals 2 tana for lateral stability thus represents the fact that knockuples aero setup if the aeroplane receives a small rotation in a horizontal plane. 11 nomenclature 185 the same thing can be seen by means of the general expressions, 23 of section 20. The condition d equals may be written 0, cos 6y sin 6l, LP LQ equals 0, m 1 and is the condition that the equations p cos 6 tilde q sin 8 equals WL plus PLP plus QLQ equals W mi plus PM plus QMQ equals should be compatible. In other words, that the motion characterized by Roman 4-2, J which gives rise to couples LM should bear rotation about a vertical axis, as indicated by the condition P cost, Q sin equals 0. The limiting condition, tan 6 equals 2 tana for longitudinal stability arising out of the expression for S, is more difficult to explain. Forever ta the general equations, 18. Assuming AU equals an IV, equals the condition becomes W sin 6 plus 11x equals, or W sin 6 plus 2x equals 0. And leads to the statement that for stability their resistance due to the component of gravity in the line of flight must be less than twice their resistance due to the air. The effect of head resistance is to increase the latter, and this is it increases the angle at which the aeroplane can rise. Nomenclature 118. Psissa, lie accordance with our system of coordinates, the psissa of an airplane is its distance in front of the center of gravity, being negative if the plane is behind. Aeroplane and plane. In accordance with the Aeronautical Society Committee's recommendation, aeroplane equals a flying machine, while plane equals one of its surfaces. In most cases in this book, a pair of superposed planes counts as a single plane for reasons explained. I-86 nomenclature chap. Angle of attack. This is the angle at which the air blows on any given surface. In an aeroplane moving steadily, it is the angle which a plane makes with T-lie direction of flight. It is sometimes called the angle of incidence, but the optical analogy suggests that this name would better be the angle which the current makes with the normal to the surface. Axis of coordinates. The center of gravity just taken as origin. Line of flight in steady motion is the axis of A perpendicular line in the plane of symmetry measured downwards is the axis of I, and a perpendicular to the plane of symmetry is the axis of Z, the three forming a right-handed system. Fin. A vertical auxiliary plane. Inherent and dramatic stability. The term dramatic stahai usage is no frequently applied to mechanical devices with movable parts, such as gyrostats. Likely are so arranged to store equilibrium when an aeroplane or other system is displaced. The Brennan monorail alphabets one of the simplest illustrations of automatic stability. An aeroplane is inherently stable when stability is secured without the movable parts, and the lie kind of stability considered in this book is inherent dynamical stability. Narrow planes. Planes off which theccord or breadth is small that when the plane rotates about an axis parallel to the axis off the diffel, rents off velocity off front and back edges is negligible, i.e. the rotary derivatives RNS fluoidal. Plane of symmetry, aeroplanes, practically without exception, aerosymmetrical. When flying in a straight line, the plane of symmetry is a vertical plane through the center of gravity containing the line of light. 11 nomenclature, 187 resistance derivatives. If small changes are made in the velocity components of an airplane, the ratios to these of the corresponding changes in the values of components of air resistance I call the resistance derivatives. Rotary derivatives. Their resistance derivatives arising from a small rotation of a plane about an axis through its center of pressure parallel to the axis of single and double lifting system. Neutral surfaces where an aeroplane has two surfaces or sits off superposed surfaces, and through off the aeroplane is borne partly by the front and partly by the rear surfaces. I call it a double lifting systemery. If the whole weight is borne by a single surface or set off superposed surfaces, I call it a CKJLE lifting system. In such cases, any other auxiliary surfaces, such as tail planes, must be parallel to the direction in which the blow s on them. And I call this position neutral. Small angles, when the angle of attack is called small, it is simply that their distance may be taken to follow the sine law. Stability, static and dynamic. A system in equilibrium is statically stable if, when displaced, it initially tends to approach its original state of equilibrium. It may, however, go past its equilibrium position and oscillate, and if the oscillations continually grow larger and larger, it will be dynamically unstable. For dynamical stability, it is necessary that the system should either return to its equilibrium position without oscillating, or that the oscillations should gradually die-out. In present book, stability means dynamical stability. Stabilizer in this book term is applied to small bentaplanes attached at extremities off the main planes. 188 notation chap. Straight and bentaplanes. When thewings off an aeroplane form at a hedral angle, I call them bent up. Straight planes, on the other hand, project perpendicularly on both sides off the plane of symmetry, symmetric and asymmetric stability. Symmetric stability is practically synonymous with longitudinal stability and represents stability for motions in the plane of symmetry. Symmetric stability is stability for rotations about thesis offs and displacements along thesis offs, and includes what are sometimes separated as lateral and directional stability. Itis Lochester's rotative stability. 119. Notation. A, B, C moments of inertia off airplane, F product of inertia. Percent 6, CO efficients off-bic duodratic with suffix O for symmetrical. J for asymmetric oscillations where distinction is necessary. A angle off attack, add J, angles off attack in a double lifting system, and in this case A equals A. Phi angle at which a plane is been up. A semi-chord off plane, H semi-span. Z radius off curve at your off-cambered plane. D, distance off centroid off areas off edge dare off transverse planes from center off gravity. F, corresponding distance off center off pressure off the pair. E, a constant determining the displacements off center off pressure off a transverse plane. E, a certain constant referring to the Antoinette type under lateral stability. 11 notation 189F, product off inertia off airplane a sabo. JA, function off angle off attack determining law of resistance. 0, a corresponding function determining position off center off pressure. FA 4 \A differential coefficients with respect to FA, A rotary derivatives corresponding to small angular velocity V. H propeller thrust, H its perpendicular distance from origin, T its inclination toxis off when different from 0. / moment off inertia off a transverse plane with respect to plane off symmetry I equals I cos A. K coefficient off resistance in R equals KSU FA or R equals KSU Sina. K radius off duration about axis offs, 7 equals TFZ. / distance between front and rear planes in longitudinal stability. / MN. Direction cosines off normal to a bent-up surface element. LMN couples about axes due to resistance in directions opposed to rotation. XMN their values in steady motion. LMJSF with suffixes e.g. L the corresponding resistance derivatives. LJ equals DLD2. 3/1, 3EO, P moments and products off inertia of S3 stem off to a more vertical fins Whitley respect toxis through their center off pressure parallel to the coordinate axes. The coordinates of the center off pressure being X, Y, Z. X coefficient in a small oscillation or disturbance proportional to, hence root of the biquadratic. Phi tangent off angle off attack / equals tan A. /A field. Tangents off angles off attack in double lifting systems. The difference off these tangents equals at U to P Q R components off angular velocity off airplane. R resultant thrust off air on a plane. 90 notation CH. Roman 11b, radius off duration off a pair off planes, where TIN's notation causes not confusion with the previous one. P distance measured from dihedral angle on a bent-up plane. S area off an plane surface, S equals scos a T, area off a vertical fin or pair of stabilizers, also total area off several fins. Z7, velocity in steady flight. UV Roman 4, added velocity components in a small oscillation. W, weight off airplane, X, Y, Z coordinates. X, Y, Z components offers due to resistance taken positive when acting in the opposite direction to thesis. A Y, Z values in steady motion, etc. Corresponding resistance derivatives X equals dxj du, a certain constant in connection with stabilizers. D, inclination off light path to horizon. Positive when descending. In small symmetric oscillations, 6 equals 6 plus E, where $ is the value corresponding to steady motion. This notation causes not confusion with the other meanino of mentioned above. V, ratio off-head resistance to drift. F, angle through which plane off symmetry has rotated about axis offs, measured from vertical position. Index aerostat, 54 Antoinette type. 158-164 approximate solutions op quadratics, 79-132 aspect ratio, 149 asymmetric derivatives, 123-128 asymmetric oscillations and stability, 5, 12, 27, 31-33, 123-164. Automatic stability Roman 6, 182, 186 bent-up planes, 151-164 Blériot aeroplane, 152 Brillouin, 4, 70, 74, 175 broad planes, 106-113, 121-122 Bryan and Williams, 4, 35, 171 camber, curvature, 50, 114, 148 center off pressure, variations of 11, 68, 69, 106-113 Chinook glider, 58 conic, application off geometry of 72-74 critical inclinations, 183 Croco, 4, 175 Curtis, 117, 169. Aeroplane, 130 damped oscillations, 30 directional stability, 5, 27, 174, 176 dirigibles, 4, 36 discontinuous motion, 1 double lifting systems, 61-74, 95-116, 143-144 Edward Mines aeroplane, 110 F-effect off-tilting planes, 64-66 equations off motion, 19-23 equivalent systems, 10, 95-101, 119 Euler's angular coordinates unsatisfactory, 20, 173 examples, material for 181 extremities off planes, correction for 149 Farman, 117, aeroplane, 118 Ferber, 4, 171 Ferguson, Roman 7 fins, 30, 128-132, 135-143 Formals off transformation, 48, 49 friction, 113, 147 glider, 10, 89, 90, 111. Glossary C nomenclature, Government Advisory Committee. Reports 2, 4, 8, 46, 175, 176, 177 graphic statics, 9, 57-74, 177 gravity. Effects of 135 Greenhill 2 Gregory R. A. Roman 8 gusts offwind, 167-170 gyrostatic action, 181, 182 Harper, Roman 7, 10, 14, 88, 94, 104, 129, 140, 142, 154, 158 head resistance. Effects, 90-93, 144-147 Helmholtz, 1 hydrodynamics, 17 inclination of flight path. Effects of 9, 88-90, 111, 120, 121, 138, 139-141, 142, 156, 162, 164, 183-185 inclination of propeller axis, 87, 88 independence of height, principle of 9, 53-56 invariance, 99-101 Jones, Robert, Roman 7 Chi RCH Hoff, 2 Lau, 117 Lanchester, 4, 9, 77, 115, 136, 169, 173 lateral stability, 12, 31-33, 123-164 Lecornu, 177 Lefebvre aeroplane, 96 longitudinal derivatives, 38-56 longitudinal equilibrium, 57-74 longitudinal stability, 27-31, 75-122 long oscillations, 80-84-87 metacentric curves, 70 modified conditions off stability, 35-77-79 modulus of decay, 30, 80, 134, 192 index narrow planes, 8, 51-53, 123-126 neutral tailplane, 57-75, 109 Newton, 1 nomenclature, 185-188 notation, 188-190 Parich, plane, 54 pendulum experiments, 46, forces on, 54 primitive conditions off stability, 35-77 problems, 178-180 propeller thrust, 22 propeller thrust, central 58, 61-66, 75-100 propeller thrust, non-central 60, 71-74, 101-106 propeller thrust, variable 26-93, 145 raised fins, 135 raised planes, 113 Reisner, 4, 175 resistance derivatives, 6, 3,336. 38-48, 52, 53 rolling, resistance to 133, 135 rotary derivatives, 8, 41, 44-48, 112, 121-122 rotative stability, 5, 27, 174 Raugier, aeroplane, 143 Routh's discriminant, 6, 30 short oscillations, 80, 81-84 simplest case off longitudinal stability, 75-79 sine law 52, 124. Deviations from 114 single fin, effects of 128 single lifting systems, 9, 56, 57-61, 55-94, 109, 154-158 single plane without rudder, 110,113 small angles, 8, 51, 7,577, 1U3, 124, 131 Soro, 4, 176 speed limits consistent with stability, 77, 112 stabilizers, 153-158 steady, ocean 23 straight planes, 126 SVM metric or longitudinal dairy S-addives, 38-56 SVM metric oscillations and stability, 5, 27-31, 75,122 three-plane system, 12, 117-121 trajectories, forms of 83, 87 transformation formula, 48-49 two-fin system, 135, 138, 141 Turnbull, 50 twin scree M's, 145 variable propeller thrust, effects of 26, 93, 145 wash, 95, 115, 150 whirling table method, 45 Wright Brothers 383 aeroplane, 139 CR, Avon Sons Limited, Brunswick St. Stamford St. S.E. and Bin. A V Suffolk, 8I00, page 209, page 210, page 211, page 212.